Ciao. Questa è la piccola, devo scappare, ci sta. Noi un dottorato comune che avrei potuto fare esattamente questa cosa, però ha temporeggiato troppo.
Sì, quando vuoi, volentieri.
Come? Si è appena connesso. Questo sta pronto?
Giusto, non sapevo chi piacere. Siamo in fila. Piacere.
Sei collegato?
No, se no è davanti. Quindi è
Ah, perché adesso ci sono questi. Cioè, mi è appena arrivata la mail perché devo andare.
qui un po' no, è cosa che ci sta, cosa si sta ancora nel dossier. Che è presente?
Sì, sì, sono tutte in mano.
Tranne l'ultima che forse tranne l'ultima. Sì, no, ma probabilmente ci sa che parla.
Dicendo di uploadare le slide il giorno prima e poi non ha mai interagito.
So I think we can start. Can you hear from Zoom? Okay. Okay, so welcome to this special session. I'll be the chair of this session. I'm Matteo Cadeddu. And first of all, let me say that we are very proud to have this session on diversity, outreach, and education for the first time here at Nufact. And we are also happy because we received so many interesting contributions. And so let's start with the first contribution, which is Lorenzo Galante, which will talk about particle physics role play games in introductory physics courses. And you have 15 minutes plus 5 minutes of questions. And if you prefer, I will notify you when your time is approaching to the end of it. It depends on you.
Does it work? Yeah.
Yes.
It's working. Okay.
So let's start.
Okay.
Thanks.
Thank you very much. Good morning. This talk is entirely dedicated to a physics course for first-year engineering students at Politecnico di Torino. The title of the course is From Conservation Laws to Scientific Discovery. It was an in-depth course which was connected and ran in parallel to the Physics 1 main course, in which basically at Politecnico students learn mechanics and thermodynamics. It was held in May 2021 in distance learning mode in the form of a role-playing game, RPG from now on. The idea was to experiment with innovative educational methods, and therefore the course was designed in order to foster the active learning of the students, and also to try to switch on to boost the identification of the students with what is being studied, which is a very important issue, and also to increase their motivation in the study of physics, which is often a lacking issue among our students. In order to meet all these goals, we decided that the course would be delivered in the form of a role-playing game. Now I would like to give reasons why we choose role-playing games. The idea is quite simple. In a role-playing game, you ask the player, which in our case are students, to play a character, and also to imagine the scene, the setting in which the game takes place, which is why we thought that the gaming framework was the perfect learning scenario where to switch on the identification of the students with what is being studied. Of course, we didn't ask them to play the role of a wizard or of a king or a knight, but rather we asked them to play the role of a physicist. Indeed, we have done even worse because we asked them to play the role of a particle physicist. Sorry? Okay. Within the game, the instructor, which is also the master of the game, tells a story, describes a setting, and asks the players to overcome challenges. And while they overcome these challenges, they also gain competences. And these competences are gained through their own work, their own reasoning. And this is exactly what we mean by active learning. Even the motivation in the study of introductory physics can be increased, fostered within the game framework, since the instructor has the opportunity to break the typical educational pattern, which sees the students that study a topic just to solve an exercise with a precise goal of passing the exam. On the contrary, in the game, students have the opportunity to explore and to discover the beauty and the power of physics law, because these laws becomes the tools in their hand that they have to use in order to solve and overcome the challenges that are proposed. Now I would like to give you a brief description of the structure of the course, which was an 18 hours course. Actually, it was divided in two different but connected role-playing games. The first one was entitled A Case from the 20th Century Physics. And in these RPG, students were asked to play the role of a physicist, of a nuclear physicist from the 30s. And they basically have to apply what they have learned during the Physics 1 course about energy and momentum conservation law to address and to consider a situation which is inspired by the problem of the neutrino that arises in the 30s with the study of the neutron beta decay. And the second game, the second RPG is nuclear collisions. In these RPGs, the knowledge of the student is upgraded to a special relativity framework. And again, they have to use momentum and conservation laws in order to try to solve a mystery which is hidden behind a collision which comes from a real nuclear physics experiment. They have to discover which is the missing particle on the basis of the conservation of momentum and energy in a collision between a pion and the helium nucleus. Since the course was delivered in distance learning mode, it's quite important to spend a few words about the supporting technologies that helped us to deliver this course. We used Zoom meetings for each game section, and we also, each game session was also supported by an interactive site that you can reach if you want with the QR code that you see in this transparency. This is the homepage of the course, which also contains, these boxes are links to sub-pages, each one for each game section. I've called this site an interactive site because it's full of interactive application designed on purpose for this course, in which students have the possibility, the opportunity to active participate to their learning process. For example, on the right, you can see an example of interactive application. This is a real collision from a real nuclear experiment. With this application, students can learn how to measure the momenta of the particle involved in the collision. They measure the momenta through the radius of curvature of the tracks. This application gives them some circle. They have to fit with their own natural neural network, those tracks. And so they learn how to check if momentum and energy is conserved in a collision. Of course, the assessment during the evolution of the game, of the actions, and the reasoning of the students is quite important. Therefore, in the site, you will also find a lot of forms that the students are asked to fill, so that the instructor has the possibility, through a quick vision, to a quick monitoring of what they say, can control the emerging patterns in their reasoning and in their solutions to the game, and also on the actions that they take. The assessment, as I've already said, is important. They overcome challenge along the game, and these challenges, through the action of the assessment of the instructor, are converted in experience points that are then published on the site, so every student can has access to this table, to this spreadsheet, so that the students can see how many experience points they gained during each game section. And also the last column, the blue one, they can monitor the evolution of their level that starts from level 1 and increases during the game. Now I try to give you a practical description of how each game session was organized. At the beginning of the game, students were divided into teams that last for all the course. The instructor tells them a story and also describes the setting and asks them to play the character that is required to play the game. Then the teams are asked to overcome a challenge, a situation, a problematic situation, and they are given a certain amount of time in order to discuss which are the action they want to take, and also the solution, and to explain why they decided to act in some way. In this part, students work in private rooms. Each team has his own private room, which are called in Zoom breakout rooms. And they also are asked at the end of their game session to report what they have done by filling a form or by producing a document that the instructor has to try to look at during the evolution of the game. At the end of this game session, there is a plenary discussion among all the students, all the teams, and the instructor, in which they discuss the solution and the principle and pattern that emerged from their reasonings. And when the game ends, almost immediately, the instructor has to carefully have a look and assess their reports and their forms in order to refresh the table of the experience point that you saw before. Now let's speak a little bit of physics, because it was a physics course, of course, and I would like to enter in some detail about the first one of the role play games that were part of the course. The one is entitled A Case from the 20th Century Physics, which in a way is inspired by the neutrino hypothesis proposed by Pauli in the 30s. Actually, the game was divided in two parts. In the first one, they had a preparatory meeting, and in the second one, they played the real game, the actual game. So in the preparatory meeting, they have to face a simple situation in which conservation laws hold, and they are asked to focus on the number of the equation deriving from the laws and the number of unknowns in order to notice and recognize if the unknowns have some degree of freedom or if they are completely fixed. This is the first situation which is very simple, which they have to face with. They have a body which initially is at rest, the blue spot, which explodes, releasing an energy E in two fragments. They have to assume that one of the two fragments is emitted along the x-axis, and they are asked to write down the equation of the conservations, and they are asked also if the modulus of the moment of the two fragments are uniquely determined, and they have to explain why. Then there is a little bit more complicated situation in which the same body at rest initially again explodes, but this time in three fragments. Again, they are asked to write the equation, and they have to tell if they can see, if they see something about how the vector of the three fragments are disposed in space, and to explain why. Here we want to see, if we want to discover if they are able to, they can recognize that the three momenta are expected to be coplanar. This phase, this stage of the game of the course is a sort of problem-solving activity. They work in teamwork. They meet each other and start discussing, applying what they've learned during the main course. And then the game begins. The first stage of the game is a storytelling part. The instructor tells a story, tells them that they are nuclear physicists for the 30s. They work in a nuclear research facility, and with their group, they are working at the decay of a particle, which in the game is called the D particle. They are told that the detector they are using in their experiment only detects a charged particle, and that according to what they have seen with their experimental data, the D particle seems to decay in two other particles, E and F. They are also given experimental data collected during the experiment in terms of the momentum distribution of one of the two particles in which the D particle decays. And so they are put in front in a real situation that every experimental physicist has to face with, and they have to interpret the data. They're asked to interpret the data in the game while identifying themselves with a real nuclear physicist. And they have to discover if there is any problem or something odd in the experimental data that they have collected. And if any, they have to discuss possible solutions. In every role-playing game, the players have special powers, which often are related to magic. But in physics role-playing game, the special powers come from what they know. And so in this case comes from the Physics 1 course and also from the preparatory meeting. In fact, in the preparatory meeting, they considered and they worked with an explosion of a body in 2 fragments. And they hopefully recognized that in that case, the momentum of the 2 fragments was uniquely determined. So we expect them to recognize in this open problem about the data that they have collected during the experiment, they recognize that the momentum of one of the 2 particles, in this case of the E particle, since is uniquely determined, should be distributed around a single value like this and not over a wide range like the experimental data seems to say, to suggest. And now I would like to give you the reaction to this game of our students. And so we will discover how they act in front of this situation. We worked with 48 teams corresponding to nearly 200 students, and 98% of the team reported something was wrong, was odd in the experimental distribution. They had to interpret. 33% of the teams realized that in a case of a 2-particle decay, the distribution should have been centered around a single value, which is what we expect from them. And 33% of the team proposed as a possible solution to the problem, the emission, the existence of an undetected neutral particle, which is something quite similar to the Pauli proposal in the 30s to explain the continuous beta spectrum of the neutron decay. This percentage could seem to be a low percentage, but in my opinion, it's not, because we have to consider that these students are first-year engineering students, and they are, at the moment of the course, they are not so far from the ending of their secondary school experience. So, and they were also, we have to consider also that they were working in a context, in an educational context, which is like to swim in open water with respect to swimming in the pool. The context was very different from the exercise. I sneaked sometimes in their private room, in their breakout rooms, and I could notice in person that the discussion were really going in almost every direction on the solid angle. So they were really in open water. So this percentage is quite good, in my opinion, at least. At the end of the game, as I have already said, there is a post-game discussion altogether, plenary, and so the instructor has the opportunity to reveal to the students that the game they have just finished to play is inspired by a real historical fact. And so the student can learn something, and the teacher can tell them something about the story of the continuous beta spectrum that led to the discovery later of what we call now the neutrino. Now some student feedback, which is very important, again, in my opinion at least, that we collected with a survey. We collected 99 answers, and at the beginning of this course, we were really afraid because we were proposing a different method as a course. The educational approach was quite different from the usual one, but as you can see, the rating of the course in a scale from 1 to 5 was quite high, 4.40/5. And this was very encouraging for us. And at the question, what do you think about using a role-playing game for a physics one, which is the core question probably in this experimentation, we collected 99 positive answers. That was incredible. I read all of them and they were all positive, and that was astonishing in my opinion. I have selected three among these 99. The first one says it made everything more exciting. Another student told that I think it's very useful to push for deeper thinking. And the third that I have selected, it appeared to be a very light and engaging way of approaching complex topics. Last but not least, they also told us that they appreciated a lot the team working. That is to say, in practical terms, the phase of the course in which they worked discussing together in the Zoom breakout rooms, because they were experiencing lectures at very long distance from the teacher, where they had not the possibility to speak and to discuss among them. And so this is the rating of the question: how much did you enjoy working with team? And this again was very, very high. I finished. Thank you for your attention.
Thanks a lot for this very nice and inspiring talk. So let's see if we have questions or curiosities. Okay, in the room first. Okay.
Thank you. Really, thank you for your talk. Really inspiring and interesting. Just two brief curiosity. The first one is, inside the team, there are any role? Are students playing any role, or they are just any defined role, in the sense that maybe someone is approaching to the problem, the other ones are collaborating to solve the problem, and so on and so forth? And the second one is, have you any trace about how students inside the 33% have developed the idea of this new kind of particle? So the way in which they have reason to discover this new particle.
Okay, thank you for your question. The teams were made up without any criterion. They were all peers. There were no roles. The only thing that they were asked is to try to act like they were a real particle physicist. They have to try to identify in the role. This was not easy because of the lack of time. So, and also they didn't have a lot of time at their disposal. Therefore, in each team, they organized more or less in this way. But they were private. I don't know exactly what happened. But as far as I've understood, they had an initial discussion just to orient themselves in the problem, and then they divided the roles, because they had also to produce a document and to fill a form, and so they had to organize themselves. And this is important because they had the chance to develop some soft skill, which is very important. The second question is, yes, thanks to the forms and the reports, I have had a read of all, because I have assessed them, of all their reasonings, because the question was designed in order to try to highlight the way of reasoning. And so I have all the necessary information about how they reach this result. It is quite interesting, because why 33% over 98%? 98% was saying there is something strange in the experimental data, but 66% was biased by the physics 1 experimental session, in which they are obsessed with the normal distribution. And so the thing that they noticed to be wrong was that the distribution was not a Gaussian. And so they were biased in that way, and they get lost there. And so they start wondering about the limit of the speed of light, something very strange. While in the preparatory meeting, we were trying to focus them on the number of equations and the number of unknowns, in order to understand if the unknowns are fixed or not, or can vary. There were other questions? No, maybe it's okay.
Okay, there is a question from Zoom, Emilia.
Yes, hi, can you hear me?
Yes, very well.
Okay, thanks. So I also would like to say that it's a very nice idea. Now, my question is, did you ever consider like some other approach? Because, for example, while you were discussing the problem, I thought to an escape room game. I don't know if you are familiar, like you.
A bit. I have daughters that love it. Yeah. Oh, I didn't. Yesterday, during a beer with some of my colleagues here, we were drinking a beer near an escape room facility in Cagliari, and for the first time, I thought that what you are saying, but I don't know if it was quite difficult to put to organize this course. And the problem is the numbers. At Politecnico, we have thousands of students. This was a selection of only 200 students. And in any case, it was quite difficult to play a role-play game with 200 students, because usually at home, RPG are played in five, 6 person with a master, which is the owner of the game. So an escape room, maybe in a virtual environment, could be maybe organized with the help of someone which was very good at programming, probably coding. Yeah.
Okay, thanks. Thank you.
Thank you for your suggestion.
Okay, there is another question, quick. Maybe.
Krzysztof Mękała, University of Warsaw. Could you estimate how much time it took to prepare the game?
Yes, sadly I can. Well, a long part of time, a big part of the time was devoted to the creation of the interactive application that were embedded in the site, and that were already done, and where I prepared them during my PhD in physics education. So, but if you account also for that time, it took months to do that. However, they asked me to design a new course at Politecnico on the end of February, and the course started in April. And I have to work a lot in order to also to create the site and to create all the stories, and to think how to prepare the game for them. So did I give you a sort of an idea? Yeah.
Okay, so I think if there are no other questions, we can thanks the speaker again.
Thank you very much. Bye-bye.
And we move to the next speaker, which is also in presence here, Matteo Tuveri. Okay, we'll talk about creativity at its best, making science by making art. Thanks.
Okay, good morning, everyone. Thank you for the opportunity to open this new session about diversity outreach and education. So today I will speak about a INFN project, which is called Art and Science Across Italy. And in particular, I will focus on the role of creativity to foster the interest of students in science, with the role of art, with art playing the role of this fostering part of the interest of students in science. So the idea is that there is a gap between science and art in high schools, and sometimes people say science as a different object with respect to art, in the sense they apparently they appertain to two different domains. But if you put together art and science, you generate what is called now STEAM, and this is a powerful tool to improve creativity in high school students and in general in people, because creativity is also an important part of the scientific process. And so putting together science and art, you can foster student interest in science at all, regardless their specific skills or their level of knowledge in some peculiar aspect of science. How to do it? Starting from one important feature of science, that is collaboration, as we already seen before. Working in team is a useful tool to improve science interest in high school students. So during art and science project, students learn to work in group and collaborate with colleagues, also coming from different cultures and experiences. And also they learn another task, important task in science, how to design a project, to trying to explain something or trying to create something which is inspired by science. So again, art can be a useful tool to spread scientific culture in society and also in high schools. And so art-based activities are useful tools to integrate creativity, imagination, and science in school settings and programs. There is another interesting part, which we also, again, we have seen before, which is competition. Because competition is an element which can which suggests a positive association between the student participation in general in STEM competition. So, for example, math or physics competition in high school, and trigger students towards science. So, working in team, creativity, and the creation part are really inspiring objects to insert in these outreach programs. So Art and Science across Italy is a 2 years project. Here in Italy is funded by INFN and CERN, and we are now at the 3rd edition. During the years, many researchers have collaborated with us, coming from all the scientific fields, math, physics, chemistry, and so on. How is structured the project? Activities are divided in 2 years. In the first year, there is the educational part. In the second one, there is the creative part. During the educational phase, students can attend seminars made by researchers, visit museums or laboratories, participate to roundtables, and also participate to some contest or championship, as we will see in a few moments. At the end of the educational phase, it starts the creative one, where students have to design a project, which is an artistic project inspired by science. So they have to collaborate in a 3 people group, design an artwork. There are no restrictions about which kind of artistic form they want to use to express their scientific idea. So any artistic form is welcome. At the end of the creative phase, there is a local exhibition. With the term local, I mean regional exhibitions. The first 7 gain the national competition, so there are local winners which are allowed to arrive at the national exhibition. And during this exhibition, students act as a guide for the public. During the national competition, there are 24 to 30 winners, and they can go to a master. In the first edition was at CERN, in the second one was at Laboratori Nazionali di Frascati. So these are basically the numbers. During the first 2 editions, we had 200 teachers, more than 100 researchers, more than 2,000 students involved. This is a quite large number. 150 schools, 11 regions, and 11 exhibitions, because there is 1 local exhibition per region, and more than more or less 2,000 artworks made by the group of students. During the 3rd edition, we are now approaching to the 2nd year of the 3rd editions, more than 100 schools, to more than 200 teachers, 15 regions, and so also 15 exhibitions. And during the educational part, because of pandemic, we have to switch the educational activities towards an online educational activities. And we also switch from local seminars to national seminars. So students coming from all the regions of Italy can access to a national program of seminars with the participation of 47 researchers and 3 artists. We also had this year a creativity championship that I will describe in a few moments. So these are just an example, 4 pictures of the some of the winners of the first edition, the second edition of the program. So you can see the artistic representation made by students about the universe expansion, the color accelerator. That was an interactive artwork because you use these guns to with colors, the black hole, and l'arte del pendolo, the art of the pendulum. Again, these are pictures about the master at CERN in the first edition. So students have the possibility to interact with researchers at CERN and to explain their art, and to and also there were also seminars and artistic seminars too. As part of our research program inside an outreach program and project, we built a questionnaire to investigate some of peculiar aspects about outreach programs, projects, and also the creativity part of the program, of the project. So we collected 2,000 answers. We see that the 58% of the sample were female, and the 62% came from scientific high schools. We ask students how much they are interested in science and art. What emerges from their answers is that they are a little bit more interested in science with respect to art. And these are the results, the distribution of their answers about how much are they interested in science and how much they are interested in art. So putting together the last two bins, we obtain these results. So students seems to be more interested in science with respect to art. This data comes from the second edition. We also ask them how difficult was working group and how difficult was the creation of the artwork. Since working in group is an important part of the project, and it is also important in science collaboration, we obtain these results, and so students evaluate the difficulty to work in group as actually as easy or very easy, but the creativity part of the project was evaluated as not so easy. Someone also evaluated it as very difficult. So again, how to transform an idea to something that is an artwork is not so easy. To put creativity, to transform science to art, and something like that. Another interesting result about the questionnaire was that to compare high school provenience of students to understand in which way the project can allow people and students to go ahead in a scientific, for example, faculty in the university. So at first, we asked them which university in which university they want to go. This is the distribution of the results. Many of them is dreaming about engineering, but there is also a distribution of interest in medicine, art, and economy, and also physics, which they reached the same result. And this is interesting because comparing the type of school of the participants to the questionnaire and that of the winners, we can state that the students have the same probability to have success in the project regardless the type of high school they come from. So this is important because if you arrive from humanities or from art, you can reach a good result in the project, even if the project is a scientific, strictly scientific project. So this is quite interesting. And this is also confirmed by the third year championship, because in the final podium, the winner of the championship has been Marta Cupaioli, who came from an artistic lyceum. So what is this creativity championship? We organized 4 different matches. In every match, we gave them 4 scientific topics, for example, DNA, black hole, the void, or the sun. And they have to try to figure out this scientific topic in an artistic way. In which kind of art they can use, making picture in the first match, making video in the second, make a collage of pictures, And then the fourth match was about text, so storytelling. There were 3 winners of the competition, the final competition, and 3 winners per match. So this is the final podium, and I show here some picture about taking from the first the first competition, the first match. And so we see how Marta Cupaioli figured out the traces of the invisible, Ruben Martello full of empty, and Caterina De Carlo bubbles of wonder. So in conclusion, students from different high schools are engaged to design and build an artwork based on science. And the idea of using art seems to work well to engage them towards science. Adding the competition element together with working in group and also the possibility to attend a master at CERN or INFN laboratories clearly motivate students to participate to the project, but also to be interested in science. And so thank you for your attention.
Thanks a lot, Matteo, for this nice talk. And so we have time for questions. First from the room. Seems not. From the Zoom. Do you have any questions, curiosities? Okay, if not, okay, no, Francesca.
No, I was just curious, but when you form the groups, the students come from the same high school, so they know each other before, or they are randomly grouped?
Yes, they come from the same school.
Okay.
And so inside the school, they form groups, and then it depends. Sometimes they know each other, sometimes not, because it depends on the teacher. If the teacher takes students in a random way from the school, they maybe cannot know each other.
And the school has to participate to the project, so
yes.
Okay, so a random student from a school that does not participate
No,
to the project
it's quite difficult to create random groups.
I see.
Okay, if there are no more questions, we can go on. So the next speaker, I think it's on. Okay, let's thank the speaker again. Okay, so the next speaker, I think it's on Zoom, which is Enrico Mazzoni. Enrico, are you there?
Yeah, I'm here. Can you hear me?
Okay, it seems. Try to speak.
Can you hear me?
Okay, not so good, but
Maybe.
try again.
Okay, now?
Yeah, perfectly.
Okay.
Can you share your slides?
Yeah, I try to share my desktop. Okay.
And if possible, can you show also your face? Just
okay. Let me go back here. Okay. Stop sharing. Okay.
Thanks a lot.
You're welcome. So let's start to share. Okay. No.
We see a. Okay, now we see full.
Okay.
Okay, thanks a lot. Enrico will talk about from physics to an interdisciplinary project to discuss with students about the big planetary threats. Please go ahead.
Okay, the project is called Warning. And I mean, the idea was to draw the attention of the new generation to the potential events that can threat the mankind. So Fondazione Pisa and INFN launched this initiative called The Warning, which took place between December 2020 and May 2021. The aim of this project was to fostering a culture of being ready instead of what we see now, this culture dominated by an approach of here and now, making people to think in a scientifically sound way. And I mean, the context, the point is that nowadays we think about the coronavirus, but this is not only the only source of risk at planetary level. We know that big part of Earth is vulnerable to dangerous natural hazard. Maybe everyone remember the floods of this summer in Germany, for example. So we have a good amount of people also in Europe that lives in very dangerous area. So there is, I mean, well-known sorts of disaster, let's say earthquakes, volcano, hurricane, and so on. But there is also other sorts of problems that normally we don't think about, let's say asteroids or things that can jeopardize our life. So the project was focused on on a dissemination of this kind of knowledge in an interdisciplinary way. I mean, making young people to think about this dangerousness and to think it at this problem in a scientific way. The project was addressed also to general public, but the main focus was the young people of high school. This project was organized in 5 events, which of this is devoted to improve the scientific knowledge about these natural hazards and encouraging a defensive behavior, so understand the problems and understand how defend ourselves from this problem, and also to stress the complexity of this kind of events and education to the complexity in obviously in an interdisciplinary approach, using knowledge across various areas. Why physics? I mean, this project was started by INFN, which is an institute of high energy, but according to us, physics is the fil rouge that accompanying the participant in this journey, making across many fields of science. I mean, physics give us a tool and a method to
Enrico, something happened. Okay, can you try your microphone, because
you don't hear me?
Not so well now.
Let's see. I don't now.
Similar. Try again.
I don't know what's happened. Maybe it's a network problem. I can try to speak louder.
Yeah.
Okay.
Thanks a lot.
Otherwise, I have to stop the share and so on.
No. Okay. Now it's better.
Okay.
Thanks a lot.
I mean, what we saw is that in this kind of discussion, the method is not so different from what we do in high energy physics. And a common aspect of these events that we speak about is the complexity. I mean, we have unpredictable developments of this kind, these events. Is difficult to quantify the risk, for example, and the interconnection between all this stuff. So at the end, the real world is made of complex things, and you cannot avoid complexity. But the scientific method is primal to develop, to deal with this complexity, and this is what we want to transfer to young people. And it's funny because we introduce the scientific method to these young guys in the cradle of a scientific method. Pisa is the burning place of Galileo Galilei. Here you have the picture of birthhouse of Galileo. Oh, the partners of this project are three: the INFN. One of the mission of the INFN is the transfer of the knowledge, the so-called terza missione. Fondazione di Pisa, which is a banking foundation that that is active in the territory for cultural heritage, scientific research, philanthropy, and so on, and Palazzo Blu, which is a center for temporary exhibition, and it is managed by Fondazione Pisa. The organization of this event, due to the pandemic, we cannot do it in presence, of course, so it took place virtually. And more than 3,000 students participate to this initiative, coming from 25 high schools. Before the seminary, we give to the teacher explanatory material. We made some presentation to let the teacher to prepare the students to the debates, and we give to the students the opportunity to prepare the question and send this question to the research that will give the seminary. We got a lot of questions, 600 on average for each seminary. So we need to do a lot of work for classify this question. For each seminary, we had two speakers, scientist or researcher, with complementary expertise, so they can give a wide view of the problem in the seminary. And big part of the seminary, let's say half of the time, is dedicated to the answer to the question received by the students. I mean, every seminary lasted 2-3 hours, so 1 hour and a half at least was dedicated to the answering of the question. Of course, we set up a website to disseminate as much possible the activity of these events to collect also the interest of normal people, not only school. On the on the site are available individual section for each of the 5 topics of this event, and there are a special section for information for school and a form to submit question to the speakers and so on. Obviously it was streaming events, so from the website of Warning to the Palazzo Blu channel, YouTube and Facebook. The seminar was also recorded, and so a school can access the seminar offline to make work on the material of the seminar. On average, every event was followed online by 700 participants, but offline there was a lot of visualization, between 3,000 to 9,000 of visualization. So it was followed by a lot of people. So the 5 events, here you have the subject of the 5 events: alarm from the atmosphere, measure biological hazard, the restless earth, wonders and hidden dangers from the space, and climate and the ocean sinister changes. The first one was dedicated to the climate change. We start from the physics of the atmosphere, and then we cover economic consequence of the climate change. I mean, one of the speakers was an expert of physics atmosphere. The other one was an expert of economics, and so we cover all the aspects of the climate change due to the increasing of the warming of the planets and so on. And this start a good debate also thanks to the question arised from the students. The second one was dedicated to the biological hazard. I mean, there is not only the coronavirus. I mean, the beginning of the seminar was dedicated to SARS-CoV-2 pandemic, but one of the speakers was an expert of history of pandemics, so we can stress and we can see how the pandemics evolves through the years, through the centuries, and how the society and the way in which the society fight against the pandemics change during the time. And what we discover is that nowadays is not so different the way that we fight against the pandemic as the 1 century ago. The third summary was dedicated to the endogenous problems. What happens with the volcans, earthquake, and so on. Again, we start from geophysics. So we start the seminary start with the understanding of the physics of this event, but again we go on another side, and Viviana Castelli told us how researchers go around the territory to discover the history of earthquake or volcans and so on. And again, there is this interdisciplinary approach from physics to physical geography, history, social science, and so on. The first event was dedicated to the problem that came from the space. So we start speaking about near Earth object, which we are very efficient to spotting and to follow this kind of object, but we don't have tested the solution for comets or asteroids that may collide with the Earth. And again, the speakers tell to the students about the scientific aspect, how to determinize how to spot this object, to follow this object in the space and so on, but also what we need to prepare ourselves to the possibility of impact and so on, and the necessity of planetary collaboration to in some way have countermeasure to this kind of events. The last one was dedicated to the oceans, to the change in the ocean, and I mean, not only the increase of the sea levels, but also all the human activities that change the chemistry and the oceanic circulation and so on, and how this change impact the climate of the Earth. Is kind of loop. The last seminar is, in some sense, connect to the first one and give us an overview of how complex are the phenomena that we are facing in these years. The student, after this path, produce a final script about what they see, and it was very, very interesting what came from these scripts, because we saw a very good and deep elaboration from the student about what they hear from the speakers. We also produce a questionnaire to the teachers to understand how positive was the initiative, and the results are very good and encouraging. And in conclusion, what we can see is that I mean, the scientific method and this the multidisciplinary approach is the best tool to interact, to face this complex problem. Warning aimed to raise young people awareness on the planetary hazards, and what we see from the outcome of the students is that I mean, we get some good results in this sense, and we are looking forward to a second edition that we are working in this day. Let me acknowledge also the other guys from Palazzo Blu and Fondazione Fisa, which give us a good help to produce this. Thank you very much.
Thanks a lot. Thanks a lot for advertising us on this very nice project. I think that natural hazards it's a topic, very timing topic in this period.
Yeah.
So are there any questions from the room? Yes, there is one.
So you said that half of the seminars, about 1 hour and a half, were dedicated to questions from the students. And usually, at least in my experience, especially in online meetings, it's difficult to stimulate students to ask questions. So how did you achieve 1 hour and a half of questions from students?
Actually, the question was not online. We achieved these results giving the opportunity to students to send us the question well before the seminary through the website. And we collect all this question, make some condensation because I mean we saw that the same things was asked, let's say, by 5 different schools and so on, and we propose this question to the speakers, saying which was the school or student that presented that question. So it's not really a live question. But in this way, students have much more time to think about question and to prepare their question.
Okay, thanks a lot. Are there more questions for the speaker from Zoom? I don't see raised hands. So we can thank the speaker again. And we move to the next speaker, which is Arndt Meyer. Okay, we see you.
Yes, I hope you can also hear me.
Yeah.
Excellent. So there's only one piece missing. That's the
Your
presentation. Okay, which should be appearing now.
Not in display mode, I think. It seems. Okay, now.
Now it's full screen?
Okay. Yeah, thanks.
Oh, excellent. So yeah, this is now like a 180-degree switch of topics. I hope it's still a bit of general interest. So I'm going to present the results of analysis of conference data, speaker data that we performed in CMS over the last couple of years. So let me first motivate that a little bit. So like all the big experiments and many of the smaller ones, CMS has a standing committee to organize representation of CMS. So for CMS, that's a fairly large body. It's like a dozen appointed members and then the usual ex officio members such as spokespeople, etc. So the goals are, as most of the time, I guess, to ensure equitable distribution of talks to all CMS members, and at the same time also ensure, promote, maintain a higher standard of the presentations themselves. So often there are conflicts, of course. The most natural conflict is that on the one hand, there's a goal to have the best possible representation of CMS, so always send the naturally best speakers, whatever that means. But on the other hand, there are the needs of the individuals, promoting their career, promoting inexperienced collaborators, etc. So do we have a diverse pool of speakers is one of the questions then. So we always consider that as part of the speaker selection. But of course, if you have a small conference with a handful of speakers, you can only do so much. You cannot balance a collaboration of 2,000 people to be represented well in 10 talks or something like that. And it's also constrained by the pool of nominations that we have at hand to choose speakers from. So it's also important then to monitor how we are doing after the fact. And we have always been doing that for the last, I don't know, 20 years or so on a yearly basis. Always making sure that regionally all countries and regions are represented well. So that has been there from the beginning, I guess, as a natural interest of the stakeholders, funding agencies, and so on. But then in the last few years, we extended that more and more. And for example, for the last 5 years, we always monitored things as the career level, seniority, gender, and things like that. So by now we have more than 16,000 presentations in more than 13 years in our database. So it's a wealth of data, and we collected many unique experiences. So it has been brought up again and again that it might be of interest to show this also outside of CMS. And that's what I'm doing here. Another aspect why it's interesting to monitor also after the fact is the way speakers are selected. So there's a long list of criteria, and I cover them up here because it's not the goal of this talk to discuss all these criteria. But I want to point out that it's not just a simple, straight, linear set that you can have. So this is now the #1 criterion, and this is why the speaker is selected. It's most of the time case-by-case decisions, which one by one always make sense. Factors are very individual, but one has to see after making many such decisions, do we asymptotically reach sort of the distribution we want to see in the end. So to make this monitoring and to make the decisions in the first place, we need complete and accurate information. So we have a database for that since well, 13 years approximately. That's a homegrown product called CINCO, CMS Information on Conferences, which has not only the talk history, but it also has what we call personal profiles of all CMS members. And it serves also as a database for all the recommendations and nominations for talks, and has a lot of automatically filled data that are useful to do our job. So like I said, nomination text. Then we also, of course, rely on information from conveners, coordinators, and a lot of inside knowledge. So now then, 1.5 years ago, of course, everything changed, and also our data changed. And so I want to mention briefly how we perceived this from the work of the conference committee. So of course, things developed rapidly in March 2020. So for us, the first conference that was just canceled on extremely short notice when the crisis developed in northern Italy was La Tuile 2020 in March. And then for a couple of months, essentially everything was canceled. For us, the only events that took place by video were CERN seminars, essentially, where we got a few additional slots to compensate for all the cancellations. So the first major conference to go fully virtual was for us LHCP 2020. It was an heroic effort, and it was very unclear at that time how that would work out. Since then, we had many successful examples, the big ones like ICHEP and DPSHEP. We discussed internally early on already whether we want to make changes in the way we promote speakers. For example, would we weight remote participation differently from in-person participation? At that time, nobody expected that it would last long, of course, and we decided, which I think is still the right thing to do, against global changes, mostly on the basis that everyone is similarly affected, which is not necessarily true. So then sometime fall 2020, the first hybrid conferences came up. It was very, very few in last year. It's becoming much more common these days, as we see right now. But we also still have many big conferences and workshops that are fully online, like the Moyon ones, LACP, and even EPS this year. And we also still see a couple of events, especially those that focus on in-person participation, to be postponed. For example, a Lepton Photon Symposium to early next year. So starting with the data. So this is like a global overview. How many presentations are given on behalf of CMS as a function of the year? So the black line is the total number of presentations. It averages in typically pre-COVID years at around 1,400 per year. That includes not only international, but also national meetings, posters, workshops, essentially everything that is in the scope of the conference committee. One can see there's a small dip there when we had the long shutdown 1, the transition between the LHC run 1 and run 2. And then you see essentially a 50% drop for the year 2020. Similarly, it looks for only looking at talks at international conferences and workshops, which is a more classical area of work of the conference committee. And then a little bit less affected in red here are talks at the major international conferences for CMS, which are explicitly listed here. So it's going down by about 50% in 2020. Looking at a few more categories on the next page. So the green here up here was the same green as before, the international talks. Presentations at national meetings go down, posters and instrumentation conferences, all similarly affected. I should say here, I did not put the data here for 2021, but one can say that currently we are up at a level of presentations which is close to pre-COVID times, as far as one can say that already now. So we tried to re-accommodate speakers from canceled talks as much as we could. Of course, we needed the information for that. We also got information early on that people actually welcomed the online events. Many people attended conferences in places they could otherwise never do because of visa reasons, cost reasons, number of reasons. One can also see that usually the online conferences have multiple times the number of participants. Often they are free anyway. For example, ICHEP 2020 already had more than 3,000 participants. But of course, we also all have seen that the number of attendance in the meetings themselves sometimes is low to very low. So there is the interactive component often missing. So, and then we, of course, also all saw that new forms quickly developed, breakout rooms, virtual coffee breaks, virtual poster sessions using a number of social media platforms have become the new normal, as also successfully done here at these conferences. And much of this will, of course, stay for the future, will be beneficial for the future. And while it's no replacement for the real conferences, I think it will definitely help to inject some new life into some of the classic old-fashioned form of conferences. So coming more to our data again. So like I said, geographical diversity has always been monitored. And I show here one example that is for the major conferences in the year 2020. So that's a small number of talks in the end. And the way this is listed is here, it's normalized to the number of physicists and students in the respective countries. And the largest countries in terms of number of presentations are at the bottom. So if one looks here at the lowest 10 countries or so, this is fairly equally distributed. So even though the number of talks is small, this looks still pretty good. Of course, there are some outliers, but they are statistically not significant at all. So one can do the same plot for the last 13 years. This is then a few thousand talks. And again, focusing on the lowest dozen or so countries, this looks fairly reasonably equally distributed. There are some interesting cases where the number of presentations is somewhat low. For example, one can see that for Russia, China, and India are somewhat below average. And of course, this could be interpreted as problems to travel in some cases, again, visa and cost. Okay. So since 2016, we do a more detailed analysis. So what I show here is based on a snapshot taken at the end of last year. And I show data here for the 2,100 CMS authors. So this is, for example, the plot of the number of presentations, any presentation, given over the last 3 years by CMS authors. So on average, this is 1.5 presentations approximately. This number is a bit lower than in previous years because of the COVID crisis. One can also see that there's a large number of people who have not given a presentation in this time period. And one can also see that there are outliers going to many presentations in 3 years. And I want to highlight here that CMS does not have a fixed quota on talks given by its members. Now, this is essentially all presentations, so it does not take into account that some talks are much more worthy, so to say, than others. And so what we developed in CMS is what we call a rank. And I don't want to explain here how this is calculated, but what this takes into account is how important the talk is, how important the conference is, and also there's a time decay factor. The talks that are longer ago count less. So the more negative the rank becomes, the more talks a person has given. And so this distribution is also shown here. Of course, one cannot make much out of the absolute numbers here, but I just wanted to mention this, that we do this. And the details are in fact in the backup. So looking for biases in our assignment of talks. One aspect that is of interest is whether we have gender bias in how we designate speakers. What is shown here is again the number of presentations in the last 3 years, in blue for male and red for female CMS authors. So the average number of presentations given is comparable. In fact, it's slightly larger for females. So overall, it looks fairly unremarkable, also including the shape, and there's no sign of overall biases. Now one can wonder, is this strongly affected by the COVID crisis? And so I show also here the plot from the year before, which then essentially are presentations given in 2017 to 2019, and the conclusion remains the same. Again, one can show this using the so-called rank. I only show the plots here and highlight here the means, which are all comparable in 2020, 2019. So the conclusion remains the same also when including the importance of the talks. So you can also drill into other aspects. So one that we look at is the position and seniority in CMS. And what we observe here is, and this is along the lines what we also want to achieve, is that we prefer in talk assignments postdocs and people in non-permanent positions over people in permanent position and PhD students, which usually have few talks because in their first year, for example, they usually don't give international talks. So I showed like one-dimensional projection so far. Of course, one may ask, what does it look like if we look in more dimensions like gender and seniority at the same time? And I show one example here that is the distribution of talks given by female and male authors who are at the same time postdocs and non-tenured CMS members. So again, the plot here on the left is from pre-corona times, and one can see just looking at the means that again, the numbers are comparable. There's no obvious bias. I should point out here that the position data, like who is a postdoc, is somewhat not accurate because this relies on personal input and people willing to share this data with the conference committee. So one can also look at the geographical distribution again of this rank that I introduced earlier. And each of these points corresponds to one country or CERN, which is counted separately. And just looking at the distribution and the spread, one can see that on average, this is fairly well distributed, both for male authors on the left and for female authors on the right. So, and just flashing that internally, we can also look at more information that are useful for how our work is considered by the collaboration at large. For example, I mentioned that we rely on nominations, and one of the things that it's always mentioned as positive in the way it's done in CMS is that the nomination process leads to the fact that most people get the talks they really want to. So they are not just assigned to any upcoming conference, but they really nominate for specific conferences. And we can see how often this nomination process is successful. And we see that even for big conferences, this has about a 50% success rate. So most people get the talks they want. We can also look at long-term developments. For example, here, the number of presentations as a function of the years that a person is in CMS. On the left for male and on the right for female authors. Here we see, for example, that in general, male CMS authors tend to be a bit longer already on CMS. So there's a bit less seniority among the female memberships and a few more talks correspondingly, because mostly younger people tend to give more talks. We also see that while this is nicely correlated for many people, that there's a fraction of like a quarter of the collaboration that is not giving talks at international conferences, many for many years. And this is, of course, also something that we are interested in. So let me conclude quickly. So we have procedure in place to distribute talks fairly. Our process relies on nominations. We think it's very important to monitor all these aspects to ensure diversity in the long run. Since CMS is a large experiment, we thought it's maybe of interest to make this data public. Last year, like everybody else, we had to deal with and try to cope with many hardships, and the number of presentations went down to about 50%. But we saw many positive developments too, with new forms of information exchange and new opportunities for our members. Thank you.
Thanks a lot. Thanks for this very nice talk. So
I cannot really hear you. Is your microphone on?
yes. So, someone can hear me from the Zoom? Seems not.
It's very, very faint.
I don't know, maybe there is a problem. Check. Okay, I can change the microphone. Now it's better.
I think it's better.
Okay. So there is a question from the audience.
Hi, thanks a lot for the contribution. Since I'm also part of the SCP collaboration, we did a study at some point during the pandemic, and we realized that especially postdocs and people with, of course, non-permanent position were affected much more for many reasons, or lack of productivity. They fear a lot the fact that they have to search for a job without being able to travel to conferences, no potential like So I was wondering if you put in place anything special in order to maybe maximize the outcome and visibility of young people in CMS with the number.
Yeah, so the sound was still very bad, but I think I got the thrust of your question about essentially young people having problem networking for finding jobs and developing their career. Yeah, we of course we see the same problem, and we try to always give priority to people for conferences, but of course the conferences are not so useful for networking anymore. What we also have in CMS since last year is what we call a job matching event, where we bring together senior people and senior people advertising jobs and students and postdocs looking for the next position. So this is developed in CMS, and one can only hope that this compensates the problem. But I have to say that personally, I know people who are really affected by this in developing their career. So it's a real problem.
Are there more questions? Not everyone, actually. In your slide 6, I think, if I remember correctly. So it seems that the pandemic has affected more the minor conferences. Do you have an explanation? Or
Yeah, this is fairly easy in this case. So the number of major international conferences is a fairly small set of conferences. The list here given here, of course, it develops over years and we just decide case by case. But for 2020, the ICHEP took place and the LHCP took place. So those are very large conferences with a lot of talks, and so they kind of managed to pull this up. So what was canceled was the Moyo conference, UCD and Electro Week, and SUSI was also canceled. But the really big ones like LHCP and ICHEP, they took place, and that's why the number is still fairly high.
yeah, it does make sense, yeah. Thanks a lot. Okay, so if there are no more questions from the audience or from Zoom, let's thank the speaker again. And the next talk will be Simone Donati, which will tell us about involving the new generation in Fermilab future endeavors.
Yeah, can you hear me and see me?
Yes, very well.
Yeah, so I'm going to, can you see my screen in full screen?
Yes.
Okay, so
go ahead.
So hello everybody, I am Simone Donati from the University of Pisa, and another change of subject with respect to the previous talk. And my talk today is a report on the initiatives that the Italian research groups working at Fermilab in the United States take to involve the new generations in the lab's future endeavors. Okay, so this is my outline. First, I will say a few words about Fermilab, that is a particle physics laboratory in the United States, and about the history of the collaboration between Italy and Fermilab. I will then describe the most important initiative that we take to involve the new generations in the lab's endeavors, that is the summer students program, that is for university students. So now we are talking about the university students. I will go through the students' recruitment process, the selection of the supervisors and training programs, the involved costs and the sponsorships. I will also show some statistics relative to the almost 40 years of the program's existence, except for the last couple of years. Sadly, we had to cancel the program last year, and we replaced it with a 3-day workshop at the INFNN National Laboratories of Frascati this summer. I will also talk about the internships at the space science laboratories and universities in the United States that we have been organizing for a few years by taking the Fermilab program as a model. My conclusions will then follow.
So Fermilab. Well, there is no need to say that Fermilab is the most important particle physics laboratory in the United States. It was founded in the 1967 as the National Accelerator Laboratory and then renamed to honor Enrico Fermi in 1974. Fermilab is now exploring the high-intensity frontier with the neutrino program and the muon campus experiments. The lab is also at the frontier of accelerator science, detector technologies, and computing technologies, all the technologies that are typically involved in the particle physics experiments. So a couple of words about the lab's organization. That is important to understand how we organize our program. Fermilab is basically structured in a number of divisions, which include the particle physics and the neutrino division, which develop the lab's experiments. The accelerator division, which develops the new accelerator technologies and provides particle beams to the lab's experiments. The technical division, which provides all the necessary technological support for the experiments of the laboratory. And the scientific computing division, which develops the complex infrastructures that are necessary for handling the large data samples that are typically produced by particle physics experiments. Today, Fermilab has about 1,800 employees and has thousands of visitors from the entire world. Well, actually, it had thousands of visitors until 1 year ago. Now visitors are pretty much less, for obvious reasons. So in general, the lab's atmosphere is very vital, and this is the ideal environment to involve young students for trainings and young researchers for the initial steps of their careers. So what about Italy? So the collaboration between Italy and Fermilab was started in many years ago, in 1984 approximately. And for many years, it was mostly dedicated to one single experiment, mainly to the CDX experiment at the Tevatron. At that time, the moment of maximum Italian participation in CDF was probably in the first decade of this century, when a total of about 100 Italian scientists from many INFN departments and Italian universities were involved in CDF Run 2. That was a large fraction of the entire CDF collaboration, which counted the total at that time, a total of about 600 researchers. Well, the departments and universities from which these researchers came from were a significant representation of the Italian most important universities and INFN departments. Bologna, Frascati, that has a national laboratory, Padova, Pavia, Pisa, Roma, the University of Roma La Sapienza, Siena, Trento, Trieste, Udine. No need to say that our students were the cornerstone of this fruitful collaboration. We counted about 100 master theses and about 35 PhD theses. Many of these students were recruited with the most important of our initiatives, that is the summer student program, that is the main topic of this talk. And what about today? Well, today, Italy is again deeply involved in the new lab's endeavors, that is the muon campus experiments G-2 and mu2e, and the neutrino experiments Icarus for the short baseline neutrino program and the future Dune. What about the numbers? The numbers are even larger than at the time of the Tevatron experiments. In fact, we can count that a total of about 140 Italian scientists, engineers, and technical staff from a number of INFN departments and universities are now involved. There are some new universities and INFM departments that 20 years ago were not working on the Tevatron. For example, Napoli, Milano, the Gran Sasso, Genova, Lecce, and Ferrara. So let's now talk about the summer students program. Although we receive most applications from students enrolled at Italian universities, a fraction of them are from students of European universities. On the map of Italy, I just put crosses from all the universities from which we have received applications for the program. You can see that almost all universities in Italy are involved. Of course, we take Italian students and students from European universities with the same level of consideration. The program is open to master students in physics, applied physics, engineering, material science, and computer science. Student selection is highly competitive and based on the CV, on recommendation letters, and an interview that has the goal to ascertain the students' interests, personal motivations, technical skills, and also proficiency in English. That, of course, is essential. So, the students that are selected spend 9 weeks at Fermilab, and that is usually August and September. Physics students may be involved in the analysis of experimental data, design and setup of particle detectors, design and test of particle accelerator components. Engineering students are usually involved in more technical stuff, for example, design and detector and accelerator specific components, test of superconducting materials and magnets, design of high precision mechanics components, or design of analog and digital electronics components, or advanced computing infrastructures development for data storage and analysis. But this is not only an internship program, it is also a university course. In fact, since 2015, the University of Pisa has acknowledged 6 ECTS credits for this internship. What are credits for someone, or ECTS for someone who is not European and is listening to this talk? Well, this is the currency that is acknowledged to the students for the courses they attend at university. For example, in Italy, a standard 1-semester course corresponds to 9 credits, and this summer program is 6 credits. Okay? For example, the total number of credits for 1 academic year for a student at the university is 60. So this is, in the end, an internship program, but also a standard university course with the same value as all the other courses. Just as an example, the plots that I reported here show some statistics of the training programs of the last 2 years of the program existence, that is 2018-2019. In 2018, we had 10 physics students and 15 engineering students, mostly involved in the development of Fermilab experiments and also contributing to the several divisions, accelerator, scientific computing, and technical division, with an almost even distribution among the divisions. The following year, 2019, we had similar numbers with 13 physics students, 15 engineering students, that was a total 28. Of course, we have no numbers for 2020 since the program was cancelled for obvious reasons. And please notice that there is also one entry in the histogram relative to space science laboratories for free students. This is something slightly different. We will talk about it in one of the final slides of the talk. So, we may wonder who sponsors the program. Well, the cost for the students is $0. In the end, they spend nothing, okay? Their balance is 0 or positive. But the cost of one student living for and working for 9 weeks at Fermilab is not at zero, is approximately $9,000. There are some sponsors, and this is the list, in decreasing order of the provided financial support. First of all, there is the US Department of Energy, the Italian National Institute of Nuclear Physics, the Sant'Anna School of Advanced Studies in Pisa, the Italian Space Agency for the internship at US Space Science Laboratories, and the University of Pisa. Let's see in more detail what Fermilab provides and what it does not provide to the students. Okay, so Fermilab provides a weekly salary of about $450, free housing in the dorms, and a shared rental car for local transportations. The students have to buy their own round-trip ticket from Italy to Chicago, and the health insurance, which is mandatory to get the J1 visa, which is necessary to be hired as interns at Fermilab. And in fact, Fermilab acts as a sponsor for that J1 visa. And of course, the employment office provides all the necessary assistance for the involved bureaucracy, which is not negligible. So how do the students end up with the zero costs if they have to anticipate some money for the ticket? Well, the salary and the cost of life in the US is such that they will, if they lead a simple life, they end up saving the money from their salary that they have anticipated. So in the end, when they come back, their balance is either zero or positive if they saved something. So let's see the important dates of the program. Between January and March, typically we receive the students' application. At the same time, we receive the training programs from the candidate supervisors. We complete the students' selection and we assign them to the supervisors in May. The students fly to Fermilab on the last weekend of July, and the next Monday, they are hired as Fermilab interns for 9 weeks. They take their trainings and orientation courses. And after 4 weeks, we typically make a mid-term review. All the students report on the progress of their work with the 20-slide presentation. In the last week of Fermilab, we make a final review. The students show their achievements in, again, a 20-slide presentation and write a 20-page report for our archives. Typically in October, a committee of the University of Pisa reviews the students' work and in case of successful completion of the examination, acknowledges 6 ECTS to the successful students. So some statistics. To me, the statistics of the past 35 years is impressive. Since 1994, 550 students participated in the program. The plot shows the number of students per year with different colors. The blue point dots are engineering students. The light green dots are physics students. Red is the total. Well, we started with the 3 years students in 1984. Well, they started, I was not there at that time. And we added 20 in 2019, the last time we ran the program. In the first few years, we mostly accepted the physics students to work on CDF within the Italian groups. And it took a few years to have our physics students known also in the other experiments, and the engineering students known in the technical, accelerator, and computing divisions. Well, most Italian universities have been involved, but Pisa, Rome, and Padova have dominated in some sense the scene. This is due to very simple facts, to the fact that these universities and INFN departments had a long-standing participation in CDF. So they had more time to accumulate students. Pisa today is also deeply involved in G-2 and mu2E. And this keeps Pisa numbers pretty high also today. We have also had a bunch of students from European universities, for example, Munich, Heidelberg, and so on. Well, about the training programs, we only kept a detailed record of them for the last 12 years. This is the distribution among the several Fermilab divisions, and the students for these 12 years correspond to about 270 students. That is 50% of the total. And as you can see, there is an approximate balance between particle physics division and all the other divisions. So with the financial support of the Italian Space Agency, the Italian National Institute of Astrophysics, and also the Italian National Institute of Nuclear Physics, 28 summer students have had the opportunity of an internship in laboratories and universities involved in space science. We basically reproduced the model of the summer students program at Fermilab. And you can see here in the map the distribution of the destinations in the United States where the students could do their internship. Caltech, Stanford, Columbia University, Princeton, Harvard, and so on. In this case, we simply selected the students, and the students chose their destination by themselves. We assisted with the logistics on the American soil. Okay, so as I said, we canceled the 2020 and the 2021 programs, but to keep the connection between the Italian students and Fermilab alive, this year we organized a 3-day workshop at the INFN National Laboratories of Frascati. We selected 20 students. They attended the seminars on Fermilab experiments and visited the Frascati labs infrastructures. This is the timetable of the 3 days. Well, just a few details. We had interesting talks from Flavio Bossi and Ezio Previtali, that are the directors of Frascati Labs and Gran Sasso Laboratories. They gave an interview of the lab's initiatives and future prospects, and also a talk from Fermilab director Nigel Lockyer. We can say that the main topics of the first of the days of the workshop were Fermilab neutrino program and the Muon campus experiments, G-2 and Mu2E. My impression was that the students enjoyed the talks, but they enjoyed even more, as could be easily expected, the visits to the labs infrastructures, for example, Daphne, Chloe, and the other infrastructure that were accessible those days. Not everything that we wanted to visit could be made accessible. So also on day 3, we had interesting talk given by young colleagues, PhD students and postdocs, which attracted the students' attention. It was even, of course, easier for the students to talk to younger people. To conclude, well, a 9-week internship at Fermilab would have been better, but of course was not possible yet. And we did our best to keep the connection between Fermilab, future endeavors, and the students alive. So my conclusions, we have this summer students program at Fermilab that is a multidisciplinary 9-week internship for physics and engineering students, and hands-on training on Fermilab research activities. The balance of the history is positive. We had approximately 550 students since 1984. Many of them extended their collaboration with Fermilab with a master thesis or a PhD thesis, and started their careers at Fermilab. Then their careers developed anywhere in the world. So we certainly hope to be able to organize the program at Fermilab live again next year and for many years to come. Thank you. This is all from me.
Thanks for this very nice talk on this interesting program. And let's see if we have, okay, we have a question from the room.
Hello, I would like to ask you if the conversion of this summer program into credits accepted by the the coming university is in a way automatic, or is something that has to be discussed with some committee in a university? It's easy to achieve or not?
This is, of course, a question that I would expect from a person from a university like you that is expert of these details. In Pisa, it is a course. The University of Pisa has a number of summer schools. They are university courses, okay? So like General Physics 1. So the students inserts this course in his piano di studi, plan of study, and if one day, when they discuss, they defend their master thesis and the committee has the list of exams, that this is an exam like all the other ones. What the Italian university treat this course of the University of Pisa is very university dependent. Some accept it as it is, some have to understand what it is. In some cases, there is technical complications. For example, I remember the University of Naples, Federico II, has the problem for the physics students that they all have exams of 9 credits. So 6 credits does not match. No. So it's complicated. For example, with the Politecnico di Milano, a few years ago, we wrote a convention, a dual agreement between the two universities, such that a student of Politecnico di Milano is allowed to insert 2 exams of the University of Pisa and vice versa. In principle, this should be doable because all universities have Erasmus programs. So if a student wants to go to Barcelona in Erasmus, there is a learning agreement which takes care of the problem. So did I answer your question?
Yes, thank you. Thank you very much. I have another short question. So you told me that the students plan to insert this experience in their study planning, right? But it depends on the application is being accepted by the Fermilab, right? So if the application doesn't end well, they have time to change.
No, the application. What do you mean does not end well? If the
it's not accepted by Fermilab, or
of course, this is available an opportunity only for students who are accepted in the program. This is a closed number summer school program. Only students who are accepted in the program fly to Fermilab, are hired by the lab, and then have this university framework that is called summer school. By definition, students who are not selected do not have an alternative path to these 6 credits because they do not participate in the program.
Okay. So are there more questions from Zoom online? I don't see any raised hand. So, so I have a curiosity. Did you provide at the end of the program to the students a questionnaire to see if the students are happy, or maybe to suggest
yes,
to improve the program?
As you can see, this is a complex program, no? And the participation of the researchers, Fermilab researchers and Italian researchers that take care of the students in the American soil is heavy. So each student has a supervisor, Fermilab supervisor, and typically an Italian co-supervisor. The reason is simple, because the goal of the program is to involve students in our experiments. So satisfaction or dissatisfaction is a fundamental parameter. What I usually do in a private way, I talk with each student and ask him or her, were there any problems? Are you happy? And we do this also during the 9 weeks. So if, because the job of the supervisor is a heavy job, because it's like being the advisor of a short master thesis. Yeah. No? So if the supervisor, for some reason, has to go away because he's going to a conference, he's on vacation, we need to know promptly and take action. And this happens every year, that at least 1 or 2 students are in a difficult situation. So the answer is yes. We monitor online, and offline we ask privately to the student his feedback, and we take it into consideration. If a supervisor did not perform as expected, we take it into account for next year.
Very nice. Okay, so let's thank the speaker again. And we move to the last talk by Christina. Christina, are you there?
Can you hear me?
Yeah, very well.
Okay,
we cannot see you.
Now
okay,
I turn the video on.
Yeah, yeah. Okay.
Okay.
Can you share
yes.
your slide? Christina is going to talk about new particle search with the Reinforced Citizen Science Project. Now we see.
Now, do you see it full?
Yeah, but not full screen. Not.
Strange, because okay. Now you should see.
Yeah. Okay.
Okay.
Thank you.
So I'm going to talk about the search for new long-lived particles at CERN, and this is done in the framework of the Reinforce EU project. And I will also say a few things about the project itself. So just before the outbreak of the COVID, at the end of 2019, we started this project, which is a Schwab's citizen science project called Reinforce, Research Infrastructures for Citizens in Europe. It has 4 working packages for discoveries, which I will briefly describe, and is coordinated by EGO in Pisa. The website you see in blue. Reinforce is built on the Universe platform, which is the largest platform for online citizen science. Citizens can build and run their own project, citizens from Europe and beyond. And it has about 2 million users. Examples of projects which may be familiar to you are the Higgs Hunters, Gravity Spy, Muon Hunters. Now I will talk about a bit about the other discovery working packages, and at the end I will come to the one about CERN. So the first one is the gravitational wave noise hunting. The leader is EGO and the University of Pisa. The citizens use data from Virgo and LIGO, and their purpose is to identify glitches, which means noise sources. Here you see an example of a gravitational wave detector, which you know very well. And the citizens, they tried to categorize the different type of noise, the glitches, based on spectrographs, and classify them. And at the same time, discuss with the Virgo LIGO experts and help them in efficient noise hunting tools and in their development. The project is already on the Universe platform, You see up on yellow the address, and as you see below here, there are different levels that the citizens, stages, let's say, that the citizens can use, and each stage is with increasing difficulty, so they can choose the one they want. The second discovery package is called Deep Sea Hunters. The leader is CNRS, and the data used are for kilometer cube net, which of course, as you know, tries to detect neutrinos. But the citizens, they don't do that. They look at noise sources from bioluminescence and bioacoustics. More precisely, in the context of kilometer cube net currently being developed in the Mediterranean Sea, they have two working package, bioluminescence, and what they do is peak counting and looking for weird signals, and bioacoustics, meaning the noise cetacean clicks picked up by the hydrophones, which they classify. They could be from sperm whales, from pilot thin whales, and noise in general. The next one, no, sorry. This is the project on the deep sea hunters on the Universe platform. And you can see the different paths, the peak counting, bioluminescence, and the bioacoustics. The next one is called cosmic muon images. So this one uses simpler muon detectors to do muonography, volcanology, geoscience, and archaeological surveys. One was done a few years ago in the north of Greece for the Apollonian tumulus. The idea is to use absorption of cosmic rays or transmission for large objects or transmission from smaller objects, and look at, try to investigate the inner density of massive objects. This is their platform. They have here, they have a track drawer where they can draw tracks, and they have a machine learning to distinguish signal from noise, and a lot of applications. Here you see an example, a cosmic ray shower, which goes through something opaque and detected by a muon telescope. Of course, the energy of the muon has to be above a certain threshold, and there are also backgrounds, as you see in this image here. Now I come to our working package, which is called Search for New Particles at CERN or LHC. The way we do it, we have the citizens focus on virtual inspection of events and train them this way to look for different kinds of particles and maybe make discoveries of new physics. We decided to build this discovery package to engage citizens to research performed at CERN, include citizens of all ages without prior computer knowledge, and motivate them since they are looking for discoveries in frontier high energy research. What we give to the citizens are data collected by proton-proton collisions at the CERN LHC and registered by the Atlas detector. So the discovery path is like that. The citizen science, they virtually inspect collision events, and they look for displaced vertices, namely the origins of two or more tracks, which vertex is located further away from the main vertex, which is the proton-proton collision point. The purpose is twofold: to enhance our understanding in the Higgs decay to two photons, one of which photon or both materialize to an electron-positron pair, or to look for some supersymmetric particles predicted by theories like RPV, which decay, they live long enough to decay further away, and the decay we're looking at is a decay to a muon and a jet of particles. And this, if discovered, it can give answers to open questions. We had divided the work plan in 3 stages. The first 2 stages use simulated data. The first stage is just to train the citizens to locate displaced vertices. The second stage is to train the citizens identify different kind of particles from the traces they leave in the Atlas detector. And more precisely, we are interested in muon, electrons, and photons and converted photons. The third stage, which is divided into 2, is the Higgs to gamma-gamma study and the long-lived particle hunting / discovery. The stages 1 and 2, they provide us the main results because we compare the citizen results to our custom-made algorithms, since they are simulate the data and we know the answer already. And the third stage gives the citizens the opportunity to apply what they learned on samples of real data. To do this, we had to do several steps for many months to develop a dedicated data selection filtering procedure in order to transform the Atlas data in a form which is suitable for visual analysis. We had to get special permission from the Atlas collaboration and management to use the data, because we needed some additional information additional to the open data, which are open to everybody. We developed visualization tools like the one you see on the left, which is a blown up of the Atlas inner detector, or the one on the right, which is interactive, is the Hypatia analysis tool. And of course, we developed automated algorithms to monitor and measure the citizen science results on the simulated data sets. This is our universe platform. Right now is under review. And there we had the different stages that you see here below. And we had a lot of material on every stage. And in general, we have videos, we have tutorials, we have additional information, everything that could help the citizen perform the tasks, because it already went to the beta testers. the universe beta testers, and of course, they judged that it's a bit complicated, but we tried everything to make it easier for them. I will just show two examples from the first stage and the last one, because there is not enough time. So on the first stage, the citizens extrapolate the tracks and guess if there is a displaced vertex. You see it here on green, and maybe you see another one, red, which is the true displaced vertex. And they get an immediate feedback from universe about the hits, if they guessed right or they guessed wrong. Then they jump for stage 2 and 3, they jump to Hypatia, which is interactive because it could not be done on the universe. And this is stage 3B, search for neutral long-lived particles. Here we have a star rating system, and we give them directions to look at some kinematic variables which would be characteristics of the long-lived particles. Last but not least, we have a working package of sense-impaired people, especially visually impaired and senior citizens. We are working with Wanda Diaz that you see here on the right. She is a blind astronomer who listens to the stars. Our collaborators in Argentina, CONICET, have developed a sonification software for the data. And we aim to cross-connect to artists and scientists. Here you just see a very recent article on Nature about Wanda working in Virgo and listening to the gravitational waves. Now I come to my conclusions. After tens of meetings with collaboration advisor board, EU review board, and Atlas, the new particle search at CERN is finalized and the platform is under review. The citizens, as soon as is given the green light, the citizens' data will be collected by about a year. Already at the beta testing, we have about 1,500 classifications. And then the analysis of the citizens' data will follow. The other three reinforced platforms are ready as well and under review. So thank you. And here is a list of our partners.
Thanks a lot for this very nice talk. Are there questions from the audience here? Seems not. And from the Zoom online? Okay, I don't see. Okay, no, we have a question here.
Thanks, Christina, and I really appreciate it, especially the last project that you are developing for sense impaired people. It's really nice seeing something similar. Maybe you said it, but I didn't get it. So, is this project open? I mean, worldwide? So you have citizens from all around the world, or?
Yes, all universe projects.
Okay, and how many citizens participate, more or less?
I don't know because it's not approved yet. So, but
Okay.
But to give you a number, the Higgs Hunter, which was similar with static images, our advantage is that we have interactive images of Atlas events, so people can click on tracks, look at the momenta, etc., etc. So the Higgs Hunter has had about 60,000 classifications.
Nice. Okay. Thank you.
Thanks a lot. So let's thank the speaker again if there are no more questions. Okay, and now we have, sorry, because maybe there is a misunderstanding. There will be a talk by Niharika, but we didn't see it uploaded. So, okay, hi. Do you have, you are muted.
Yeah. Can you hear me now?
Yeah, very well.
Yeah.
Do you have your presentation? And
Yeah, I have my presentation and I thought I had uploaded it yesterday, but I'm sorry, I think I might have missed it. Classes are going on.
okay,
So,
sorry for the misunderstanding. So you can show your slide and then we will restore the also the Indico page.
okay, thank you.
Okay, we cannot see. Okay, now we see your slides.
So you can see my screen.
Yes, not in full screen now. Yes, okay, please go ahead.
Okay, yeah. So good afternoon. It's afternoon in India. Good afternoon, everyone. I'm Niharika Kulshresht. I'm a high school teacher. And like I've been in teaching for around 30 years. And thanks for being here for this diversity education outreach. Like I'm a late entrant into, diversity and education because all my life I've been teaching physics. Now, recently I started doing a program on women and gender studies, and then I realized how it relates so well to my life. So I would here discuss what is the present scenario, why it matters that we should not have gender gap in STEM education, and what high school teachers can do to narrow the gender gap. So I'll first share in India. I would also like to share one of my, like in 1983, I was in class 11th and I mean, the computers were unheard of in those days. So I used to do what was called electronics hobby. And after my class 11th, when I went to my teacher, physics teacher, I had done very well in the hobby. So I wanted a validation from him in form of a certificate. He just laughed at me and he told me, are you going to use it as your dowry? And dowry is a social evil in India, which, the girl's parents give to the bridegroom. So these are the scenario in India. 12 to 14 years of age, most of the girls are very interested in science, but gradually this fizzles out. So by nearly 43% of the total STEM enrollments in the country are in STEM. But only 3% of the women enroll in PhD and 6% for a PhD in engineering and technology. And then what comes next is they account for only 14% of the total science engineers, technologists, and research development institutions. This also reflects an increase in women enrollment, particularly in medicine-related courses. But during the same period, enrollment in bachelor's in technology courses only went up from 39 in 2016-17 to 42 in 2019-20. Globally, only 35% of STEM students in higher education are women. And only 3% of female students in higher education choose information and communication technology studies. And the gender gaps are particularly high in some of the fastest growing and highest paid jobs like AI, computer science, and engineering. And if we go for recognition, only 7 women have won the Nobel Prize in chemistry and 4 in physics. So this is what we call leaky pipeline in STEM. Now, such huge disparities and such deep inequalities have not happened by science. It has taken years of socialization and stereotyping to reach where we are now. So why does it matter? It matters because STEM careers are the jobs of the future, and these are the jobs in which the leaders will be made in future. And these will be the driving force for innovation, social well-being, inclusive growth, and sustainable development. The underrepresentation of women in STEM puts them at a high risk of being displaced by technology. And let us accept that 49.6% of the world population is female. It matters because it results in unequal opportunities, and the opportunity cost is extremely high. For example, if at school level, girls are excelling in STEM subjects, and because of biases, stereotypes, or socialization, by the time they reach the stage of graduation and post-graduation, if they leave that field, it's a huge loss of talent and an unexplored potential. Now, teachers can play a significant role in dissipating stereotypes in STEM education. The most effective way to narrow the gender gap in STEM is to prevent it in the first place. By taking an early age approach, I believe that the pipeline can be plugged before it begins to leak. So now I will discuss some of the strategies which teacher can do to encourage the girls to not only take up STEM, but to stay in it. The first strategy could be catch them young. Interest and sense of belonging play an important role in girls' engagement in STEM at school, their subject choices in higher education, and their career plans. Early interventions are needed to sustain girls' interest in these fields. Now, this is also the age when stereotypes start forming in the children's consciousness. So if we could enforce, gender equality and gender equitable classrooms at a very early age in the high school itself, probably we will not have those leaky pipeline. Fun and engaging curriculum to stimulate girls' interest in STEM subjects, providing equal opportunities to all regardless of gender, encourage girl students to participate in competitions and clubs in STEM such as robotics, coding, and AI. Female role models. Most, whenever, I have seen in textbooks and in generally, stereotypically, most of the scientists are men, those disheveled hair, and they are mostly men, Einstein-looking men. And or astronauts, children usually relate astronauts to males. So if we could have more, we could introduce more female role models inside the classrooms, then girls would try to opt for STEM subjects. Then they can gain exposure to women in STEM through activities such as film screenings, guest talks, museum visits, or bringing those female role models into the classroom. Astronauts, we could have surgeons, we could have scientists coming into the high school classrooms. STEM achievers from the school alumni also can act as a great influencer, mentor, and role models, showing the path towards the achievable dreams. Another strategy could be STEM organizations exclusively for girls. Create all-girl organizations, clubs, and competitions that encourage young women to work together in a supportive environment. Giving young women this exclusive space helps them feel more supported and less alone in their STEM interests. The social component is very vital for the girls to keep them interested in STEM-based subjects. Then introduce them to the career paths in STEM. They should be provided first-hand experience in STEM employment through internships and career counseling at a very early age. Then we need to train teachers for gender-sensitive classrooms. Like if I honestly share with everybody, I'm a work in progress. I have also been through those, 50 years of socialization and everything there. But yeah, I'm trying to work on my gender sensitivity. So we need teachers who are more gender sensitive. Then we could also work on developing special skills in the girls, because these are positively correlated with performance in science and math. And they should be provided multiple opportunities of conducting hands-on experiments. Then provide positive feedback to the girls about their performance. Focus on the process of learning, the strategies used during learning, and the efforts made by them. I would say create a classroom environment that sparks curiosity and fosters long-term interest through project-based learning, innovative tasks, and technology. The most important thing is to be beware of stereotypes. Stereotyping of academic subjects. Like, there is a stereotype that physics and math are difficult subjects, and social sciences are easy, or languages are easy. So these are just stereotypes. So we have, high school teachers have to be beware of these stereotypes. We should not differentiate between subjects as being softer, which are meant for girls, and harder, which are meant for boys. Then then even the dichotomized version of science is gendered. The biologists have naturalized sex differences based on XX and XY chromosomes. And stereotypically, the intelligence has been associated with the size of the brain. Textbooks. A recent review by UNESCO of over 110 national curriculum frameworks in primary and secondary education in 78 countries found that many mathematics and science textbooks and learning materials conveyed gender bias. There were more figures of male than of female, or there were more boys shown in the illustrations than in the girls. And if we look deeply, even the language is biased. Like, there are words like mankind. So if a teacher is gender sensitive, even in spite of the fact that there might be certain things which creep into the textbook, if the teacher is gender sensitive, they can just point it out to the kids and make it matter. Adding images of female mathematicians or scientists throughout classroom materials, and assigning individual or group work that summarizes or contextualizes women's achievement in these subjects can also shift perceptions. And then the main thing which high school teachers have to fight is unconscious bias. The years of stereotypes, socializing, and prejudices which have crept into our consciousness. These are the ones which we have to be really alert of. I'll just give you one example. Like, if in a classroom, we find, in a co-ed classroom, you find that there is a boy who's creating mischief in the class. And so the easiest recourse the teachers take is, make the boy sit next to a girl, because it is understood that, the girl would have a calming effect on the boy. Now, this is a sort of stereotype, because we have taken it for granted that girls will be the nurturing and the boys will be nature. So we have dichotomized the roles of girls and boys, and it's time we started shifting our teaching so that we have a gender sensitive classroom, and the girls and boys have equal potential and equal opportunity to develop and grow into STEM subjects. Thank you. I come to an end.
Thank you very much. So, thank you. Let's thank the speaker and see if there are questions from the room. Seems not. And from online, from the Zoom? Seems not. Okay, let's thank the speaker again. And this was our last talk on diversity outreach and education session. And so I will close officially this session. And let me thank also on behalf of the other conveners, all the speakers for this lively session. And we hope that in future this session will be included in future editions of Nufact. So thanks again. Okay, we will reconvene at I lost the 12:40. Okay, so there is the lunch break. See you.
Thank you.
Hello, can you hear me?
Yes.
Oh, okay, thank you. So does anybody in plenary meeting hall? Not yet. Maybe people still having a lunch. Have a coffee. So yeah, maybe it's a time to start this session, but let us wait a bit more. Okay, good. Okay, recording is also. Thank you. So anybody in plenary session hall? On site is ready to start. I see people are joining. That's good. Oh, hello, Keith. Thank you. So maybe you can prepare for your presentation. Thank you. Okay, I see. Yeah, full screen.
Okay.
Okay.
All right.
So yeah, maybe we should start it now. If plenary session hall is fine, on-site hall is fine. Not yet. It looks the screen is. Oh, okay, it might be okay.
Okay.
Let me check. Somebody in their on-site can say something.
Yes, it's fine from here. I can see your slides and hear you.
Okay, great. Thank you. Okay, so let us start. So first speaker is Keith about the status of LBNF beam. Okay, please start.
Hello, my name is Keith Goldwitzer. I'm with the Target Systems Department and Accelerator Division at Fermilab. And this talk is on behalf of the LBNF Beamline team. That's part of the LBNF Dune US project. And so I'm going to give you the status of the beam. Let me see where. Okay, so I'm going to give a little bit about requirements that we're working towards, and then describe the primary beam, the target complex, the decay volume structure, the absorber complex. As I go through, I'll give a little bit of some recent work and talk a little about instrumentation. And our main focus recently is getting the civil facilities designed for what we want for LBNF. So the beamline requirements are designed for initial delivery of 1.2 megawatt beam power and make sure the facility is upgradable to 2.4 megawatts. And during this conference, you've heard about PIP2 and possibly PIP3 discussing about how they're going to achieve those beam powers for us. The proton beam energy can be anywhere between 60 GeV and 120 GeV. We actually work more toward the 120 G for most of our design work, but we do make sure that everything is compatible with running at 60 GeV. The pulse length is going to be 10 microseconds on the target, and the proton beam size is tunable between 1 and 4 millimeters. A few years ago, there was a beam optimization. It was discussed at the most recent Nufact, which maximized the dune physics. And there were some engineering constraints put on there. And as we've gone on with designing the equipment, further engineering constraints are. So we've ended up with a 3 focusing horn system where the optimization set the geometry and the spacing of these 3 horns. We also have inserted the target inside the first horn, and we put a limitation of the beam, the current pulse on the horns at 300,000 amps. It'll be a half sine wave, and of course, beam will be delivered at flat top. The target will be cylindrically symmetric and made of graphite, and the desired length of the target is to be 4 interaction lengths, which is about 1.8 meters. So you've probably seen the picture in the upper right before, showing the LBNF Dune project on the Fermilab site, where the beam is extracted from the main injector, or from the down on the blower part here, and the new part will be the extraction part. The beam will go up and onto this artificial hill and then down an angle towards the FAR detector in South Dakota. So the LBNF beamline part of the project is this primary beam here, where the proton beam comes to the target complex. You got the decay volume here, and then the absorber complex, which is all this first part of this picture here, but the left-hand side, which is the immunity detector building, is not part of LBNF beamline. That is a separate part of the project. You heard about that as well. So this artificial hill, it means that we're going to take the proton beam line and direct it upwards to a point that's about 17.5 meters above the main injector elevation. And then from there, it's bent downward at the correct angle to achieve the 101 milliradian angle that we needed to direct it towards the dune detectors. More looking at the beamline view of this, you can see all the different components involved here. There are 25 dipoles to bend it up and then down. There's 21 quadrupoles for the focusing, and then there's 23 corrector dipoles to help steer the beam and get it directed to where we want it to go. The project starts with installing kickers into the main injector and a Lambertson to direct the beam out. It then leaves the main injector enclosure, as I showed before, and then we go up a hill and then down. For the magnets, we have some international partners that are not part of the LBNF project, but are going to make in-kind contributions. For the dipoles and the quadrupoles, BARC of India are building these magnets based upon previous Fermilab designs, where they're at the point that they're about ready to prototype build some prototypes for testing. The correctors, IHEP from China, they've actually already been developed, produced, and actually delivered to Fermilab. So this is actually one that was delivered a year or so ago. For the target complex, the heart of making any neutrino beam is shown here. Beam is coming from the right down the hill. Goes through some shielding. There's a primary beam window followed by a baffle to intercept the very tails of the beam, as well as if there's an errant pulse from being misdirected from the beam line upstream. And then there's the first of 3 horns with the target inside of it, a second horn, and then a third horn at the very end of the target chase, the region where all the components hang. And then there's a decay volume window. And then the decay volume itself is all in helium gas. What's different for Fermilab this time is that we are not using air inside the target chase, but we're using nitrogen. This is to limit the amount of argon, radioactive argon-41 that's produced, as well as to eliminate water vapor as much as possible from the system, so we are not making nitric acid, which does attack the components. So that requires a hatch cover system that actually does seal, and we have actually been prototyping on that with our friends at KEK. To support all that, there's a series of support rooms, and I'll talk a little bit more about some of this in upcoming slides, but there's helium cooling that will be used for cooling the target. There's radioactive water systems that do the main cooling of the components directly. And then there's actually, furthermore, that nitrogen atmosphere is actually being blown about quite well to provide cooling for most of the shielding. And then there's also a horn power supply room. The target, UKRI is providing the target as in-kind contribution. They're going to build a prototype and production. We've settled upon using a cantilever target based upon UKRI's previous work with T2K. We did investigate making longer targets, but we concluded that using downstream supports just absorbs too many of the secondaries and reduces the neutrinos that are desired for the experiment. So UKRI is going to build a prototype that is going to be 1.5 meters in length. This is 50% longer than T2K, but it's short of the desired 4 interaction lengths that the experiment would like to see. And so after the prototype is built and tested, we'll do some testing to see how much it moves about when it's pulsed in the horn. We'll see how much it sags and so forth. We'll decide on be a decision point in whether or not to make the production target longer to get to be closer to this 1.8 meters or to actually maybe achieve it. There's been some prototyping by the people in the United Kingdom. There's this helium gas manifold. You can see here where the helium goes in, it gets distributed, it goes down around the outside of a tube that holds the target, and then gets turned in and actually then cools the target, and then the manifold directs it out. The beam comes in from the left here, and this curved part is actually the beam window into the target system and into this gray part, which would be the graphite that would be the target system itself. So there was some concern about whether or not you can actually manufacture this manifold, and so with UKRI has done a manufacturing prototyping of this. They're also working, which is not shown here, on how to make the titanium containment vessel here that holds this. This is longer than what manufacturers like to do, so they're having to learn how to weld these pieces as straight as possible and still keep the structural integrity. Focusing horns. This will be the next generation of focusing horns built at Fermilab. On the left, you can see a very complete looking design of what would be the first horn, horn A. On the right, you can see what an inner conductor would look like, and this in particular one is for horn B. Scales are not the same here because this scale on the right, the one on the right, is about twice as long as the one on the left. We have just started building the horn A prototype. We're receiving materials for it now, and we hope in the next 2 years to have it complete and then tested over the third year. As you can imagine, the integration into the target into the horn A is a large concern, especially with 2 groups working on it. So we have quite a few meetings with UKRI discussing how we're going to insert the target into the horn, how to mount it. And the big point here is that the target, everything that's on the green here is a green flange. It's going to mate up to the red flange. This house also has to be done remotely, which I'll show in the next few slides. So everything off the green flange is going to be provided by UKRI, and it has to connect up, as I said, to the red flange to hold it in place. And then you can see some piping here, and this is for the helium cooling system. Those have to be also connected. And then you can see these points up here. These are for instrumentation, which is pretty much strictly all thermocouples that help understand the temperature distribution as the gas is pushed in and other places on the system. This is going to take specialized equipment to remove and install the target assembly, and it's all done remotely. As you can imagine, these are very radioactive components after they've seen some beam. So you can see here, there's a table that's adjustable. It's going to be able to take one target out, put the next target in. And we have to also do this without touching the interconductor that's put in, attach the flanges, to connect the gas cooling lines and those instrumentation lines. Further work from this, we at Fermilab hang our components off of support structures, which are designed to secure the components, hold them in positions, and to position them precisely. So in this case, you see these rods here, one here and one there. Those go up and down to adjust the vertical position and the vertical angle of the horn itself. And then there's drives here to take the whole structure and move it left and right, or position it transversely on the beam. The end walls here, you can see along with that those rods that can hold the component below. There's a whole series of things that provide pathways for utilities, which include, in this case, the strip line bus, which carries the 300,000 amps down to the horn. There's also cooling water. There's also the helium cooling, and then there's the instrumentation. The walls are also part of the radiation shielding, and you can see in between these 2 end walls, there's a big gap, which does get filled in with shielding later on once the component's positioned. And as I said, connections are all done via remote handling. And we have a preliminary design of our work cell. Here you can see, this is a side view of that support structure. With the horn hanging below it and target on this exchange system, getting ready to be pushed in, a thick wall, and then we have telemanipulators, which will be then operated from this shielded room. What you can't see here, it's not very obvious, is that there's a lead glass window that's about 1 meter thick, that allows you to look and watch as you do this. We'll also have cameras inside to help look at things. We'll probably have a camera station at the end to make sure we're not hitting the interconductor of the horn as this goes in. Some recent prototyping work that has been done. This strip line, which is a hard metal bus. This is just 3 layers of a 9-layer strip line that will be used to deliver the 300,000 amps. We're doing some testing to make sure that we do not get sparking between layers. So we're testing the ceramics and isolators. and then how you join these pieces together with clamps, and this is a test of that. Another thing for us, what we do is that with the water cooling, we spray water on the inside of the horn to cool the inner conductor. The water is collected in a tank, and then it's pumped out. And since we don't want any really moving pumps on this, it's done by a suction system, essentially, a Venturi pump, which provide lots of water flow across it, and then it sucks water up these ejector lines. But this is these ejector lines are going to be on the order of 8 meters, which is more than we've done before. And we wanted to make sure we can do that. And the volume that we actually have to pull out of the water tank for the larger horns, which are the horn B, requires us to actually have run 2 in parallel. So we've set up a test, and we've recently shown that we can do this. And with our choices of the Venturi system is going to work. The decay volume, which is downstream of the target complex, is on the order of 194 meters in length, and it is filled with helium. And next slide, I'll show you a typical cross section. It is a big item. The decay volume, which is this inner circle here, is actually 4 meters in diameter. Outside of it, there are 2 concentric steel shields, steel tubes, which is providing some shielding, and is the containment vessel for the helium on the inner one. And we do 2 layers so that we can cool this with the nitrogen cooling, similar to like the nitrogen cooling that we're doing in the target shield pile. We're also using nitrogen to cool the steel tubes. Outside of that, to contain the radiation created by secondaries that intersect with the wall and then into the concrete, is we have at least 5.6 meters of concrete shielding around that. These other 2 circles here are essentially the nitrogen gas return lines from the nitrogen that's flowing between the 2 steel tubes that are here. At the end of the decay volume, this is the end of the decay volume here, there's an end cap window, and then we go into the absorber, the hadron absorber. Downstream of it, there'll be 3 stations of muon detectors, and with muon shielding, or some shielding in between, so that the 3 muon stations sample 3 different energy ranges of the muons that are created within the decays that are associated with neutrino production. With this amount of hadron shielding in front, so we're actually sampling the high energy tail of the muons that are created by the neutrino beam line that's upstream of it. The hadron absorber itself is also cooled with water, so we have a radioactive water room to support it, and above that, not labeled here, but is an instrumentation room, which will have electronics for the muon detector system, as well as a hadron detector, which I think is my next slide. This is
5 minutes left.
I'm sorry?
5 minutes left.
Okay. The hadron detector that's in front of the absorber we use it for beam-based alignment. So we use it at low beam intensity as part of our system to understand where our beam is directed. When we lower it in position from when we want to use it, and then we're going to raise it out and up into the shielding area when we are running full beam power. It's designed to be replaced. The absorber itself is made up of a series of aluminum and steel panels. It's water cooled. It's essentially, we are going to drill long lines in here, connect these long lines with the drilling paths. Then we'll plug up the first part of these so that our water path is just a simple square as it goes around. These are being designed to be replaceable, but we expect them to they are designed for 2.4 megawatts, and they are expected to last the lifetime of the facility, but we've designed them so that we can take them out if something were to start leaking. Some instrumentation that is going along and that we're going to use for monitoring during the experiment. As I said, there are these 3 muon stations behind the absorber. They sample the high energy muons that are produced. We're looking at, this is mostly used for monitoring. We're looking for changes in the muon distributions as a function of time, or as on a pulse by pulse basis, we can look at the number of muons that are produced per proton on target, make sure that we're being consistent on the beam we're delivering. We're also going to have a thermocouple array distributed through the absorber. This will help us monitor the showers that are produced by the protons that did not interact with the target. And so they're really sampling the very center of the absorber. We're going to have a hydrostatic level system, which will help to monitor the movement of the target station components. This is with respect to the final focusing, elements of the proton beam line, and they will just monitor the vertical movements. These can be caused by actually movement of motors or things like that, but also the thermal expansion that we do expect a little bit of thermal expansion, but we want to monitor it to make sure we understand it. And then there's instrumentation involved with the beam-based alignment, which is done at this low intensity. We scan the beam across different features on the horns and target and baffle system, and we look at responses of beam loss monitors that we insert into the target chase area, or we use that hadron detector at the beginning of the absorber area. This last year has been mostly work with civil facilities. They are working very hard to get their design done. The largest concentration that, of course, is involved is radiological issues. We have to make sure all the buildings have enough permanent shielding to handle the eventual 2.4 megawatts, as well as control of radioactive gases. There's been a lot of work to define the air flow path to allow most of the isotopes to decay before release to the atmosphere. We are limited in how much we can release. And as well as provide what we'll call a buffer volume between the radioactive air path and the atmosphere in case a quick storm comes through. We've in the past seen air pressure differences develop quickly and overwhelm our systems. So we've designed that into our civil facilities. We also want to control water, make sure that any water that does get into the buildings, we are able to capture and understand if it becomes radioactive with tritium, as well as any air handling units where does the condensate end up going. So quickly to go over what is being designed for 1.2 and 2.4 megawatts. Anything that's being designed for 1.2 megawatts is designed to be replaced for the future upgrade. So pretty much all the components that are inside the target chase, the baffle, the target, the horns, are being designed for 1.2 megawatts. It doesn't mean that we do expect, for instance, the third horn, it should be survivable at 2.4. We will check, but we're not going to make sure we design for 2.4 megawatts straight away. The beam windows on either side of the target chase are being designed for 1.2 megawatts, instrumentation and detectors. And I say some of the cooling systems, the amount of water needed to push through the system may change between 1.2 and 2.4. And if it means the difference of changing out some pumps in the future, that's what we're looking at to do. But we're also making sure that if it's only an extra $1,000 for an upgrade of a pump, we'll do that at the start. What is being designed for 2.4 megawatt and should not have to ever be replaced. Of course, the proton beamline components, those can be replaced, but where they're being designed to handle 2.4 megawatts. All the shielding, piping of the cooling systems between the support rooms and components, which are essentially buried in shielding walls and things like that. Those are all being designed for 2.4 megawatts. That large decay volume we don't want to touch after we use some beam on it. The absorber is being designed for 2.4 megawatts in the power supply. And my final remarks is that the beamline part is part of LBNF. The LBNF beamline is based upon the experiences of other neutrino beamlines built at Fermilab as well as in other places. Prototyping is in progress, and the facility will support an initial beam power of 1.2 megawatts and will be upgradable to 2.4. Thank you.
Okay, thank you very much. Yeah, I see great progress in the design and the prototyping. Thank you. So it's time for discussion. We have some 1 or 2 questions. You can have any questions? Please raise your hand. Oh, okay, Eric, please.
Okay, thank you very much for this this nice presentation. I have some question about the strip line insulation. You are mentioning that you are using ceramic. Did you make some tests about the? Do you have some experiment on ceramic behavior regarding the level of radiation? What are the main constraints are you considering in your design?
I'm sorry. My volume was too low. I did not hear your entire question.
Okay, I mean, can you comment on the strip line insulation?
Oh, the ceramic pieces that we're using for the insulation, it's the same component or composition that we've used in the past at Fermilab, and they're also been used at KEK as far as I understand. We're not really worried about the radiation aspect of it. We're more worried right now whether or not we've got the design correct for 300,000 amps, and that is our main concern right now, is making sure that we have enough spacing and that we are able to clamp them enough that the Lorentz forces from running the current through the bus doesn't push apart.
Okay, thank you.
Mm-hmm.
Okay, so any other questions?
We have a question in the room.
Oh, okay, please.
Andrea Longhin.
Sorry, a quick question. Which is the rate at which you foresee to pass the horn?
Let's see, the rate. I can tell you that the cycle time of the main injector ranges from 0.7 to 1.2 seconds, depending on whether you run to 60 GeV or 120 GeV.
Okay, so this is the upper limit of the frequency.
Yes.
Okay, thanks.
Mm-hmm.
So any other questions?
Seems not.
Okay. Okay, no online. So, okay, then thank you very much for the nice presentation. Let's move on next talk. Right. Okay, so next talk is JPAC neutrino beam and upgrades by Megan. Can you? Okay.
Yeah.
Thank you.
Yeah, so can you hear me?
Yes.
Oh, but maybe you cannot yet see my slides.
Not yet.
Yes. Now can you see my slides?
Maybe yes. Yeah, full screen. I think so. Okay, so then
okay.
Please start.
Thank you. So right, then thanks a lot to the organizers for inviting me to talk about the JParc neutrino beam and also upgrades to the JParc neutrino beam. So I'll give a bit of overview, and then I want to talk a bit about the JParc accelerator and upgrades to the accelerator that are happening right now, and then I'll talk a bit about the JParc neutrino facility and upgrades to the JParc neutrino facility. So the JParc neutrino facility provides the neutrino beam for the currently running T2K experiment, which of course is a long baseline neutrino oscillation experiment in Japan, which has been running since 2009. And I think there have been several talks this week on that, so please see those talks. And we also provide beam for a few other smaller auxiliary experiments. And we're upgrading our neutrino facility for T2K and also towards the Hyper-Kamiokande experiment, which is scheduled to start in 2027. And I think this week there have also been plenty of talks about Hyper-K. But so what we have is the JPark facility on the east coast of Japan in Tokai village, Ibaraki prefecture. And then we send a beam of neutrinos 295 kilometers to the Super K or Hyper K large water Cherenkov detector on the east side of Japan, on the west side of Japan, sorry. So that's what our experiments look like. And how do we produce the neutrino beam? So what we do is we take 30 GeV protons from the JPark accelerator, and we smash them into a long carbon target, and of course produce hadrons, pions, and kaons. And then we can sign select and focus the outgoing hadrons in 3 electromagnetic focusing horns. So then, for example, focusing pions, which decay into muons and muon neutrinos in a long decay volume. And if we change the horn polarity, we can switch between mostly focusing pi pluses or pi minuses, so mostly having a beam of neutrinos or antineutrinos. And then we can decay, we can monitor the muons in a muon monitor, which is downstream of the beam dump or sort of inside of the beam dump. And then, of course, the neutrinos go on to the near detector and onto the far detector. And JPark uses a 2.5 degree off-axis beam, which allows us to have a narrower neutrino beam energy spectrum. And so our neutrino beam energy spectrum looks like this. So on the left is what our beam looks like when we run with mostly muon neutrinos, and on the right is what it looks like for the antineutrino mode beam. And we get this quite pure beam of either muon neutrinos or antineutrinos. That's the biggest curve on these plots. You can see that there's a maybe 2 or 3% wrong sign background around the flux peak energy, for example, anti-muon neutrinos in the muon neutrino beam. And less than 1% NUI contamination again at the flux peak. Although when you go to higher energies, backgrounds become worse. And so in order to precisely predict the flux, we have to understand our proton beam and also all of our beamline components very well. And we also have to constrain hadron interactions inside and outside of the target. And so the first one we have to do by understanding our equipment well. And so when we design the beamline, of course, we design it with that in mind. And the second one we do with external experiments who take dedicated data for us. So this is what the JPark neutrino beam running status looks like over a function of time. The red and purple points here are the beam power. So T2K commissioning started in 2009 and started taking physics data taking in 2010. And you can see in this plot, we gradually ramped up the beam power from as low as just a few kilowatts in early 2010. And now a few months ago, we were running at 515 kilowatts. And you can see we've run with both neutrino mode running in red and anti-neutrino mode running in purple. And so far, we've accumulated a total of 3.8 times 10 to the 21 protons on our target. We've also been able to produce a very stable neutrino beam over these last 10 years. So this is a plot of the neutrino event rate at the on-axis near detector as a function of time on the top. And you can see that, it's quite stable. Of course, it changes when we change the horn polarity. And then the bottom 2 plots are the horizontal beam direction and vertical beam direction, which is measured again by various monitors. And you can see that we have this very good beam position and angle and event rate stability over more than 10 years. So JPark, I just described to you a conventional neutrino beam. Then, of course, what we want to do for our neutrino experiments is to increase the number of neutrinos. We want as many neutrinos as possible. And of course, the first step to doing that is increasing the number of protons as much as possible. Then there are a couple of ways you can do that. You can increase the frequency or increase the number of beam spills. And to do that, you can increase the beam repetition rate. And also you should, as much as possible, maximize your beam operation time. And the second one is, of course, to increase the number of protons per spill by reducing beam instabilities and beam losses and that kind of thing. And then, of course, after we increase the proton beam power in these 2 ways, all the components in the neutrino extraction beamline have to be able to handle that increased power. And of course, there are also other ways to increase the effective number of protons. For example, you can increase your target or upgrade your target to try to increase the number of right sign hadrons or increase the horn current to get better right sign hadron focusing or something like that. Yeah, so there are very major upgrades ongoing at JPark exactly right now. Yeah, focusing on all of these towards high intensity. So yeah, this year and next year. So now a bit more details about each component. So first, the high power proton source, which is the JPark accelerator. So we accelerate protons to 30 GeV, first in a 400 MeV LINAC, which feeds into a 3 GeV rapid cycling synchrotron, and then into this 30 GeV main ring synchrotron. And then we accelerate protons to 30 GeV, and then they undergo some fast extraction into the neutrino extraction beamline in red here, which bends the beam towards the neutrino experiment detectors. So the JPark main ring accelerator currently delivers 2.65 times 10 to the 14 protons every 2.48 seconds, giving us 515 kilowatts of beam. And we are increasing the beam power in two ways. One is to increase or upgrade the power supplies and also upgrade the RF cavities in the accelerator to reduce the time between the spills from 1 second, from one spill every 2.48 seconds to next year 1.32 seconds, and then more in the future 1.16 second repetition rate. And then we'll also improve our stability to increase the number of protons per spill by about 30%. And so, yeah, we're going to be increasing our beam power from the current 515 kilowatts to more than 700, and then up to 1.3 megawatts. And here's a table showing a bit more details of that main ring upgrade work. I won't go into this table in detail here, but I will point out that right now we're right in a long shutdown. And during this long shutdown, we are doing mass production and installation of new magnet power supplies. And so that's where we are now. And then after the shutdown, we'll be running with this 1.32 second repetition rate. And if you're interested in details about these main ring upgrades, there was actually a really nice paper that came out earlier this year that I strongly recommend you check out. But for the status of the work right now, so we have these new main ring power supplies that have this energy recovery using huge capacitor banks, and those have been developed and tested. So here are some photos of the big capacitor banks. That's a door back there, so you can see the capacitor banks are huge, and a photograph of the new power supplies. And all of these things are, being installed exactly now. And they'll be tested in April and May next year. And then the plan is to do beam commissioning with this new upgraded accelerator next June. Very exciting. Okay, then next I'll talk more about the neutrino extraction beamline. So what we do is we take the 30 GeV protons from the main ring at JPark, and we do this. We extract them into the neutrino primary beamline, which consists of a series of superconducting and normal conducting magnets that bend the beam sharply and bend and focus the beam onto the neutrino production target, and then outgoing hadrons are focused in some horns, and then pions decay into muons and muon neutrinos, and downstream we have muon monitors, and then neutrinos keep going. So here are some better photos of the primary beamline. So the beamline includes this series of normal conducting magnets on the bottom here, and superconducting magnets on the top right, again to just bend and focus the beam onto the target. And the beamline is, of course, also instrumented with a series of proton beam monitors, so current transformers to monitor the intensity, beam position monitors, beam profile monitors, and also beam loss monitors. So that's what our proton beamline looks like. And we're actually right now also doing upgrade to our primary beamline maintenance scheme. So the residual radiation dose at the most downstream end of the primary beamline is high, and there's nothing we can do about it. It's directly upstream of the target station. It's directly upstream of the target, and so we have a whole bunch of backscattering or radioactivity or whatever coming from the neutrino production target in the beam window that's scattering back upstream into our beamline. And the residual dose is reaching more than 1 millisievert per hour on contact weeks after we stop the beam, even at only 500 kilowatts. And of course, that's proportional to the integrated POT. And so that means that when the beam power goes up or we run for longer periods, this is only going to get worse. And so this is a photograph of the beam line at the very downstream end of the beam line. So the beam is traveling from the left of the photograph to the right. Sorry, the left side. Oh gosh, left side of the photograph is the target station wall here, and the right side of the photograph is showing the most downstream magnet. And you can see some beam monitors or a gate valve or something. And if something goes wrong with one of those components and we need to do maintenance on that component, it's very difficult to do hands-on work at this very high radiation dose. So we are upgrading this to basically make space for a quick hands-on maintenance by reducing the length of the most downstream bending magnet. And so this magnet that you can see in this photograph, we're installing a new shorter one now. And actually I went to the beam line yesterday and I happened to see the work in action. So this magnet is being replaced now, and this guy is actually working to replace this magnet. He was doing it yesterday. So yeah, that work is ongoing, and we also have plans to do a longer term upgrade to move to a more fully remote maintenance scheme. But this is rather major, so we'll be doing that a little bit further in the future. Next is proton beam profile monitor upgrades. So the proton beam profile is measured by a series of foil-based segmented secondary emission monitors, which are installed along the beam line. And each monitor causes 0.005% beam loss. So we can only use them for beam tuning, except for the most downstream one. The most downstream one is close enough to the target that anyway, it's very hot there. So we just use that one continuously. But there's some concern that the foils of these monitors can degrade. And also as the beam power goes up, the amount of beam loss goes up. And then you can start irradiating components with this beam loss and all these issues. So for example, this photograph on the bottom here is the segmented secondary emission monitor after 3.2 times 10⁻21 incident protons. And you can see very clearly where the proton beam has hit this foil and has caused a very nice brown spot. And so the monitor is working okay, the signal is fine, but we're worried that this darkening could indicate that it's become brittle or that it might break soon. And so this is a major issue. And so then we did some joint R&D with Fermilab to develop a lower loss beam monitor, a wire secondary emission monitor. And we've installed one of these in the beam line now, and it's working well. It gives 10 times less beam loss than this monitor we've been using since the start of T2K. And we've also developed a non-destructive profile monitor, beam-induced fluorescence monitor. And we developed it, we installed a prototype and we tested it in the JPark proton beam. And the bottom right plot here is the beam profile measured by our new monitor at at JPark. And so we're upgrading this prototype monitor now towards a full working monitor. And I actually gave a talk on this a couple of days ago. So if you're interested in this kind of thing, please check out my slides or ask me a question about it. We also have an optical transition radiation monitor, which measured the proton beam position and profile directly upstream of the target. What we do is, the beam hits one of these foils, and actually we have several foils mounted on a disc, and so we can rotate this disc and choose different foils to use in case, for example, one foil fails. We have had some decrease in the OTR light yield observed over the 10 years of running with it. And at first we were concerned some degradation of the foils, but it turned out to actually be radiation-induced darkening of an optical component, which is not in the target station, but upstairs. So now, right now, we're upgrading the optical system to use some easily replaceable components so that if it becomes dark again, we can just swap it out. And we're also, another thing we're doing right now is a new OTR disk will be installed in 2022, basically. And so we're also upgrading the titanium foils now. So we're going to add holes to all of our target foils so that we can cross-check the foil position using some backlighting, shining the backlighting and checking in the optical system for the OTR light. And we're also going to upgrade to thinner foils to have improved stress tolerance. And as I said, we'll be installing this new disk with new foils later during this shutdown. And we've also upgraded the OTR readout towards 1 Hertz operation, and also moved from using a Windows-based system to a Linux-based readout system for the camera readout for this OTR, which was done at UCL. And this upgrade is also going up. It's been tested and it'll go online for the next, when the beam starts next time. We've also upgraded the DAQ for other beam monitors. So all of the beam monitors are now being read out using a DAQ that can run at the 1 Hertz operation, or the 1.32 second beam spill beam spill repetition rate, and that's running now. That's running today. We've also been developing a new interlock system for fast beam interlock. So what we have been using until now, so we have this proton beam monitor, and it has a bunch of strips, and each strip is read out by an ADC, and then the ADC information is passed to a PC. And then on the PC, there's some analysis that calculates the beam position and width. And then, if the position or width passes over some interlock threshold, a beam abort interlock is fired and the beam is stopped. Of course, this is super important, because if the beam is in the wrong place or the beam is too narrow, we can seriously damage equipment. So we need this to work. But this process takes around 1 second, and that's too slow if we're running the beam at 1 Hertz. And so we're developing a new monitor, which basically we read the strip information from the monitor, and then using an onboard FPGA, we calculate the beam position directly, and then that FPGA can issue a fast interlock in less than 1 millisecond. And so then we can stop the beam very quickly. Yeah, so we are working on that. So next I'll talk a bit about the secondary beam line, so everything that's downstream of this wall at the end of the primary beam line. And so what we have is we have the neutrino production target and focusing horns, and they're kept in this gigantic helium vessel, where we fill it with helium to minimize production of tritium and NOx, which would be produced in air. So the J-Park neutrino production target is this 1.9 interaction length long monolithic carbon target, and we install it, actually insert it into the first horn. And it's cooled by helium gas, and we're increasing the cooling capacity for higher power right now. And also Rutherford is now developing a new target and a new beam window for 1.3 megawatts. And so that's also going on now. So here's some photographs of the different components going into the target cooling upgrade. And on the right is a photograph of the new prototype 1.3 megawatt target. Longer term studies are also underway to try to establish new types of targets to further maximize the number of produced neutrinos. So for example, it's maybe possible to increase the pion yield and decrease the forward-going wrong sign component using a new target design, for example, a longer target like the LBNF target, or a higher density or hybrid material target. So then one example idea is to insert a second, maybe higher density target into the downstream end of horn 1. So on the left is what it looks like for T2K right now, but then groups at Glasgow and Rutherford are studying the possibility of moving towards this double target design with targets inserted on both ends of the first horn.
We have 5 minutes left.
Okay. So next, I'll talk about the focusing horns. So electromagnetic focusing horns consist of an inner and outer conductor. And of course, a large magnetic field between the conductors is achieved by flowing some high current down one and back the other. And then pions of the correct sign traveling between the two conductors are focused, and the sign, the wrong sign particles are defocused. And of course, we can select which sign we focus based on the direction we flow the current. We cool the horn conductors by water spray between the two conductors. And we also have current carrying strip lines, which were cooled by helium gas, and that's being upgraded to being cooled by water. And JPark neutrino beam line uses 3 horns, and they have been running at 250 kiloamps, but exactly right now we're upgrading to 320 kiloamps, which is very exciting. And we're also replacing horns 1 and 2, which were built at University of Colorado. A little bit more details. So we're upgrading the horn power supplies. So what we've used until now is we have a single power supply powering horn 1, and then a single power supply powering both horn 2 and horn 3. And that has limited us to 250 kiloamps horn current. But right now what we're doing is we're installing a third new power supply, and we're installing a third new set of strip lines and a third new transformer. And we'll have 1 power supply for each horn, and then we'll be able to run with 320 kiloamps horn current. And what this gives us is, it's very clear, it's a 10% increase in our right sign neutrino flux and a 5 or 10% decrease in the wrong sign component, wrong sign contamination of our neutrino beam. And then details on this one. So the horn 2 strip lines are particularly susceptible to being hit by beam defocused by horn 1. And so for high power proton beam, we basically need to do a cooling upgrade. And so there's this newly developed method for embedding water pipes directly into these horn strip lines. And so now upgrades are ongoing to use this new water cooling for the horn 2 strip lines. And this is just a photograph of the horn production. So a new horn 1 was produced. We have a spare, and it's waiting to be installed. It's sitting at JPark. And the new OTR disc, which I talked about a few slides ago, is going to be installed in horn 1 early 2022. And horn 2 production is also underway at University of Colorado, and it will be shipped to Japan and installed also during the shutdown now. So you can see how, that's what horn 2 looks like as it's being built. We have this, I already said, a helium-filled decay vessel and helium vessel and decay volume. It's water-cooled by piping. You can see the pipes all over the walls of this vessel, in the photograph here. And the water cooling capacity is going to be upgraded by increasing the water flow, not this year, but sometime in a few years. And then the last one, this is not the most, this is super important. Radioactive water disposal. So it's essential to properly handle our radioactive water that we produce when we run the neutrino beam. The government has some regulations, and if we cannot properly handle this radioactive water, the government will tell us to stop running the experiment. So we must dilute and dispose of our radioactive water that we produce. And actually, we did not have the capacity to do that at 1.3 megawatts, but right now we're building a new dilution tank to be able to increase the water disposal capacity. And it's being built now. So here's a photograph before construction. So the new tank will sit here between these 2 other buildings. And here's a photograph from earlier this year of the tank being constructed. And this new tank will work at 1.3 megawatts. All right, and then muon monitoring. So I said we measured the secondary muon beam profile. It's actually monitor sort of inside of the beam dump. And this one is also super important to understand the beam alignment and healthiness of the target horns. We also use it for beam tuning and all of this. And now we have 2 redundant measurements of the muon beam profile and position. We do it using 7x7 arrays of ionization chambers and silicone photodiode sensors. But we've had some issues with degradation over time of this one, and IC also has some issues. And so now we're developing a new EMT, which is a PMT without a photocathode, as a more robust sensor option. So it's being tested now. And we've also been testing a muon current transformer, MCT. And this one is really interesting because it can actually measure the signs of the sign of the muons passing through it. So that one is quite exciting. And there was also a talk about this a couple of days ago. So if you're interested, please check out the talk from Wednesday. So yeah, this is sort of the overview of the schedule of the neutrino beamline upgrade. And of course, we're here in this red box working, yeah, very hard on a lot of this upgrade stuff. So okay, that's mostly what I wanted to say. So the JPark main ring power supply upgrade for the 1.32 second repetition rate, which will give us more than 700 kilowatts beam on our target. It's happening exactly right now. And further RF upgrades towards 1.16 second repetition rates towards 1.3 megawatts are coming in the following years. And we're doing a whole lot of upgrade work in the JPark neutrino extraction beamline in order to accept the high power proton beam. And maybe, yeah, my talk was too general and you want more technical details. And in that case, I urge you to take a look at our technical design report, which is at the bottom of this slide. So, okay, thank you. That's what I wanted to say.
Okay, thank you very much. Yeah, many interesting work currently ongoing. Thank you very much. So it's time for question or discussion. Any question?
We have a question here in the room by Francesco Terranova.
Okay, please.
Yes, can you put back the slides 25, where you discuss about the urns?
Yes.
Because I was wondering, why up to now you cool down using helium flow? Because the tritium production in the urn is generally negligible compared with the target. So I would have expected to have water cooling since the beginning.
Well, so, okay, I'm not an expert on the horns, but the horns are sitting in the helium vessel. So already they're in a helium environment. Then already there is helium there. So I think, oh gosh, it's certainly doesn't require this kind of upgrade work or complex system to flow water. So that was the initial design.
Okay,
but
I see.
Yeah. It's being upgraded now, so it should be fine for the future.
Okay, so any other questions? No questions? Okay, so we are a bit behind, so maybe let's close. Thank you very much for the nice presentation. Okay, so let us go move on next topic about the high power target by Kevin.
Yes, let me try and share my screen. Okay, can you see my screen full?
Yes, please start.
Okay, thanks very much and hello everyone. So my name is Kevin. I'm part of the Target Systems department at Fermilab, and today I'll talk about high power targets and really an overview of the challenges for the next generation high intensity neutrino beams, and also provide an overview of some of the R&D work that we're doing to address these challenges. So give me 1 second, let me get my... So yes, we need really high power targets that are robust for the future in order to maximize the neutrino production. And recently we've actually seen major accelerator facilities been limited in beam power, not really by the accelerators, but by the targets. And such examples include the NUMI-MINOS experiment at Fermilab in early 2010 to 11, where we had to run at reduced beam power due to failures to the target. And as recently as earlier this year, we've also had to limit beam power on our 1 megawatt target because of elevated temperatures at the downstream beryllium window. And similarly, we've had targetry issues at MLF and SNS where reduced beam power had to be directed to the targets because of concerns. So next generation upgrades and new facilities will operate at much higher beam powers and present even greater challenges. So you see the LBNF, Hyper-K are all going up from above 1 megawatt up to 2.4. And future down the line, we might have neutrino facilities that are 4 megawatts and or higher. So at this time, it's critical to do some target R&D. What we want to do is avoid compromising particle production efficiency by limiting the beam parameters that accelerators can deliver, and also maintain a reliable operation and accurately predict component lifetime in order to maximize the experiment time. So what we want to avoid, we've seen various failures in the past of targets, windows, and as you can see here, this is the NUMI target failure that cracked along the beamline position here. We've also have the beryllium window embrittlement cracking, and more recently the NOVA MET01 target. During the autopsy, we actually saw a cracked piece of graphite here. And other failures include, as I just showed, the NT01 target with a water leak. We've had horn strip line failure due to fatigue, and thermal shock damage here at Isolde, the target completely distorted, as well as the target containment vessel cavitation issues we've seen at the SNS. So this is basically our motivation, really, to address target challenges through R&D. So what's the scope of high power targetry? It obviously covers the particle production target. These include solid, liquid, fixed or rotating targets. Some of the facility requirements we have to factor in includes remote handling, shielding, radiation transport, air and the cooling system. And also all the other beam intercepting devices that are part of the target facilities and accelerators. So these are collimators, collection optics, monitors and instrumentation, beam windows, as well as absorbers. So high intensity targetry challenges. We have heat removal. This is removing heat deposited in the target away. The physics performance, obviously, the target is optimized for physics. Operational safety in terms of shielding. We have storage and disposal of these activated materials when we have to replace them. And the last two are the thermal shock and radiation damage. So the high power targetry community has identified both these material behaviors to be the most cross-cutting challenges facing high power targetry. And here list additional neutrino beams challenges here to do with the actual beam on target, as well as focusing the beam-based alignments, and monitoring the hadron production. So what is radiation damage in materials? This is beam-induced damage to the microstructure of the material after a sustained bombardment of highly energetic particles. So the little schematic on the left shows the reactions, how high energy particles interact with the target nucleus and produce the various processes. So what happens during radiation damage? You get atomic displacements. So this is disruptions to the lattice of the materials. And we use this displacement per atom metric to measure the number of the average number of stable interstitial and vacancy pairs that are created in the lattice. And from that, over time, we have creation and agglomeration of point defects. You get segregation and depletion of point defect sinks, as well as creation of transmutation products. These include hydrogen and helium production in your actual material. So what are the effects? So the microstructural disruptions then lead to changes in the bulk property of the material, and all properties that are important for thermomechanical health of the target are affected by radiation damage. So I list these properties here. And on the right here, you see optical micrographs of tungsten compression specimens after they were compressed to about 20% strain at room temperature. So for the 0 dPAs, no damage, you see no cracks, it's just been compressed. And as you go up in radiation damage and dPA, you see cracks showing up on the surface, possibly indicating that the material is now more brittle. So all these radiation damage, the actual radiation damage effects is very dependent on the material and irradiation condition, and in particular, the radiation temperature, the dose rate, and the actual particle energy and type interacting with the material. So here are a couple of examples of radiation damage effects from neutron irradiation. And this plot here shows how significantly the thermal conductivity of the material can degrade with only 0.02 dPa. This is for graphite. And this loss of thermal conductivity can be very damaging, degrade the cooling efficiency of the target. We can get overheating, and as well as excessive expansion or dimensional changes in the material. We also have swelling in graphite. It's a very complex process. We have expansion, swelling in one direction of the lattice structure, and compression in the other, which the A is a basal plane direction. And here is another example of void swelling in stainless steel. You clearly see how the dimensional changes occur upon radiation. So swelling is basically result in dimensional changes, and you can get a reduction in effective density of the material, thus affecting the particle production efficiency on the long term. Secondly, we have the thermal shock effects. This is due to high intensity pulse beam that creates a localized area of compressive stress. This is the stress is generated due to the expansion of the material, which is surrounded by cooler material, and that what happens is it sets up dynamic stress wave that travel through the material at sonic velocities. And an example here is the NUMI 1 megawatt target, where with one beam pulse of 10 microseconds, you get a temperature jump of about 250 degrees C, at 250 K. And on the right here, you see how the thermal shock can actually induce a plastic deformation, cracking, and failure. On the right here, you see an iridium target tested with one single pulse at high red mat, and you see how it's totally destroyed the material with the intensity of the beam. So an example of stress wave, this is analysis that were done for the T2K window with one single beam pulse. You see how it generates stress cycles through the beam window, very thin beam window, and these stress cycles repeats themselves after every beam pulse. So it can lead to fatigue failure of the beam window over time. And some of the properties that really drive thermal shock are the specific heat, which will determine the temperature jump, the coefficient of thermal expansion, the strain, the modulus of elasticity gives you the stress that the material will see. And here I provide some equation, first order equation to estimate the initial stress wave amplitude. So given a set of material properties, you see if the beam power goes up, you deposit more heat in the material, so delta T goes up, and therefore directly drives up your initial thermal shock effect. So, and the key here is also all these properties are also dependent upon radiation damage. So as your properties degrade through radiation damage, you expect the thermal shock response to be even stronger. So there are extensive amounts of nuclear materials radiation damage available, especially on graphite, but unfortunately, we cannot directly use them. So as you can see from the plot here, I show from the table here, I show the difference in irradiation conditions between low energy neutrons versus high energy protons. And the main values to take into account here is the dPa rate for high energy proton beam in materials are orders of magnitude higher, and the helium gas production from high energy proton beam is also orders of magnitude higher. So we cannot really use radiation damage data that are in the literature for neutron irradiation. And therefore, there's a need to generate new materials data for specifically for high energy proton targets. So here's a map of material challenge parameter space for targets and beam windows. And what I plot here on the y-axis is the fluence per pulse, representative of thermal shock severity. On the x-axis is the accumulated peak fluence over the lifetime of the target, which represents radiation damage and severity. So as you can see, I plot some the red dots markers here are those targets that failed in service. The blue ones are those that completed service life. And you can see that we've had mixed failures and those successful targets over the years. But as we move on to future experiment, which are shown in green here, we're actually pushing the limit in terms of radiation damage and thermal shock severity. So we expect at least a 10-fold increase in accumulated proton fluence in future multi-megawatt facilities. So to address these material challenges, the HPT community formed the Radiate collaboration in 2012, I believe, with Fermilab as the leading institution. The goal was to bring experts from the accelerator and fission fusion communities together to generate new data for accelerator materials. So over the last few years, the collaboration has grown up to about 14 institutions. And the activities we're currently involved in is really analyzing the materials, failed materials from existing beamline, as well as executing irradiations of candidate target materials at low and high energy beam facilities, and also doing in-beam thermal shock experiments. So our website, I believe, is currently down, but it should be up soon. But if you have any questions regarding the Radiate collaboration, feel free to contact our program manager, Dr. Frederick Belmont here. I think I provided a hyperlink to your email as well. So high power targetry R&D, what that entails is basically examining targets and beam windows materials behavior under prototypic multi-megawatt proton beam conditions. So the benefits to that is I list here. This will drive the selection of the alloy created material and the heat treatment that would be needed, where we should be able to identify novel candidate materials. It will dictate and give guidance on the cooling system design and operating temperature, the tolerable beam intensities, and also the expected lifetimes of these components in beam. So in the next few slides, I'll give some insight into the type of R&D that we've been doing on these materials. So we have the graphite, which is a target core. We have beryllium and titanium, which are beam windows, primary beam windows, as well as target containment windows, and also novel materials that we're studying in order to try and push the state of the art for targets by exploring newer materials and qualifying them. So as a first approach, we have studied targets and windows which have failed in service. This is an example of a failed target, the NTU2 target at Fermilab, which actually showed gradual decline in the neutrino yield towards the end of the target's life. So this was attributed at the time to radiation damage, but then we decided to do some autopsy and extract these fins, these graphite fins here. They were 20 by 20 and width of about 6.4 millimeter. We extracted them from the target and then shipped them to participating institutions for post-irradiation examination. And I have to point out that these are all activated, so it was a lot of effort to have these shipped, and then all the analysis had to be done in hot cells with telemanipulators to do the measurements. And one of the initial results here is from PNNL, where they've measured the fins, and what we found is bulk swelling of up to 4% here. So again, this can lead to a reduction in the effective density of the material, and also build up internal stresses in the graphite, which might have led to it actually fracturing along the beam line here. We also took these graphite fins for X-ray diffraction at Brookhaven's NSLS2. So this is basically using X-ray to measure the lattice parameter changes of the graphite from these fins. So what we've done here is basically scan the X-ray beam from the top to the bottom of these fins. So we're going from away from the beam to the center of the beam and then away again. And what you see in this plot is basically the peaks that show for the 002 plane, the diffraction patterns peaks. What the larger peak indicate more intact material. So as it goes to the beam center, you see that it gets flatter, which means that amorphization has occurred. So it's lost, the graphite has lost its crystal structure. And the peak shifts also indicate the lattice swelling between the atoms that we've observed here. And this result really is interesting to get, as it confirms the bulk swelling measurements as well. Another material that we've used to analyze, which failed in beam, is the NUMI beryllium window analysis. This is from the NUMI beamline. Is a picture of the beryllium window here. And when we extracted it, we saw cracks near the beam spot. As you can see, we did some dosimetry film, and the high exposure area matches the area of damage exactly, really. And this is work that was done by Slava at the University of Oxford. So he's done some analysis on this fracture mechanism here and observed some transition from transgranular fracture to grain boundary mixed mode fracture and irradiated beryllium. This could be due to the weakening of the grain boundaries or strengthening of the matrix. And he's also done some hardness measurements on these materials at various locations on the window, spanning from 0 dPa all the way to 0.5 dPa. As you can see here, he's done a hardness measurement as a function of the angle of, relative to the crystal structure here. And you see a definite increase in hardness for the irradiated materials. Increased hardness basically means less ductility and more brittle, which means that there's a higher chance that the material will fail suddenly with a rapid growth of cracks, which we don't want. So another approach is that we're taking in our R&D work is to export candidate material specimens to prototypic high-energy proton beams. So this is a facility at Brookhaven where we're able to irradiate materials in tandem with a medical isotope production. And what we have here is very small specimen tightly packed in this capsule. These are only about 70 millimeters in diameter, and then stacked upstream of the isotope targets where we can irradiate these for a long time to accumulate damage in those materials. It's a challenging experiment. It takes about 2 years or so to design, and then at least 3 to 4 years to run the experiment, and then allow for cool down and do the PIE work on activated material in hot cell. So we completed this in 2018, and we had over 200 specimens here, a lot of different participants, and we, as I mentioned, it takes a long time, so we're still doing some of the post-irradiation examination on the different materials.
You
Here I
have
show
over
results.
5 minutes left.
Okay, thanks. So here I show results from tensile testing of the titanium alloy relevant to beam windows at both Fermilab and KK especially. And so what we've seen here very briefly is a significant reduction in uniform elongation, which we do not want. So as you can see, before irradiation, we had these curves here as stress versus strain. As we pull these specimens before irradiation, we get a lot of plastic deformation. But after irradiation, we see a sharp drop in the uniform elongation, which is, as I show here, is from 0 to where the peak of the stress is. So this is very interesting results. And again, this had to be done. I show pictures of this work all done in hot cells at PNNL. And what we found here between those two different alloys is that evidence of the Ti3Al 2.5 alloy is a little bit more radiation tolerant. We've also been able to do high cycle fatigue testing. This is the first high cycle fatigue data on irradiated titanium that's been generated. This was done with a custom-built device at Fermilab. And as you can see here, this shows the maximum stress and the number of cycles at these stresses that it would take to fail the material. And the control specimens were unirradiated. And with the irradiated specimen, we see a significant drop in the fatigue strength. So this will provide insight on where we want to operate in terms of stresses for these beam windows. And we're also doing a novel ultrasonic mesoscale testing at MRF in the UK. This is a foil that was irradiated at Blip, and we've shipped these to MRF recently, and we'll use this new setup here to extract fatigue life data. And it's very high frequency, so we can accumulate a lot of cycle within a very short period of time. So another method that we're using, strategy, is to investigate radiation damage in materials using low energy ions. The idea here is to accelerate the R&D cycle and be more efficient at down selecting materials. And one of the initial irradiation we've been doing is graphite with helium ions. This is at the University of Michigan, MIBL lab, and work done by Abe Burley. So he's already done some irradiation here to impose up to about 0.8 dPa in graphite. And he's done some AFM measurement to show bulk swelling, as well as TM work that shows lattice swelling consistent with those observed from the NTO2 target. We've also done similar work by Slava with helium implantation and beryllium. The idea was to impose both displacement damage and helium implantation to mimic the high helium that's produced in high energy proton beams. And what you can see here, he's done this up to a depth of about 3 microns. We see this photo here showing the actual helium implantation peaks. And from these specimens, he then did some hardness measurement to show that indeed the hardness does increase when you irradiate with iron as well. And the plots here, if you can see clearly, it's at 2 different dPa. It's at 2 different dPa levels, as well as 2 different. It's at 2 different temperature levels. So if you see the lower temperature specimens show a higher increase in hardness than the higher temperature, irradiated temperature specimens. So there's a lot, it's a complex process. We see helium bubbles typically form when at higher temperatures. We've seen this with a NUMI beam window at 360 degrees C, but then we also have evidence of higher temperature is usually desired to anneal displacement damage. So it's a complex process we're still trying to understand. And in parallel, we're working with University of Wisconsin to do a project on radiation damage modeling to simulate a bubble formation and migration in beryllium under different irradiation conditions. Moving on to thermal shock experiments. So we've done this at the CERN's High Redmine facility. This is a dedicated facility at CERN where you can use single shots to do thermal shock experiments on materials, really. And we've done a test in 2015, which was very successful on various beryllium grades. And we were able to see distinct thermal shock response between the various grades, and also able to validate a highly nonlinear Johnson-Cook model, which now gives us confidence in modeling these material response at different higher beam parameters. And more recently, in 2018, we did a unique test including pre-irradiated material specimens. This is where we tied in radiation damage and thermal shock together in the same experiment. And we're still doing analysis here to get data from there. And very quickly, I'll talk about novel target-tree materials. So again, the idea here is to look forward and try to develop new materials that could replace some of the target and beam window materials. We have nanofiber electrospinning materials at Fermilab. The idea here is that the continuum is discretized at the microscale, which will help absorb and dampen thermal shock. And we've also seen some evidence of radiation damage resistance for these nanofibers. We're also looking at high entropy alloy. This is relatively new. It's alloy consisting of 3 or more principal elements. And we've seen evidence of inherent properties for enhanced radiation damage resistance. So we're just starting to work on this. And it looks like a promising material that could be used for accelerator applications. So in the interest of time, I'll quickly mention that we're also involved with a variety of other activities regarding HP high power targetry R&D. I've given you a few insights on what we're doing. And here I'd like to point out that we're now focusing a little bit more at developing more effective alternative testing methods to help reduce the cost and duration of our R&D cycles. So these include low energy ion and electron beam for radiation, as well as pulse electron beam to do fatigue and thermal shock studies. And we're also putting a lot of effort in radiation damage modeling using ab initio and molecular dynamics modeling. We have different groups. We're working with different groups at University of Madison and PNNL for this. And obviously we have the novel, as I just mentioned, novel materials development, as well as novel targetry concept, which different groups are also working on. So in summary, I'll reiterate that yes, of course, the future neutrino beams present critical targetry facility challenges. We believe and understand that material behavior under these high beams, high intensity beams, is high priority in regards to radiation damage and thermal shock. And therefore, we're continuing with the R&D work to help us and guide the design for more robust components with a goal to maximize primary beam power in the target. So we have a globally coordinated R&D activities. We are investigating alternative testing methods, and also with the novel targetry concept and materials being explored and developed. We hope to be able to make some progress regarding targetry for future facilities. So that's all I had today. Thank you very much. And I'd like to point out all our collaborators here that's worked on the various high power targetry projects over the last few years with us.
Okay, thank you very much. Yeah, it was interesting results and very good summary. Thank you very much. So any questions?
We have a question here in the room.
Okay, please.
Okay.
So let me note first that you did not mention mercury. So I think mercury is really out for environmental reasons, and you seem to register that. Although there are still experiments planning for mercury targets. A question I have is about thermal shock.
Right.
And this in particular in view of the proton complex for muon cooling, muon collider projects, where the pulse length, which ordinarily for neutrino experiments is of order of microsecond, we have to bring down to a few nanoseconds. So the same charge, or even higher charge, 10 to the 14, 10 to the 15 protons, in a several nanosecond long pulse will then hit the target. What has that as implications from the point of view of thermal shock, that this very high charge is delivered in such a short time? Could you comment on that?
Yes, so let me go back to my slide. Can you see my slides?
No.
I'm not sure what happened here. Let me try again. Okay. So yeah, so thermal shock is really, let me show you the equation here. I mean, what's driving it is really the time you deposit those energy, the heat deposition in the target. So for the same beam intensity, if you reduce the pulse length, you expect that initial stress magnitude to be generated to increase significantly, right? So if you see the equation here, as a delta T here represents the pulse length.
Yeah.
So if this goes down, you expect an increase in.
It's linear.
Yeah, this is just a first order, one-dimensional. So I mean, if it's 3D, you get some other effects there. But yeah, that's the driving factor in stress wave here.
So, but we're really talking about 3 orders of magnitude here, going from a microsecond to a nanosecond order. That seems to be a very big step then. And the question is really what complications this will provide for the muon collider proton complex targets.
Right, and it's also, I mean, the beam spot size to target size aspect ratio is also something to consider too. So if you have a very tiny beam spot and then you have a lot of cooler materials surrounding it, then you generate a lot more thermal shock, really. Whereas if the beam spot is blown up, is larger, that's another way to reduce thermal shock effects, is blowing up the beam spot.
And if you have a granular target with small granuli or spheres, would that help then when we approach these very short, high intensity or high charge pulses?
Yeah, I think granular or powdery target will definitely help. I think there are a few groups already working on that, and basically what you're doing is mitigating the stress wave propagation, right? If it was a full solid target, so you distribute it on the powdery or pebble bed sort of targets. So that will definitely mitigate the stress wave response compared relative to a full solid target. So, but then again, there are other associated challenges with running the pebble targets or powder targets.
Thank you.
Yeah.
Any other questions? Okay, seems not.
Doesn't seem so in the room.
Okay, so then this is the end of Accelerator Working Group plenary session. Thank you very much for all speakers again. And we are a bit delayed, so I'm wondering we should resume when. How about May Hall? We planned 10 minutes break. But
we come back at 25, I would say.
25, okay. So let's have 9 minutes break.
Yes.
See you later, sir.
Thank you.
Thank you.
30. Okay, let's go. Let's come back at
okay, 14 minutes later.
People ask for 5 minutes more. Okay. 30.
Più che altro bisogna dirlo al combino che è l'unica cosa che può. Sì, quello sì. Perché ok, combino. Sai quello dei monti. Non so uno dei perché se è lui che deve iniziare. Prendere Paolo. Andate a prendersi il caffè in fretta, adesso glielo diciamo.
Yes. But they should not expose their fear. That's very they are, yes. So yeah. We would be late in time. We are not part of the company. Right, just that we haven't thought about for a long time. I agree that is something that, but there are a lot of politics in our field. Japanese doesn't want to. Yeah, they have invested. I know. No. It is not trivial. And what is optimal cannot always be. So that's right. Okay.
Yeah. So this is on. Yeah, this is on. All right. So people are coming in, and we'll start the second plenary session of this afternoon. So I welcome you all on the muon physics plenary session. And we have a few overview talks. So at the end, we'll have a overview talk on charged lepton flavor violation experiments. We have a theory overview talk, but first of all, we start with the experiment that got a lot of attention this year. And so Simon Korodi will present the G-2 experiment and results. So you have 25 minutes, Simon, for your talk, and I'll give you a 5-minute warning if needed. So yeah, please go ahead.
Thanks a lot. Yeah, thanks a lot, Frederick. Yeah, hello everyone. My name is Simon Korodi, and it's my pleasure to present here the results from the muon G-2 experiment at Fermilab. I would like to remove this. I would like to directly start with kind of where we are. So as probably most of you know, that the Fermilab muon G-2 experiment we announced our first result earlier this year. It was the 7th of April. And this is what you see here. That's a slide from the announcement talk given by Chris Polly, our spokesperson at the time. Our result, so the first result of the Fermilab G-2 experiment is here shown in red. It's in really good agreement with the predecessor experiment from Brookhaven, here shown in blue. And the new experimental world average is now in a 4.2 sigma tension with the prediction of the standard model. In parallel to this announcement, we published a paper. So we have our main paper, the PRL, shown here. And the collaboration managed to have 3 companion paper published at the same time. They are listed here. As Frederick already mentioned, the result was really picked up in media quite a bit. So these are kind of newspaper articles around the world. And it was also picked up in pop culture as kind of indicated down here. So my goal for this talk is to kind of show you how we got to this point, what this means, and give you a few details about this announcement. So let me get started from the beginning. So the magnetic moment of a particle, mu here, is connected to the spin of a particle through the dimensionless vector G, highlighted here in red, the chiral-magnetic ratio. What we measure in the experiment is the anomalous magnetic moment, a mu, here defined as G-2 divided by 2, therefore also the name G-2. In parallel to the experimental efforts we are undergoing, there was the muon G-2 theory initiative. That's a collaboration of theorists led by Fermilab that came together and published a white paper that, with a recommendation of the calculation of a mu from the standard model. That's the number I show you here, and I would like to just walk you quickly through it. So we have the Dirac G+2 for spin 1/2 particles term, which is not part of a mu, right? So that's the part that's not in a mu. Then kind of the leading order, it's the famous Swinger term, which is the first order QED. Then we have vacuum polarizations, higher order QEDs. I tried to indicate the size of these contributions here with the color scheme. Then we have hadronic contributions, we have light by light, and we have hadronic vacuum polarization. What I would like to highlight here is that these are 43 times 10 to the minus 11 uncertainty, and the theory prediction or calculation of a mu is really dominated by this hadronic vacuum polarization of 40 times 10 to the minus 11 here. Then least we have the really well understood electroweak contributions here. So now that we have basically a prediction or a calculation for a mu from the standard model, how do we actually measure a mu in the experiment? We do this at Fermilab. We do this with a storage ring that's shown here. So the experiment essentially consists of this large donut-shaped superconducting magnet with a strong 1.45 Tesla magnetic field here between the pole pieces, which allow us to store the muons we get from the beamline over here. The concept is the following. So we get highly polarized muons. We store them in our ring, and then we have the cyclotron frequency that's indicated here with the momentum in the green arrows here. So we store them so that the momentum goes around the ring. In addition, the spin of the particles precesses in the magnetic field that's indicated here with red and the formula over here. And if you assume now G would be exactly 2, this means a mu is exactly 0, so there's no anomalous magnetic moment. This term here cancels out. This means there's a constant phase between spin and momentum around the ring. But now we know G is larger than 2. There is an anomalous magnetic moment as indicated here. This means there's a phase difference evolving over time between the spins here shown in red and the momentum shown in green. This is what we call omega A. That's defined as the difference between spin precession and cyclotron frequency. It's the spin precession frequency we measure in the experiment. So in order to measure a mu, we need to measure these 2 parts. We have the spin precession frequency, as I was mentioning, and we also need to measure the magnetic field shown here. And in experiment, we do this with NMR, which allows us to relate the magnetic field or express the magnetic field in terms of precession frequency of protons indicated with omega p here. So in a sense, this is a co-magnetometry experiment. This really nice kind of formula form up here. Unfortunately, that's only true if everything is perfectly on orbit and in one plane. So this formula has additional parts. These are shown here. So we have one contribution here, which is proportional to the momentum dot the magnetic field. And since we are in a storage ring, this is kind of by definition or by construction, this term is rather small. And then we have a second term, which is proportional to the momentum cross the electric field, shown here. And as I show you, or will show you later, that we have significant electric fields in our experiment. So this term is not small at all. But at the Fermilab experiment, we operate, or we get muons at the magic momentum. And this means we basically choose the momentum of the muons to minimize this term here, or to minimize this. So these two terms, they give rise to corrections we have to apply afterwards, or in this talk, they are going to be called CP and NCE. We're going to see them throughout the talk. Okay, with this, I would like to kind of focus on what we measure. So in order to measure a mu, we have these two quantities we need to measure. In the nominator, we have omega A, which is the precession frequency of the muons. And then in the denominator, we have the magnetic field, where this is the magnetic field experienced by the muons expressed in terms of precession frequency of protons. In addition, we have these terms here, which that are all known either from other experiments or from literature. And kind of the largest uncertainty we have here is this 22 ppb shown here. The TDR goal of G-2 experiment is to measure a mu on 140 ppb level. This is a fourfold improvement over the last measurement of Brookhaven result. So in the following, I would like to kind of focus on this ratio here. That's the parts we actually measure. This is kind of our master formula we use to kind of go through the analysis. I'd just like to walk you through. So we have this precision frequency of the muons that's already mentioned. Then we have a blinding unblinding factor in front of it. And then we have corrections in the nominator here due to the beam dynamics. In the denominator, we have the measurement of the magnetic field that's shown here. We need to weight the magnetic field measurement by the distribution of the muons actually in the storage ring. That's shown here. We need an absolute calibration to be able to express this in precession frequency of protons. And then we have also corrections to the magnetic field due to fast transient magnetic fields down here. Okay, with this, I would like to kind of walk you through the full chain. And so for us, kind of everything starts with 8 GeV protons at Fermilab in the recycler ring. That's shown here. So that's the Fermilab beam accelerator complex. We have a target station over here where we produce the pions, and then we have the delivery ring where the pions decay into the muons, and the leftover protons are kicked away. Then in the end, the muons are guided into the muon campus. So this is the muon campus over here. We are located in the MC1 building, which is exactly located here. This is how the experiment looks like. I showed you before. And once we get the muons into our experiment, we store them in our storage ring up to 700 microseconds, which corresponds to 10 times the lifetime of the boosted muons. We get the muons in a pulsed scheme, so we get 2 times 8 shots every 1.4 seconds. Once we are in the experiments, the most important part of the experiment is the storage ring, and the storage ring we are using, it's not new, it's the same storage ring that was used in Brookhaven, and it was literally shipped from Brookhaven to Fermilab. It was shipped across half the country, and then up the Mississippi, and then trucked to Fermilab, as kind of these pictures show here. This led to this really amazing shot where we have a Fermilab Wilson Hall shown here. We have the storage ring arriving on the truck, and then we have typical Chicago weather here in the background. Okay, once we are kind of in our experimental hall, MC1, we have the storage ring, which consists basically of this really well-shimmed magnetic field. There's a lot of effort went into really shimming this field to get it as homogeneous as possible. The first thing you need to do to actually be able to store muons is the inflector. The inflector itself is a superconducting magnet that cancels out the field in the injection channel over here. So we end up with a field-free injection channel, which allows us to bring the muons actually inside our ring with an offset of roughly 8 centimeters to the storage orbit shown here. So now we get the muons in with this little offset. If you do nothing, the muons would directly leave the storage ring on the other side. So what we have to do is we have to cheer them onto orbit, to a storage orbit, and we do this with a fast kicker system. Fast kicker system is located here. This is how these kicker plates look like. And really the purpose of these is to kind of change the orbit of the muons, kind of sketched here in green, to this red version where we basically store them or we are able to store them in the ring. So a few more details about the time structure. So what this shows you here is the time structure of the muon pulse shown in red as measured by our T0 detector. Then you see the time structure of this kicker pulse. This is shown in black here, overlaid. And then these blue bars or dashed lines here. This is the cyclotron period. So this is the time it takes the muons to get runs around the ring. And I think here you see the concept quite well. So the idea is to give the muons in the first orbit a kick, to tear them on orbit, and then afterwards the kick is basically not present. So now that we have the muons in our ring, we need to actually store them for some time. So we need focusing. We have radial focusing from the 1.45 Tesla vertical magnetic field I already mentioned, but we also need some form of vertical focusing. And we do this with electrostatic quadrupole plates. These electrostatic quadrupole plates cover 43% of the ring. They are located at these locations, as kind of highlighted here in the picture. And this is how it looks like. So we have these quadrupole plates. We have a positively charged plates at the bottom and top, and then we have negatively charged plates on the sides. And just as a reminder, right, we can do this. We can apply these pretty large electric fields because we run at the magnetic momentum. This means this term in front of this one is minimized. It's pretty small. Okay, now that we are able to actually store the muons, we need to detect them. We do this with calorimeters. We have 24 calorimeters. They are distributed around the ring. Again, I try to highlight it with these circles here. This is how the supply box looks like. The calorimeter actually is up here next to the ring. It consists, well, each calorimeter consists of 54 Cherenkov lead fluoride crystals that are then read out by sequence as shown here. This system has a support system, which is a laser system for gain, response, calibration, and monitoring throughout data taking. So how does this look really in detail? So we have the muons on orbit, then they undergo Michel decay. The parity violating nature of the Michel decay results so that the highest energy positrons are emitted preferably along the muon spin. So the information of the muon spin is encoded in the energy spectrum of the positrons. I have a little sketch how this looks like. So here on the left side, I show you the energy spectrum of the positrons as a function of the spin phase with respect to the momentum here shown on the left side. On the right side, I show you the same with taking our acceptance into account. And now you see if the spin is aligned with the momentum, as in this configuration, we get more high energy positrons. And if the spin is anti-aligned with the momentum, for example, in this configuration, we get less high energy positrons. What we do then, we apply a threshold indicated with this line here, so over here, and then we count the number of positrons above this threshold and build up this histogram shown up here. I play it again. So over time, we build up this histogram, which results in these wiggle plots. And this wiggle is exactly the precession frequency of the muons. This is exactly this omega A we are trying to measure. I would like to focus a little bit more on these wiggle plots. So this is a wiggle plot from the 1.1 data set of the one of the sub data sets. So this is a real wiggle plot. And here it's plotted modulo 102.5 microseconds so that it actually fits onto one canvas. If we would do just the most naive fit we can do, which consists of a decay from the lifetime of the boosted muons, and then nothing else than the oscillations from the omega I, from the precession frequency of the spins, we end up with the residuals shown here in red in frequency space. So in reality, we end up doing a 22 parameter fit. And if we do this, we end up with the black line here for residual. So essentially, we end up residual free. And there's one kind of comment I would like to make. It is kind of for the nominator. We have these corrections. So I already mentioned the E-field correction and the pitch correction shown up here. We have two more, which is the muon loss correction, and we have a phase acceptance corrections. What I would like to show you is just the main ingredients for these corrections. And just in general, whenever we have early to late effects, and this basically means that this somehow constant phase we have here in the formula becomes a function of time. This requires additional corrections, or this requires that we have additional corrections. So what I show you here are the ingredients I already mentioned. These are both kind of a function of decay position in our experiment. So the first one is the detected phase, and here you see that the detected phase is a function of the decay vertex in space, basically. Then the second one, that's the relative acceptance of our calorimeters, and these two together are the main ingredients for these corrections. So in order to be able to evaluate these beam dynamic corrections and also to be able to fold or to weight the magnetic field measurements with the muon distribution, we need to measure the muon distributions, and we do this with 2 tracker stations. We have a tracker station located here in the ring, and we have another tracker station located here in the ring. These are straw trackers. That's how they look like, and they work pretty similar as the calorimeters they do. We don't directly measure the muons. We measure the decay positrons and then reconstruct the decay vertex, shown kind of here. I have a little movie how this looks like. So this on the left side, I can play it. This shows the reconstructed decay vertex as a function of time. And you can observe 2 parts. First of all, the beam is moving in and out. And then in addition, it's breathing over time. Just let it play a little bit because it's a really nice movie. Yeah, so with this, we have all the ingredients that are needed for the nominator for the measurements of the precession frequency of the muons. With this, I would like to come to the denominator, the measurement of the magnetic field. As I mentioned before, we do this with nuclear magnetic resonances. We have these NMR probes as they look like shown here. We have an active sample in the center, which consists of petroleum jelly. And how does this work? We have this active sample. We apply a pi-half pulse to flip the spins. The spins start to precess in a strong magnetic field. And then this precession of the spins induces a signal, which is the free induced decay, the FID, which you pick up and digitize. And that's what we measure here on the right side. Since we are using petroleum jelly and our probes also have additional material effects, we don't measure exactly directly the absolute value for the magnetic field. So we need an absolute calibration, and we do this with a dedicated calibration probe that's shown here. This dedicated calibration probe is water-based, and it's designed in such a way that it minimizes all perturbations, and all corrections we still have to apply are really well understood and we can calculate and test. These probes, it's in situ, it's on a 3D arm, and we can kind of do in situ calibration of the measurements I'll show you afterwards. So how does this measurement of the magnetic field actually work? It has 2 parts. The first one is here shown on the left side, which is basically a field mapping of the magnetic field in the region where the muons also live, in the storage volume. It's what we call a trolley. That's the device seen from the side. So this is a trolley from the side. Then this is for a view from the front, where the front or end cap is removed, and you see it has 17 of these NMR probes. And this trolley is deployed roughly every 3 days, and it's pulled around the ring, and it maps the magnetic field kind of in slices as indicated here. We can not always do this because during the time there's a trolley or this field mapper is inside the ring, we cannot store muons because it blocks the path. So we have a mechanism to retract it to let the muons actually pass by. During the times this field mapper is not inside the ring, we have a second system, which is shown here on the right side. We have roughly 400 fixed installed NMR probes. These are outside of the storage volume, and they are also outside of the vacuum chamber. So they are located below here and above the vacuum chambers. They are segmented into 72 positions. So they have basically one position roughly every 5 degrees in the ring. How does this look data-wise? So here on the left side, I show you one of these field maps from this trolley. So I show you the relative field measured in units of parts per million on the y-axis as a function of azimuth around the ring. So this is one of these field maps we get roughly every 3 days. In between, we use these fixed probes to interpolate or to track the field. And for one location in the ring that's shown here on the right side. So we have one value from a field mapping device inside here, shown in green. And then roughly 3 days later, over here, we get another measurement from this field mapper. In between, we use these fixed installed NMR probes to track the field, and that's indicated here with this orange curve over here. Then you see if we just do this, we end up with a little offset between where we think we should be and where actually the measurement is. So in reality, we go from both sides, we interpolate between these 2 measurements, and we use these offsets for an estimate for our uncertainty of this tracking with a random walk model. Okay, with this, we have all the parts together. What I would like to do now is show you the experiment from the inside. So what I'm going to show you is a special one. We mounted a camera on top of this trolley that goes around the ring. So you're going to see the experiment exactly the same way as the muons see the experiment. I play it now. So typically it takes a little bit more than 1 hour for this field mapper to go around. So you're going to see the speed up for this movie here on the left side, that we don't spend the full day looking at our experiment. We start at the same location as also the muons start. So on the left side, this is the wall of the inflector. So that's the region where the muons actually enter our ring. Then the first thing you're going to see here is the electrostatic catapult plates, the ESQ plates. These are for vertical focusing. Now we are approaching roughly 90 degrees from the injection point where our kicker is located. So these are the kicker plates on the left and right sides. This is to tear the muons onto orbit. We have 3 of them. That's the second one, and we have a third one. There's more electrostatic catapult plates. Coming up on the right side now is this mechanism we call a trolley garage. This is this mechanism that allows us to retract the trolley, get it out of the muon's path. Afterwards, again on the right side, you're going to see this NMR absolute calibration probe mounted on a 3D stage in situ. Yeah, so this can be moved inside the storage volume, and then this field mapper can be calibrated in situ with it. What I have not yet mentioned is what comes up. We have collimator systems, which are typically where we use to collimate the beam. You're going to see it in just a few seconds. So during we are storing muons, these collimators are inserted in kind of this configuration, but we need to retract them for this field mapper to be able to pass by. So the next thing you're going to see is on the right side. This is the one of the straw tracker stations. That's the second one. There's more electrostatic catapult plates. And with this, we are basically once around the ring, and we are back to where we started our little journey. Okay, with this, I would like to kind of recap where we are and come back to our master formula. So we have the measurement of the precession frequency, which I showed you with these wiggle plots. Then we have a beam dynamic corrections, which I mainly showed you that we have these tracker stations, how it looks like to extract beam dynamics input to calculate these corrections. Then in the denominator, we have the measurement of the magnetic field. I showed you how we measure it, and we track it over time. We also need the tracker input here to weight the magnetic field, the measure magnetic field with the actual muon distribution. We have this absolute calibration probe here to actually be able to express these terms in precession frequency of protons. Sorry. And we also have correction terms in the magnetic field measurements, which I have not yet mentioned. So these are corrections due to fast transient magnetic fields. We have 2 of them. The first one is BK. These are transient fields due to eddy currents caused by the kickers. And then we have BQ. These are transient fields, fast transient fields induced by oscillations of the quadrupole plates that induce a magnetic field. If you're interested,
4 minutes, Simon.
Thanks. If you're interested in more details, I recommend the recordings from Matteo, from Alessandra, and Alec about the corresponding topics kind of listed here. Much more details. Okay, with this, I think we are basically ready to come to an unblinding and to the overview of our result. So the run 1 data set was segmented or was grouped into 4 subruns, and these are, well, it's 1 to D, and these are the subruns, as you see here. These are basically the results of only the frac of the ratio. Before I show you the unblinding, I would like to mention or talk a little bit about the uncertainties and corrections. So you see so in this plot, sorry, the uncertainties are shown in blue, and the size of the correction are shown in orange. You see the overall uncertainty here, that's a little larger than 420 ppb. And it's completely dominated by the statistics of this omega A measurement. These are the wiggle plots. And you see the corrections have a considerable size, but the uncertainties of the corrections, they are also, all the systematics are considerably smaller than the statistics shown up here. Just as a reminder, our ultimate goal is to measure a mu on a 140 ppb level. This means we had for statistical uncertainty of 100 ppb and 70 ppb in both parts of the fraction, so in omega A and omega P measurements as shown here. Okay, with this, I think we are ready that I show you the unblinding. And before I do this, just a few words about it. So the full analysis of the full DAQ in G-2 is blinded. And we do this by actually blinding the reference clock of the digitizers that are used for the omega A plots. The blinding is performed by 2 persons that are not part of our collaboration, and this unblinding value is only revealed after the analysis is completely done, and that's what I'm going to show you, kind of the unblinding ceremony. You're going to see kind of envelopes with 2 numbers of it. The first one is delta, and the second one is epsilon here, where this epsilon is the important one because that's from the digitizer. Afterwards, you're going to see that this number is entered into a form, and then the result immediately pops out. And with this, I think we are ready for the unblinding. This happened on February 25th this year.
Put it up on the screen. Put it in the chat. Wait, 399.
So that's the important number.
7844.
envelope from the second blinder.
7, 8. Same number. Yay. Yep. The same number.
And this is what we get.
So you see these numbers entered here, and then this plot I basically started with immediately shows up. Yeah, with this, we are basically back where we started our little journey. So the first result of the Fermilab G-2 experiment is shown here in red. Well, the part up to this first bar here is a statistical contribution, and the full bar is statistical and systematics together. You see that our result is in very good agreement with the predecessor experiment at Brookhaven, and the new experimental average is now in a 4.2 sigma tension with the prediction from the standard model. With this, what to expect next? So after run 1, we have already been taking data for 3 more years. Currently, we are right in the transition between run 4 and run 5, and we expect to have at least a run 5 and a run 6. As overall, this run 1 publication, we expect that this is only going to be roughly 6% of the full size of the expected data sets of all runs together. And as a reminder, our TDR goal is to measure a mu on 140 ppb level. But just in general, I think it's really exciting times. There's much more data to come, and then also the theory side is very, very active. For example, there were new lattice results published, and there's much more to come. These are results that will be really scrutinized in the coming months and years. With this, I would like to close with a picture of the collaboration. That's a picture taken at the unblinding ceremony. So this is how an unblinding ceremony looks like in times of COVID.
All right, thank you, Simon. So any questions from, maybe let's start in Zoom. Any online questions? I cannot see that, so if somebody's raising their hand. If not, from the room, maybe? Yeah. Go ahead.
So I think this is a fantastic experiment, a beautiful result. This is Alain Blondel. The work together with the theorists is absolutely remarkable because they produced a paper before giving the answer before the experiment did. Now that's a double blinding in a way. Now, are you still accepting new theoretical calculations after this, or is there a new theoretical unblinding which will take place later?
I mean, in a sense, our experimental work is completely independent of the theory, right? So we measure and publish. So in a sense, we are not really, from the experimental side, we are not really involved. But the theory initiative is still working on it, and there will be, there are more results to come. And
no, but when they published the result before knowing your answer, you could say that the theory was independent of the experiment. But now that they know the experimental result, is that still true?
Well, I guess that's more a question for theory colleagues. Right, from the theory side, we are really, the experiment is really independent in a sense, right? Because there's no input from the theory.
Okay, I'm asking this because we are setting up to do extremely precise measurements with the FCC, and we may have the similar problems.
So, yeah, one more question in the audience.
Yes, Roman Sano from Sofia. Is there any other experiment planning to measure the same in near future or distant future? Because whatever you do, the community will believe you and other experiment if the results coincide. You remember the story with the CP violation in K and the case N831 and E73-1, and then the big effort for KTEF and NA40 something. Okay, I forgot already. So is there any other experiment? And the second question I have, I will keep for the theorists. What at all that has in common with neutrinos?
So to the first question, yes, there is. There's a JPAC G-2 experiment that's planned and coming up. Yeah, so that the answer is yes. And the experiment works quite differently. So it's a completely different scheme. So they don't run at a magic momentum. They basically run an electric field free. So it's an additional experiment with completely different systematics in a sense coming up.
Yeah, I think on the second question, we'll have a theory talk, which maybe will try to answer this in a few minutes. We have time for one more question, if there's one. No, otherwise we thank Simon again, and we move on to, yeah, I think this is deserved. And we move on with Sasha Davidson with her theory talk. So are you there? I think you're online. Yes, we can see your screen. No audio yet.
So can you hear me?
Yes. So please go ahead.
Okay, so let me first say that this was going to be a talk about mu2e flavor changing contact interactions. So I wasn't originally planning to say anything on G-2, but I can make a flippant theorist's comment on the question about relating G-2 to neutrinos, which is if I wanted to build a model that explained both something related to neutrinos and G-2, I would probably put some lightish new physics that could mediate non-standard interactions and G-2. Okay, but that's my sort of silly theorist's reply. Let me go on with my talk. I want to talk about contact interactions that change leptons from muon flavor to electron flavor. And these are things we don't see. So I will start by reminding you about constraints on these and about the theoretical mechanism, the theoretical formulae, mechanisms, assumptions that go into doing an effective field theory analysis, which is the perspective I'm going to take in this talk. And then I will focus on charged lepton flavor violation. So mu2e processes like mu2e gamma, mu2e, and mu-e conversion. And if I have time at the end, I want to also mention some work we did for mu2e flavor changing NSI. So here is a list of charged lepton flavor changing processes and some current experimental constraints. So at the top here in black are mu2e flavor changing processes. And you see that the branching ratios, the upper bounds on the branching ratios are of order 10 to the minus 12, which is restrictive because this is compared to a weak decay. And for taus, the limits are less stringent, more like 10 to the minus 8 at the moment because it's more difficult to make a beam with taus. And there are a few constraints on heavy decays from the LHC as well. Now, for most of these decays, they're occurring at low energy. And at low energy, the relevant gauge symmetries are QED and QCD. And it's a renormalizable theory. In that renormalizable theory, you can't write down a lepton flavor changing interaction. But of course, you can build contact interactions. And then you can, I drew a few of them here, you can put those contact interactions into the Lagrangian by building an operator, O, who is constructed by taking all the fields, who are the external legs of your process, and combining them in some Lorentz invariant way as a scalar or a vector or as you like. And so I'm going to put them in the Lagrangian as this operator who has a subscript which tells you something about the Lorentz structure. It's going to have a coefficient C who is dimensionless. And there is then some factor that has mass dimension, lambda, that sits downstairs to some power to make the dimensions work. And since I'm assuming that I have no new particles below the weak scale that have renormalizable lepton flavor violating interactions, I can build this Lagrangian and use it for the below the weak scale. So I'm going to be making two assumptions in this talk for the value of my parameter lambda here, my scale. From a lot of the time, it's going to be the Higgs Vev, because that is convenient normalization since the branching ratios are compared to weak decays. And then what the branching ratio constraints give me is a bound on the coupling constant for the contact interaction C. But at some point in the talk, I will also want to set C equal to 1 and then see how big a value of lambda the experiments are compatible with. And this is a way of comparing the reach of experiments. Okay, so since I need operators, here is a list of them. I don't want you to look at it. All I want you to notice is that there are about 90 of them. And all I've written down here are contact interactions where I have a muon who turned into an electron in a contact interaction with one or two other particles who themselves don't change flavor. So my 90 operators will describe mu to E gamma, mu to 3E, and mu E conversion, but not, for instance, kaon decays to mu E. For that, I would have to add even more operators. So here again are the three experimental processes I want to focus on. And I'm going to be interested in them because experiments currently under construction are hoping to improve the experimental sensitivity to these processes by 4 orders of magnitude. And so then you can ask, if you're a theorist, whether measuring 3 branching ratios is going to find mu to E lepton flavor violation if it's there, because I wrote down about 100 operators. Okay. So let me start with that question. And the answer is going to be yes, it will work. And this is because of loops. So what I drew here is some loop diagrams where I wrote my contact interaction, any of the 90 I could have had, for instance, where I have a muon and it turns into an electron, and then I had some other legs. And I can draw standard model QED or QCD one loop diagrams, where, for instance, I close 2 legs and attach a photon and different flavored fermions, or I can decorate with a gluon or a fermion, a photon. Or in the case of generating mu to E gamma, I, in a few cases, might want to draw 2 loop diagrams like these. The interest of doing this is by drawing these diagrams, I can take most of my 90 operators and turn them into one of the 4 fermion operators that directly contributes to my 3 processes that I'm interested in. And technically, theoretically, I can include this kind of diagram in my effective field theory formalism as essentially beta functions for the operator coefficients or the coupling constants of the contact interactions. So I have running couplings like in the standard model. And I wrote here an example. So for instance, if I consider mu to E gamma, for instance, that's mediated by a dipole operator, right? In other words, here I have a muon, an electron, and here I have a photon. And it has a coupling constant in front. branching ratio at the experimental scale, therefore, constrains those coupling constants of this operator. But if I include all these loop diagrams, that coupling constant now has all these corrections proportional to a variety of my 90 operators. They're tensor operators and scalar operators. And in this thing called two-loop, there are vector operators. And the net effect is that almost every one of my 90 operators is going to contribute to at least one, if not all three, of mu to E gamma, mu to 3e, and mu e conversion, suppressed by at most a factor of about 10 to the minus 3. So as long as I assume there aren't sort of accidental cancellations between these operators, if mu to E flavor change is there at low energy, we should find it in these three processes. So that's good. So now let's move on to the next question, which is, suppose you see mu to E flavor change in one or all three of these experimental searches, what do you then learn? And of course, the question you really want to answer here is, can you distinguish between models? In particular, could you learn what is the model that gives you neutrino masses by measuring these processes? And unfortunately, I don't have an answer to that because I haven't worked on that problem enough yet. So instead, I will discuss, first I want to count how many experimental constraints I have from those three processes on all my operator coefficients. And then I want to compare the complementarity and the reach of the three experiments. But let me first explain the cartoon I put on this slide, which is supposed to be some sort of a representation of how I imagine effective field theory to work. So on the vertical axis of my slide is energy scale or inverse distance scale in some sense. So I'm assuming that my new physics model that would generate neutrino masses and or charged lepton flavor violation is a model with heavy new particles. So it lives at the top of the slide, up here at the top of the mountain in the clouds. And me and most of the rare decay data, we live at the bottom of the slide. And what we, of course, we want to do is relate the models to the data. And one way to do that would be to take your model parameters and compute the amplitude for the various experimental observables. When you do that calculation in a model, you usually assume that between the new physics scale where your model is and the experiment, there's no other relevant new physics. Now, if that assumption is valid, then I can do in effective field theory the calculation the other way around. So if there's nothing between me and the data at the bottom of the mountain and the model at the top, I can take the experimental constraints and climb the mountain with them, peeling the loops, the loops off the experimental data, because the loops are generated only by standard model particles, because they're the only dynamical particles in this range by assumption. And then I can take, in effective field theory, the data up the mountain to the model. So that's what I now want to do. Okay, but first I want to count how many constraints I have from my three processes on those 90 or however many they were operator coefficients. So here is a branching ratio for mu to E gamma. In some normalization for my operator coefficients, this is the normalization where I took lambda to be the Higgs Vev. And you get two constraints on the coefficients of the two dipole operators. And the point here is that of course, the electron in this decay is relativistic, so it comes out with fixed helicity, and the electron with left-handed helicity and right-handed helicity essentially don't interfere because the interference is suppressed by the electron mass, and that's a very small parameter. So that's why you get two independent constraints on the two operator coefficients. Then for mu to 3e, you have various 4 fermion operators. So this is a scalar 4 fermion operator, and this is vectors with different chirality for the electrons. And again, it's like mu to e gamma, because the electrons are relativistic, the amplitudes with electrons of different helicities don't interfere, and one bound on the branching ratio of mu to 3e gives you a constraint on the 6 4 fermion operators who contribute to mu to 3e. Now, you notice that the dipole is going to contribute to mu to 3e as well, because you can have mu goes to e gamma, and then the gamma turns into e plus e minus. So the dipole interferes with some of the 4 fermion operators, and it also contributes squared on its own. So anyway, now I've got 6 more constraints from mu to 3e, and I come to mu-e conversion on nuclei, which resembles a little bit WIMP scattering on nuclei, in the sense that there is a spin-independent part of the amplitude, which is coherent on the nucleus, and therefore picks up an approximately an z squared or an a squared enhancement with respect to the spin-dependent amplitude. And so I'm going to forget about the spin-dependent mu-e conversion in this talk and just focus on the spin-independent. And since the spin-independent is coherent, all the operators who can contribute sum at the amplitude level. So you have vector operators on protons and on neutrons, and scalar operators on protons and neutrons, as well as the dipole operator, because you can interact with the electromagnetic field at the nucleus. And they all add at the level of the amplitude, and they're weighted by these weird factors S and V, who depend on both the nucleus and whether it's a neutron and a proton. And these depend on the wave function of the muon in the nucleus and on the distributions of the nuclei. So it's target dependent. Now there are spin-independent bounds on gold and titanium, which gives you at least 2 more constraints. And again, each time you can have an outgoing electron who is either left-handed or right-handed, so each target gives you 2 constraints. So I end up with, from gold and titanium, 4 more bounds on my operator coefficients. So that tells me that I can constrain a 12-dimensional subspace of my 90-dimensional operator space that I started with. And since the electron coming out of the vertex with the muon can be either left-handed or right-handed, and the 2 cases don't interfere, I'm going to focus on half of that 12-dimensional subspace, so only 6 dimensions. And this is because the other handed electron is essentially a mirror image. And I want to think about what I can learn from this from knowing the coefficients in this 6-dimensional subspace. So what it's telling me is I have a Lagrangian at the experimental scale with 6 operators, and I can learn the coefficients. And then I know that the renormalization group equations allow me to take these coefficients and climb up the mountain with them. So if I write those solution of those renormalization group equations as a matrix, who is here written as G, I can identify the combination of coefficients that correspond to each one of these at the new physics scale. So I still, at the new physics scale, will have a 6-dimensional subspace that I'm interested in. So let me skip details. In that 6-dimensional subspace at the experimental scale, I can ask if my observables are complementary. Are they telling me different things about my new physics models? And that's what these plots are supposed to represent. So to understand how I made them, first you have to restrict to a 3-dimensional subspace of my 6 dimensions, because in 3 dimensions we can visualize. And my 3-dimensional subspace is here. The vertical axis is mu to E gamma. And the horizontal plane here is going to be mu to 3e and mu E conversion. And I'm going to fix the angle phi to 45 degrees. So I've set equal amplitudes for mu E conversion and mu to 3e. Okay. And then what I'm plotting on the horizontal axis of my plots is the angle theta. Now, if I was still using the parameterization in terms of operator coefficients, my experimental bounds would give me an allowed ellipse around the origin. But now I've traded my coefficient, I've set my coefficient to 1, and instead I'm plotting reach in new physics scale on the horizontal axis. So now instead the allowed space is at high lambdas, and what I exclude is low energy. And so we first look at the left plot. Mu to E gamma is in black. And so it's of course maximal at theta is 0 and pi, because that's on the z-axis here. And it's going to vanish when I am exactly in this plane. You notice that neither mu E conversion nor mu to 3e are going to vanish when I only have the dipole, because the dipole operator contributes to all 3 processes, right? And you see here that mu to 3e, it went down a little bit when the dipole vanished, but because the 4 fermion operators are all there, it never goes to 0.
So 5 more minutes, Sasha.
Yes, okay.
Let's go ahead.
Mu E conversion, on the other hand, does vanish for a particular value of the dipole coefficient, where it exactly cancels the sum of 4 fermion operators that was giving mu E conversion. Now, the plot on the right is actually exactly the same plot as the one on the left. It's just that we are plotting the horizontal, this angle theta differently. So we're plotting it in terms of the tangent of the angle. Anyway, okay, so I have a few minutes to tell you about NSI. So let me just summarize it. So now we're changing gears, okay? I'm sure you all know who non-standard neutrino interactions are. I'm going to focus on a very particular subset of them, okay? I'm interested in neutral current NSI, so these are the ones that contribute to the matter effect in neutrino oscillations. And I'm going to be interested in the ones where the neutrinos change flavor. And I remind you that puts they're sitting in a 4 fermion operator, these 2 neutrinos of different flavor, with 2 first-generation fermions who are either going to be electrons up quarks or down quarks. Now, the somehow puzzling thing about NSI is they need to be the coefficient of here of this operator. This is like the C I had from my lepton flavor violating things. It has to be relatively large for NSI to be observed, but lepton, if in the case of charged leptons who are sitting in a SU2 doublet with those left-handed active neutrinos, charged lepton flavor violation tells you that for instance, mu to E flavor change, the equivalent of this epsilon has to be smaller than 10 to the minus 6. And so how, the question for a theorist like me is, how do you make these two things compatible? Now, it's well known that you can build models for non-standard interactions with either heavy nu particles or light nu particles, such that you generate big enough NSI and you manage to make all the tree level lepton flavor violation, charged lepton flavor violating amplitudes vanish. And the question, though, is I just told you that loops are important for charged lepton flavor violation. What you might wonder is whether loops generate charged lepton flavor violation from the operator combinations that were giving you NSI. And that's what we set out to calculate in effective field theory in the particular case of NSI models where the mediating particles are heavy. Okay. And so let me skip straight to the summary, and we can start with the NSI part of the summary, which is down here. And what we found in our calculation is that you always regenerate from your NSI operators charged lepton flavor violating operators at 2 loop, and in most cases, you got them at 1 loop. Now, for flavor changing NSI involving a tau neutrino, this is not a problem. However, if you were changing your neutrino flavor between a muon neutrino and electron neutrino, it is hard to put an value of epsilon for NSI that is bigger than 10 to the minus 3 without it generating at 2 loops charged lepton flavor violation that is larger than current constraints. Now, this is, however, is not a showstopper because it only applies in the case where your NSI are generated by heavy nu physics. And even in that case, if you really want to make it work, you can ask some tooth fairies to come and help you and arrange for some special extra cancellations, and you will get rid of this lepton flavor violation. Okay, let me now come to the summary of the first part of the talk. We know that lepton flavor change in the charged leptons has to happen because the neutrino mass matrix and mixing angles we see tells us so. And it would be nice to see it because it would hopefully tell us something about the neutrino mass mechanism and other new physics in the lepton sector. Now, the current experimental bounds on mu to E are restrictive. They probe new physics scales up to 10 to the 100 to 1,000 TeV. And the expected sensitivity of the experiments under construction is hoped to be 4 orders of magnitude better than this. So this is an exceptional improvement. Now, there are only 3 experiments, but the loop corrections tell you that almost any operator that you can write down that changes lepton flavor from mu to E will generate these experimental processes at 1 loop. So it's probable that if mu to E flavor change is there, we should see it. Thank you very much.
Thank you, Sasa, for this nice overview talk. Any questions from either Zoom or the audience? Please in Zoom raise your hand or maybe speak up, or from the room.
It's Friday afternoon.
Yeah. Yeah, I'm sorry you had to skip a few slides, but I want to remind everyone that I also have a Slack channel. So if you want to ask questions more on the neutrino part in detail, we can go there. Yeah, if there are no questions, then I propose we move on. Because we're still right in time to go to the charge lepton flavor violation experimental overview. So Gavin will show us how we can actually access all these coupling constants and measure something. So hi, Gavin.
Hi, I hope you can hear me okay.
We can hear you okay. So please go ahead.
Yeah, sure, great. So yeah, thanks a lot to the organisers for the invitation. Sorry I can't be there. I'm sure it's a beautiful location. But yeah, I'm going to give a run through of the muon experiments that are currently in construction and will be coming online in the coming years. I hadn't really started with the intention of this being a kind of recap talk, but there have been many excellent talks on this subject throughout the week. So inevitably, it is a bit of a review of some of those. But I guess what I can do in this talk is draw out some of the similarities and differences and complementarities between the different experiments. But for more information, yeah, I'll try and highlight the talks that I'm drawing information from throughout the week. So if you want to know more, please do go and look at the other slides. Okay, so as a very general motivation, we are of course in this position where at the energy frontier, the LHC, there's been no direct observation of new physics. But there are questions around neutrino mass generation mechanism, and we are accumulating a series of more or less significant tensions in various measurements related to the neutrino sector. So this plot is maintained by Patrick Koppenberg of LHCb, showing the pool of various measurements here. And the single most significant one of these at the moment is the muon G-2, which we heard about earlier in the session. So, whether or not there is any BSM physics going on in all of this, charge lepton flavor violation is really a complementary tool to probe the lepton sector. And what makes it particularly interesting from an experimental point of view at the moment is that, so the plot on the right here shows the history of the limits on charge lepton flavor violation, going all the way back to the 1940s. And you can see in the coming decade, we're going to have this real changing gradient on this plot. And there's going to be a huge jump in sensitivity with the new experiments that are coming online. As was said in the previous talk, about a 10 to the 4 jump in sensitivity, which makes this particularly compelling at the moment. It's interesting, I mean, as you can see that people have been studying charge lepton flavor violation going all the way back to pre-standard model days, and so it's interesting to look back a little bit to the kind of questions that have been asked and how charge lepton flavor violation was, or non-violation was instrumental in developing the standard model. So for example, in 1947, Pontecorvo was wondering about whether the mu, or meson as it was at the time, could decay. Basically, is it some kind of excited electron that could decay by photon emission? Proposing some experiments related to that. Moving forward into the late 50s, Weinberg and Weinberg here were wondering, could the muon possibly decay via emitting a charged boson in a process like this? And probably not, because you could simply join these neutrino lines and have a decay like this, which again, we know doesn't happen. But that was resolved, of course, with the discovery of neutrino flavors, with the discovery of the muon neutrino just 3 years later. This diagram on the right here, of course, is actually possible now that we know about neutrino oscillations. So you can have a process like this in the standard model. but given the masses of the particles involved, this is suppressed to basically unobservable level. Whether this is suppressed to 10 to the minus 50 or 10 to the minus 54 is kind of beside the point. I mean, it's unobservably small. However, we know then that number is not conserved in the Standard model. There must be no underlying symmetry protecting it, and it's a very common feature in BSM models, and indeed Sasha was just saying it has to happen. There's many BSM models which include charge lepton flavor violation if you want some concrete models that do such a thing. You can also connect it to a big question, if you like, in that it could be related to leptogenesis of the matter-antimatter asymmetry of the universe and the generation of neutrino masses. And however it occurs in some BSM theory, the general idea is that you can either have some new loop process, some new particles going on in this loop, or some other mediator for this process. And this could boost the charge lepton flavor violating process to an observable level, hopefully. Or flip that around, and pushing the limits on this process then sets very strict constraints on BSM theories. So yeah, we have the three kind of golden channels that we study, and here they are. So mu to e gamma. The current limit on this comes from the MEG experiment at PSI. It's at 4.2 times 10 to the minus 13 branching ratio. The aim for this is about a factor of 10 improvement with the MEG2 experiment. And the mu3e process, the current limit is 10 to the minus 12 from syndrome, and then this is one of the big jumps, aiming at 10 to the 4 jump in sensitivity with mu3e, phase 2. And then what's called muon conversion, so it's muon to electron in the field of a nucleus. The current limit here is 10 to the minus 13. And again, this is there's 3 experiments targeting a big jump in sensitivity here. Rather than going through what all of these limits mean on individual BSM theories, I'll take an effective Lagrangian, not the one that Sashi was just talking about, but hopefully there are enough similarities. So here I'm just talking about two kind of processes here, but as Sasha was saying, through loop effects, they can both contribute to all possible decays. But here on the basic level, we've got a photonic type process and then a 4 fermion kind of point contact type interaction here. We've got the scale, the lambda for the new physics on the bottom, and then this kappa parameter, which I believe is the same as the kappa parameter that Sasha was just showing. And that controls basically which of these processes is dominating. And so on my plot, I'm showing a narrower range of kappa than Sasha was showing. But for a contact interaction which prefers leptons over here, and then a photonic type interaction over here, these are the limits currently excluded in yellow. And then the dashed lines show where we're going to be with the current experiments under construction. So here's this big jump in sensitivity. If you look at a contact interaction which prefers quarks, then it's the conversion type experiments, and the current exclusion is a bit higher, but then again, the conversion experiments are going to push this very significantly. So yeah, I mean, just to say it in a very simplified way, what Sasha was just saying, there is complementary information in the 3 different channels. Observation or non-observation of a signal in any one of these does not tell you which type of BSM theory exists, but it does give you constraints, and there is complementary information, and you can extract information from the ratio of limits in the different channels, for example, to place constraints on possible BSM theories. Okay, so onto the experiments themselves. I'll start with some general statements about the experimental challenges. So splitting these into muon decay and conversion. So the decay experiments, these are really coincidence experiments. You're looking for 2 or 3 final state particles. This means combinatoric backgrounds are important. And so the way to deal with this is to minimize the instantaneous rate of muons, but still maximize the total number of muons you see. So a continuous muon beam is the preferred mode here. For muon conversion, your final state is 1 particle, just the electron. And there are 2 types of backgrounds. Some of them are associated with the beam and that they're very prompt, whereas the signal is quite delayed. So you want a very pulsed beam so the beam associated backgrounds die away, and then you have a high extinction factor with it, so you get a very clean window to look for your signal. And I'll come back to this later. All the experiments are basically endpoint type searches. The signal would sit at the kinematic limit of the equivalent standard model decay with neutrinos, where the neutrinos effectively carry away no energy. So resolution is critical, and it's resolution on low energy particles, so electrons of 100 or 50 MeV or less, while dealing with very high rates, 10 to the 7 or 10 to the 11 millions per second. So that's the general kind of experimental challenge. I'll now briefly go through the experiments. So starting with MEG, so this is the search for mu to E gamma. So the current limit is from, well, MEG, which run up to 2013, looked at a total of 7.5 times 10 to the 14 muon stops, and here's the limit they extracted, and yeah, this is the best limit in this channel to date. The signal is really a back-to-back electron and photon, each carrying half the muon mass in energy. And the background's, well, that there is a radiative Michel decay, so you can have a photon radiated off the electron muon line. Or a combinatoric background where you have two Michel decays and then a photon from Bremsstrahl or some equivalent process. This is a plot showing you how they contribute. So this is the data points, and then the combinatoric background is the pink line, and the radiative Michel is the dashed red line. And the green is a signal at the exclusion limit blown up by a factor of 100 to make it visible, to show you where the signal would sit at the kind of endpoint for this spectrum here. So MEG2, which is currently in an engineering run, so it's basically a factor of 2 everywhere in terms of resolutions and also beam intensity. So this is a kind of sketch of the detector. The beam line comes in, and then there's a stopping target. There's a liquid xenon calorimeter to capture the photons. And here's a cartoon showing, well, not a cartoon, but a kind of display showing the improvement in resolution from MEG going to MEG2. Then there is the tracking system for the electrons. Again, material budgets are really critical for these low energy electrons. So here it's a cylindrical drift chamber. And to get the coincidence in timing between the photon and the electron, there's a pixelated timing counter outside that. And then there's a radiated decay counter for kind of upstream or downstream, sorry, to capture electrons that don't hit the tracker. So yeah, here's some numbers on the resolution. You can see the resolution significantly improve for the upgraded detector. So yeah, here's the status. They had a pre-engineering run in 2020. There was a couple of issues discovered. Those are mostly understood now. And they're currently in a full engineering run with the full detector and the upgraded TDAC. And with physics data expected at the end of this run. So with 3 years of data taking, they should reach their expected sensitivity, which is a factor of 10 improvement. Most of the experiments are also looking for other things you can do with these really high precision detectors and large data sets. And with MEG, it's a look for this atomic X17 particle. Here they would use a proton beam, which is also used for their calorimeter calibration. So it's an interesting spin-off. And there's more in Manuel's talk on Tuesday on that. Okay, on to the other decay experiment, mu3e. This is also at PSI, and it actually shares the pi5 beamline. So this is the pi5 beamline, and normally it carries on through this wall to MEG, but there's a new branch which takes some of the beam round to the mu3e experiment, which sits here. The signal here is 2 positrons and an electron, and the background is, again, it's radiated Michel decay with the photon now giving you E plus E minus. But still with the 2 neutrinos, or combinatorics where this electron can come from bar-bar scattering or something similar. So the handles you have are the kinematics, well, the coincidence in time, and also the fact that the momenta should sum to 0, and the energy of the electrons should sum to the mass. And it's a kind of, again, it's like sitting at the end point of the Michel decay, and the combinatoric background is where the signal would be. But yeah, it's all about timing, momentum, and vertex resolution on these low energy electrons. And the way this is done is with a extremely low material tracker. It's 4 layers of these HV monolithic pixel sensors. Andre gave a nice talk on this technology earlier in the week. So I'm not going to say much about it, but it's 80 by 80 micron pixels on a 2 by 2 centimeter sensor, which can be then thinned to 50 microns, giving you the low material needed. The important thing here is that the electrons and positrons recurl in the field, so you can catch them again on the way back in, which gives you the long lever arm to improve the momentum resolution. And then there's timing information from scintillating fibers and then thicker tiles out in the recurl stations. Okay, one of the other things you can do that's fairly unique to mu3E is also a dielectron search. So searching for things like dark photons, axion-like particles, or even this could be a long-lived particle in here. So that's one of the nice spin-offs from mu3E, as well as the core kind of 3-electron search. The status of the experiment, well, we had a, I say we because I'm involved in mu3E. We had an integration run earlier this year where the magnet and beamline were commissioned, and we took data with 2 layers of pixels and the scintillating fibers. So we're analyzing that data now. The plan is an engineering run in 23 and then physics in 2024. And that would take us to a branching ratio limit of 10 to the minus 15. Then there is plans for phase 2. This would use the high intensity muon beamline at PSI, which Andrea spoke about earlier in the week. This is a factor of 10 increase in the number of muons per second. There's possibly detector upgrades needed to deal with that rate, but that would take us to the final target sensitivity on this process. And this is just a photo from the integration run showing you the detector in the cage being loaded into the solenoid magnet there. Okay, so onto the conversion experiments. So yeah, here the experimental challenge is quite different. So it's in principle, it's a similar idea. You stop muons on a target. Aluminium is a good choice for a target for these experiments. The muons get captured, and then you're looking for the neutrino-less decay. And that means essentially all of the muon's energy, less some binding energy, goes into the electron. So it's a monoenergetic electron. It's almost the muon mass is the signal. But the backgrounds are very different. So there is a very significant backgrounds associated with the beam itself. So you can have pions, muon decays in flights, and radiated captures and so on. So if you have a pulse of protons on the production target, you then get this kind of beam splash, which follows shortly afterwards, which are these beam backgrounds. So this is where the pulsed beam structure becomes very important, because then after these prompt backgrounds have died away, you can have a nice clean window to look for your signal. So getting a very high extinction factor, giving you this clean signal window is really crucial. The remaining background is then decay in orbit. So it's a standard Michel decay with neutrinos here. So this is the electron energy from the decay in orbit. And again, the signal would sit way out on this endpoint, which looks lovely and clean on this plot. But if you zoom in to the level of sensitivity that's needed, well, yeah, there is still quite a significant tail of this decay in orbit all the way out to the endpoint here. Okay, so onto the experiments themselves. I'll start with Comet at JParks. This is they're going for a 2-phased approach here. And this is the phase 1 experiment here. So the proton beam comes in here, and there's the production target. You capture the pions, which decay to muons, and then the muons get stopped around here. Surrounding the stopping target is again, it's a low material tracking system. This drift chamber here. And then downstream again of the production target, they've got this straw tracker and ecal system, which in phase 1 is used to measure the beam and normalize everything. So the status of the phase 1 Comet is that the beamline is expected to be completed in 23, and then physics should follow the year after. And they reached the phase 1 target sensitivity with less than half a year of running. The aim is then to go for phase 2, and the way you improve the sensitivity is to increase the proton beam intensity to get more muons, and also to drive down the beam backgrounds by adding an additional turn in these transport solenoids. So more time for the pions to decay, and also select out the muons before you reach the stopping target around here. For Comet phase 2, they then also have, after the target on which the muons decay, there's then also an electron spectrometer to get rid of all the neutrals and also only select the higher energy electrons before you come around to the actual detector, which is a kind of upgrade of the straw ecal system from phase 1. And yeah, this has to be upgraded to get the resolutions needed to push on to the sensitivity that's required. And then, this would then be, I guess, the single tightest limit on this process from Comet phase 2. Mu2e at Fermilab, they don't have a phased approach. They're going from the beginning for a 2-turn transport solenoid system, which again drives down the beam backgrounds from the beginning. But other than that, you'll see there's a lot of similarities between the experiments. Pulse proton beam comes in, you have a production target here, you capture the pions, they decay, and then you stop the muons on a stopping target here. And then downstream of that, there's a tracker. Again, it has to be low material tracker, so it's a straw tracker. And it has a wide bore in the center. And this is so that most of the positrons from the decay in orbit don't even reach the tracker, so this greatly reduces the occupancy. And then some calorimeters downstream from that as well. The status for Mu2e, well, the beam is basically complete. It's part of the muon campus at Fermilab, which is currently devoted to muon G-2 primarily. And the production is ongoing. So here's one of the transport solenoids at Fermilab. Here's one of the planes of the tracking system, the straw tracker there. So the planned beam on target 2024. There was a talk on the Fermilab muon campus earlier in the week as well. And then data the year after. With this initial run 1 should reach a limit of 10 to the minus 16. They then have to shut down for the PIP2 installation at Fermilab and then resume when the beam comes back in 2029, going on to their target sensitivity of 8 times 10 to the minus 17, so comparable to Comet phase 2. They're also looking into the possibility of a mu- to E+ conversion search. So this is Majorana neutrino type search. So it's the neutrino-less double beta decay type diagram where you just flip the muon, this electron leg around and turn it into a muon. And already with the run 1 data, they should be able to set a very impressive limit on this process. Finally, there's the DEMI experiment at JPark, which is a somewhat simpler idea. It's the same basic concept though. But they take everything apart from the detector of say Mu2e or Comet, and you do it in one place. So the production, pion decay, muon capture all happens in the production target here, and then you just collect the electrons that come off from the muon decay, select out the high energy ones, and then have your detectors here. So yeah, it's a much simpler experiment. It would have obviously then different systematics, but ultimately isn't going to reach the same level of sensitivity as the full Comet or Mu2e. But they had an integration run in 2019. They've been waiting for the H line at JPark, which should be ready next year, and data should follow. And here's some example limits based on 1 year running. There's an idea of doing a longer run, which should take them up to sensitivities comparable to Comet phase 1. Okay, then looking further ahead, there's an idea to upgrade Mu2e to Mu2e2. The idea here is to really make full use of the PIP2 beam at Fermilab. So you can get a 3 times increase in the beam intensity, and also increase the lifetime of the experiment. So effectively collect a lot more data over a much shorter time, and gain about a factor of 10 in sensitivity on the branching ratio. This comes with challenges, so it would require a new production target, and the favorite design at the moment is this quite interesting conveyor belt of circular targets. This has to keep moving to give you the cooling needed. But there's also the opportunity, so if a signal is observed, you could then swap in different stopping targets for the muons. And the reason for doing this is that depending on the type of operator that you have causing this charged lepton flavor violation, you would see different behavior based on the Z of your target. So looking at different targets, it then becomes interesting. But it requires new solenoid and new detectors. To give you an idea, this is the endpoint of the decay in orbit spectrum, and a possible signal here. If you boost up the muon rate, this would kind of completely dwarf your signal. The decay in orbit background would dwarf your signal. So you need to sharpen up the resolution to still identify this peak here. And there was a nice talk about this by Craig earlier in the week. Moving further ahead, there's been this prism idea around for a while, and this seems to be emerging as the consensus for how to push the conversion limits further. So prism is this phase rotated in tensor muons. The idea is you have a fixed field alternating gradient ring. And what this does is that if you have a bunch of muons which have a spread in energy, it effectively decelerates the high energy part and accelerates the low energy part, giving you a much narrower energy spread in the muon beam. This means that you can have, you can much more effectively stop the muons on the target, and you can also have a much thinner target, which means less energy loss by the electrons when they escape, really sharpening up the peak of any signal that would be there. So yeah, this has been around for a while. There was a proof of concept at the music facility in Osaka, and there was an idea for the prism plus prime detector at JPark, which would look like this. Some of the ideas for this detector ended up going to Comet Phase 2, such as the electron spectrometer here. But yeah, this kind of detector could give you about a factor of 100 on the Comet or mu2e conversion limits. There's also this idea for this Enigma facility at Fermilab, which could do both. So a DC beam and a pulse beam. So surface muons give you the DC beam at a very high, using the PIP2 facility would give you a very high rate of surface muons. You could push the MEG limit by a factor of 100. And then for a pulse beam, using again this prism idea to push the conversion limit even further. So these are now being picked up as part of the SNOMAS initiative. And so I've linked, there's a couple of documents here if you want to learn more about these, or there was a talk by Bertrand as well earlier in the week to get more information. Okay, so that brings me to my conclusion. So yeah, charged lepton flavor violation, it's this complementary way to get at any new physics or set stringent limits on new physics that may be happening in the lepton sector. We've got these 3 golden channels, which are all going to see a jump in sensitivity over the coming decade. So yeah, here's the limit plot again now with also including the mu2e2 line at the top here. So again, the yellow is where we currently are, and then the dashed lines are where we could be in the not too distant future. And then yeah, there's lots of ideas going around for utilizing future beam facilities to push these limits quite significantly even further. Okay, thanks. I'm happy to take any questions.
Thank you, Gavin, for this overview. Questions on charged lepton flavor violation experiments, current and future? Yes, there's one question here in the audience.
You mentioned lepton flavor violation for muons. Did you have any comment to make on the possibilities to improve the similar measurements for taus?
Yeah, I didn't really go into taus because my title was muon. But if I go back to this plot, the tau limits are on here.
Okay.
Yeah, obviously the tau experiments are much more challenging, but there are ideas for it, pushing the tau limits, though, either using beam dumps, or I believe LHCb was looking into what they could do in tau.
Right, we'll be looking for that at a future Z factory as well.
Yeah, yeah.
I believe a lot of those are from the LEP still.
I think the B factories, probably some of these are from B factories as well. But yeah.
Okay, thank you.
So more questions? If not, then let's thank Gavin again. And I've seen in the chat, I didn't read it in detail yet, but there's actually a request from the next speaker to give her talk before the coffee break. So you can maybe, so who's the, I'm not the chair of the next session. So who's the chair of the next session? Is he already here?
I'm the chair of the next session. So this is Carsten Roth, and I'm chairing the next session. And yeah, I agree. I mean, we should move actually to Carlos. So this is the so the last plenary session of today. So this is physics beyond PM and SN, and our first speaker is Carlos Arguelles. And since he has to leave soon, let's actually get started right away with him.
All right, that's that then. I'm sorry for people who are, I guess people can quickly run out and grab a cup of coffee if they really need it. So go ahead.
Thank you. I'm sorry for the inconvenience. I hope you can hear me. Yeah? Hear me fine? No? Can people hear me?
Yes, I can hear you on Zoom.
Yes, we can hear you.
Okay. I hope you can see the good screen. So I'm sorry to not be able to be there at Calgary. It looks like a wonderful place. I hope to be able to visit soon. And I thank the organizer for giving me the opportunity to talk about this very exciting topic. I hope you enjoy this talk. So this talk is going to have 3 moments. First, I'm going to tell you about why we need, why we think maybe we need more antineutrinos. And then I hope I will convince you that not only we may need more antineutrinos, but we may need something additional to more neutrinos. And then I'm going to go and tell you a story that I call here the Garden of Forking Paths, which is going to be an investigation of what may lie ahead of us. And then finally, I'm going to have a brief outlook of what awaits us. So let me tell you about the need for 3 neutrinos and more. So the light-stellar neutrino searches are motivated originally by the LSND and mini-moon experiments. First, LSND was performed in the 90s. It used a pion decay at rest beam that had a very pure nu bar beam. And it used inverse beta decay to detect electron antineutrinos. It saw an excess of electron antineutrinos that you can see in the figure on the top. And that excess has a significance of 3.8 sigma compared to the no excess hypothesis. The LSND experiment was followed up by the minimum experiment, which operated at a similar ratio of baseline to energy, so as to test the hypothesis that LSND was seeing the oscillation probability or a conversion between muon antineutrinos to electron antineutrinos. Minimum ran for more than 10 years in 2 different modes, in neutrino mode and antineutrino mode. And it also saw an excess of electron-like events. And since both of these experiments operate a similar ratio of energy to baseline, namely 1 kilometer per GeV, if this and see a consistent appearance of electron antineutrino events, this points to a mass square difference of around 1 electron volt square. These observations are not alone. There are also other interesting observations. So in this table, I show you in the top row, the neutrinos channels, and in the bottom row, the antineutrino channels. And then each column shows you the type of analysis that we have performed, people have performed. So on the leftmost, you have see electron appearance. Then the center column shows you mu neutrino disappearance, and the rightmost column shows you electron neutrino disappearance. I highlighted here in light red experiments we have seen some anomalous observation that is not compatible with neutrino expectations, and I mark those with red. And so you see that we see something strange going on, of course, in minimum LSND, which is what mostly motivates these searches, but also some interesting hints in electron antineutrino. No, 2 notable cases is the gallium anomalies and the recent neutrino 4 statement. However, we will see no anomalous results in mu neutrino disappearance. And I will go into more details on these particular observations in a minute. What I want to point out is that the anomaly seems to lie along the line. So in the horizontal axis of this plot, you see the energy of the neutrino experiment. And in the vertical axis of this plot, you see the distance between the source and the detector. And so the experiments that have seen something unusual, I put them in red color here. And experiments that have seen nothing unusual, I put them in black. And so you see that the experiments that see unusual appearance or disappearances are along the line. However, there are also experiments that do not see nothing, for example, Prospect here, or Minos, which brackets these lines, that put constraints or tension in this particular interpretation. So what is this interpretation in more detail? So the vanilla solution of this series of anomalies is the light neutrino solution. And that implies to add a heavy mass state called Nu4. And the heavy mass state is mostly comprised of sterile neutrino flavor. And by sterile, we mean that it does not participate in the standard model electroweak interactions. And the heavy mass state has a small component of active flavors, here showing colors, red, yellow, and the lightest blue. And so the game here is to try to figure out what's the mass score difference between the lightest and the heavier mass states, and what is the amplitude of electron, muon, and tau mixins in the heavier mass states. Beyond the LSND and minimum result I showed you earlier, we have also performed measurements of electron neutrino disappearance, which I was hinted earlier. This slide summarizes the latest of these results. The electron neutrino disappearance was originally, well, about 10 years ago, made of interest due to something known as the reactor antineutrino anomaly, which is an overall deficit of electron antineutrino events from reactors. However, the uncertainties in the reactor flux have been questioned, and it's not very clear if the reactor antineutrino anomaly is due to sterile neutrinos, or is it due to mismodel of the reactor fluxes. In order to go around this, these new experiments that you see in the slides do not use the actual flux of the reactor, but actually, or rather the absolute flux of the reactor, but rather do ratio measurements at different positions. So different experiments have different strategies. Of these experiments, only neutrino 4 claims to see something at high mass score difference, around 7 electron volt square, whereas the other experiments do not see any indication or significant indication of neutrino electron disappearance compatible with light sterile neutrino, and are carving into the reactor anomaly region, here showed as different shaded vertical colors. Muon neutrino disappearance has also moved forward. Here is a plot that shows the result from a couple of years ago. And you can see here in the horizontal axis, the muon mixing, and in the vertical axis, the mass score difference. Muon neutrino disappearance is dominated by 4 experiments. Minos and Minos Plus, which covers most of the mass score region of interest. The IceCube experiment, which I will talk later on, which covers very well between 0.1 and 1 electron volt square. Then CDHS and minimum muon neutrino mode. So if you take the anomalous LSND results, minimum results, you take these electron neutrino disappearance constraints, you take the muon neutrino disappearance constraints, which have seen no significant observation, and you put them into a big pot and you stir those around, you do a combination of all these experiments, you will find out that there is a quite statistically significant preference to have something beyond the three neutrino paradigm. So in this plot you see here is the resulting like global parameter combination. This hasn't changed significantly in the last years. So the horizontal axis is the amount of conversion between muon and electron, so the amplitude of muon neutrino to electron neutrino oscillation, and the vertical axis is the mass score difference. So the data really wants to have something additional to 3+1. However, I will tell you that this is actually in an interpretation that's in severe trouble. And the reason is that the appearance and disappearance signals should be related. So muon neutrino to electron neutrino appearance, electron neutrino disappearance, and muon neutrino disappearance are controlled by 3 parameters: the amount of electron in the heavy mass state, the amount of muon in the heavy mass state, and the mass square difference that tells you the oscillation frequency. So the short baseline approximation, these oscillation probabilities are given by the formula shown here. And you can see that if LSND and minimum are claiming to see appearance of electron neutrinos, that means that the product of U mu4 times U E4 cannot be 0, which means that individually, none of those can be 0. That implies that we should be able to see electron-neutrino disappearance and mu-neutrino disappearance at a correlated amplitudes. And we should see them also at the same mass square differences. However, that is not what we observe. If I separate the overall data sets into two data sets, the left, I have the appearance data sets, essentially LSND and minimum. And in the right set, I put the disappearance data sets. You see that the appearance data sets, they want to have small mass square differences and relatively large mixing angles, whereas the disappearance data sets want to have high mass square differences and small mixing angles. And in these two plots, the crosses I see in black are put in the same position. And so you can see that there is not a single overlapping solution point between the appearance and disappearance data sets. This is a conclusion that is not only from the global fit group that I work with, but it's something that every global fit working group agrees upon, that there is just no good solution. So the 3+1 model is severely disfavored by the tension between appearance and disappearance statement, and this tension has been growing and growing in a way that is now extremely unacceptable. We should also be mindful that cosmology seems to put a very strong constraint in the existence of light particles. So you can see this in the plot on the right. So in the horizontal axis is the electron mixing, in the vertical axis the mass square difference. The region preferred or allowed by cosmology rather is the region in blue, and the regions preferred by reactors, which is to first order the region of interest, are shown in black. And you can see that there is a big disagreement with cosmology. Theories have been working around trying to get around these constraints, but at the moment there is no satisfactory solution to the tension between light cell neutrinos and cosmology. So for me, this means that the 3+1 model, though it is able to explain LSND and minimum and maybe some of the other anomalous observation, it just doesn't work as a global solution. It's essentially ruled out. And so that brings us to what I call the garden of working paths, which is to ask ourselves, so what do we do now? So there are a bunch of questions that you could think about. So for example, you could ask yourself if the standard model backgrounds that minimum has are well understood enough. There's been a lot of discussion about, for example, coherent delta production. You could also ask yourself if maybe we are seeing different kinds of physics. So for example, are all of these anomalies related? Is minimum, LSND, and the reactors, are they seeing the same thing? Maybe two of them are seeing the same things. Maybe they're actually three different things. We do not know. We should also think about that when we do these combinations, what's guiding this tension is really a combination of different experiments. We tend to look more into the anomalous ones, but we should be mindful that the negative results also need to be checked, because if we accidentally rule out this model, we will be in trouble. The electron-neutrino disappearance signals, as I was saying, all of the experiments do not seem to see any indication. However, neutrino 4 seems to have statements that they are seeing something. This should be clarified. Mu-neutrino disappearance is the biggest problem that the light cell neutrino faces. And I will talk a little more about recent hints for mu-neutrino disappearance in the IceCube data set, if that is maybe compatible with what we're seeing. And in general, we should be mindful and think about if this is actually a real deal, how can we actually put this into a theoretical framework that makes sense? So I'm going to step back for a second and see what we actually know and see how we put these pieces together. So LSND saw an excess of electron antineutrino events. So we know because it's the IBD process, we know that actually what they saw. Minimum saw an excess of electron-like events, both in neutrinos and antineutrino modes. Reactor experiments using ratios see some hints of oscillations of large square difference, whose significance is not very clear at this stage. Mu-neutrino disappearance has resulted in very weak signals or no signals at all. If there are any signals, there are large mass square differences. The anomalies seem to lie along the line in L over E. And finally, cosmology seems to disfavor generation neutrino, though the recent tensions in the Hubble parameter seems to indicate that we may be missing something in the overall picture of our universe. So I'm going to try to classify this piece of evidence into two categories. Some of these look to me that could be indications of some new oscillatory behavior. Some of them could be indications some additional new physics has nothing to do with light cell neutrinos. So I quickly just gather them around. So for example, the fact that the anomalies are all in a L over E line, that's actually really interesting, it's really unusual. That seems to be fit well with an oscillatory explanation. However, other things do not. For example, the lack of mu-neutrino disappearance, is, of course, put tension in the oscillation interpretation. The fact that cosmology essentially strongly disfavors a light neutrino and requires additional physics seems to indicate something else is missing. So some of the elements suggest that there is something like 3+1, but something else seems to be missing. So I'm going to give you two tasters of what may be missing here. So I'm going to talk first about why do we not see anything in mu neutrino disappearance. So the strongest mu neutrino disappearance observation that we have to date is the recent one by SQ that was published last year. And again, it's not very significant. You see that the null result, the null hypothesis is only rejected at 8% p-value. So this contour that you see here in this plot, by the way, here the horizontal axis is the mu neutrino appearance and the vertical axis the mass core difference. This contour you see here is only close to 90%. But the SQ result is interesting because it's because of two reasons. First of all, the SQ neutrino analysis is different because it doesn't actually work on vacuum. It works due to the presence of a matter resonance effect that enhances the oscillation probability between active and stellar neutrinos. So what SQ does, it measures the atmospheric neutrino distribution as a function of direction, which gives you the length of the trajectory from the source to the detector, and as a function of energy. And for there, they can extract two parameters, the mass core difference and the mixing angle. So you can see how the oscillation looks in the bottom plots. So in each bottom plot, the horizontal axis is the cosine of the zenith angle, which tells you the direction of the neutrino, and the vertical axis is the energy of the neutrino. And you can see that there is this red blob, which is a resonance conversion of anti-electron, anti-mu neutrinos to stellar neutrinos. So they look for this dip. The other thing that's interesting about the ice-cube result is that it also is the most significant mu neutrino disappearance, but again, without even getting to 2 sigma. But what's interesting is that the result is in the region of parameter space that is also hinted by the short by the global fits. So you can see here in this plot, so the ice-cube results are shown different significant levels, but the global fit regions are shown here in colors, and you can see that they're quite in the same neighborhood. So there is, it's interesting, but it's not significant. So in light of what I was saying earlier, that we must be missing a piece here, it's interesting to re-examine that maybe the problem here is one of the reasons that we're not seeing mu neutrino disappearance is just because we are testing the wrong model, since we have essentially ruled it out due to the tension between appearance and disappearance results. And this reminds me of like this sort of like games that we play with children. We're trying to pick some shapes, and if you just put the wrong shape, you're just never going to get a satisfactory answer. So what have people thought about that could be variations on this theme? So one possibility to have stellar neutrino decay, and this has been proposed now several years, and the idea here is that you have your stellar neutrino, could be heavy, could be lighter, and it's allowed to decay via some new force. Depending on the nature of the neutrino, this decay can be invisible or visible. If the neutrinos are Dirac, it produces an invisible decay. If they're Majorana, it produces a visible decay. So this has actually been looked at in the global data set. If you actually take the global data set, that means appearance and disappearance experiments, and consider the case of stellar neutrino with invisible decay, it turns out that the tension between appearance and disappearance gets significantly reduced, and the fit quality also improves significantly. So the question is can this be tested? Can we then do another test to see if we're in the right direction? So this, for example, this global fit that you see here, what matters is the table in the bottom, shows you that there is an improvement with respect to null hypothesis, but we know that already, but there is also an improvement with respect to 3+1. And so the question is if this improvement holds in the next measurement we can do. And what was shown by Graham Parker earlier this week is that there is a new ice-cube result that looks into 3+1 plus decay, which is the same that I was showing you earlier. And the latest result seems to have an indication of a preference towards no decay scenario. So you see here is in the horizontal axis is the coupling strength that mediates the decay of the light stellar neutrinos, and the vertical axis is the delta likelihood. And you can see there's at least a mild preference towards this scenario. So I think that's interesting. So now let me go back to my list of things that may be going on. So another thing is interesting is looking at the minimum excess. So the minimum excess could be due to oscillations, but I will show you that maybe there is something that's going on here as well. So if we look at minimum, show you this plot here. The horizontal axis is the energy of the neutrino, assuming a quasi-elastic interaction. And I have divided this plot into two regions, the high regions, which is about 400 MeVs, and the low, what I call the low region below 400 MeVs. And what is interesting here is you see the histogram of colors, which are the backgrounds, and you see the dash histogram, which is the best fit hypothesis according to 3+1 model. You see 3+1 model does a pretty good job in actually explaining most of the high energy range. In fact, that high energy range was the range where originally LSND parameter space was supposed to be observed. However, the low energy part doesn't seem to be explained at least fully with a 3+1 explanation. This is not new. This was already pointed out by Carlo Giunti now many years ago, that the low energy part just doesn't look like an oscillation at all. So the question is there something else? So to think about this question, we need to switch gears a little bit. We need to stop thinking about the ratio of length to energy. We need to actually look at the excess in terms of its kinematic quantities. We need to look at this angular distribution, which is shown in the top plot, and its energy distribution, which show you in the bottom plot, which is seen already. And we have to be mindful that the excess in minimum is actually not necessarily an excess of electron neutrino events. It's an excess of electron-like events. Being minimum, an oil-Cherenkov detector, it actually cannot distinguish between photons and electrons. Here I show you the minimum morphologies. It can differentiate a muon from an electron. It can, to some capacity, differentiate between a pi naught and a single electron. But between an electron and a photon, it cannot tell apart.
So 5 minutes left.
Yeah. Given this low energy excess that may have a different origin, and this ambiguity in what minimum is actually observing, there have been lots of avenues of investigations in the literature. So people have talked about like new signatures. So for example, you have a heavy neutrino that through a magnetic moment interaction produces an extra photon in the detector. You can have heavy neutrinos that have a new C prime interaction. You can have also heavy neutrinos produced in the target that then decay in the detector. There are two of these scenarios. Sometimes they decay into an electron neutrino. Sometimes they decay into a photon. There's also ideas of having maybe the high energy part is just normal oscillations and the low energy part is some other oscillatory behavior. I already talked about stellar plus decay, but there's been discussion of stellar plus NSIs and or things like that. And then there are also more baroque solutions where you can just take two of these ideas and put them together to see if it works better. In general, the menu is quite broad, and how we're going to test this is quite different. So let me just talk about one of these cases. So in this scenario, for example, how will that work? You have mu neutrino that has there is a heavy neutral lepton that has its charge that U1, that's accompanied with a C prime. So what happens here is a new mu can upscatter into a heavy neutral lepton, and then that can subsequently decay, making a pair of electrons. If the parameters are just right, that pair of electrons can look like a single electron in minimum and fake the signal. This sort of model does a really good job in actually explaining the angular and energy distribution of the minimum excess. You can see that in the bottom plots, and the parameter space of this model shown on the right. However, now we have now we are in a non-oscillatory explanation. Now they have different ways of testing these explanations. So now if we have introduced this new scattering that produces electron pairs, then immediately we can actually test in a different way. So for example, what you can do is you can look at measurements of electron neutrino scattering in a similar way that this minimum excess produces 2 electrons. In the case of, it's something that you can actually see in measurements of electron scattering as well. And so if you look at measurements of neutrino electron scattering, but for example, CHARM and MINERVA, you will see that puts severe constraints on this particular type of explanations. I will not talk about the other examples, but essentially all of the other examples in my menu had some caveat or there's something going on there. So we still don't know what way we're going to go forward. So let me now tell you what is ahead of us. So I think that one thing I want to highlight, and was mentioned in a talk by Maruyama earlier this week, is the upcoming JSN square experiment. JSN square is really interesting, I think, because it's essentially a direct test of LSND. It uses a pion decay at rest beam and uses IV detection as a detection principle. Here you can see how it performs in comparison to, or in the framework of a light stellar neutrino. But again, what I hope you take of this talk is that we have to do direct tests of LSMD and minimum rather than thinking about the 3+1 framework, which is essentially do a good benchmark. It doesn't seem to really work. So I think this is really going to be really exciting when we get results from there. Another interesting is the short baseline experiment at Fermilab. This was a talk by Bonesini earlier this week. And the short baseline program actually has 3 detectors: the SBND detector about 100 meters from the booster beam, the micro detector about 500 meters farther away, and then Icarus 600 meters farther away. And so here you can see the performance of SBND. Again, it's able to very nicely cover the region of interest. So this is actually going to be a very good direct test of the minimum low energy excess. It will tell us if, because of the capability of liquid argon to differentiate between electrons and photons, it will inform us if the excess is due to photon events and electron events. And that's really going to steer us in one or another direction in that big array of possibilities that I was showing you earlier. Additionally, because it has 3 detectors, we will be able to perform new searches of electron neutrino appearance. Other ideas are to use more precise beams. So ISODAR is an idea to use, instead of a large radioactive source, to make to induce the decay of isotopes to produce neutrinos via beta decay. And you can see here the expectation of ISODAR next to kiloton scale liquid argon detector in Korea, in Gemilab. And what's interesting about the ISO proposal is that they're able to trace the oscillation wiggle. They have enough statistics that they can actually see the oscillation going up and down, which I think will be quite convincing. And as well, because they have a very good understanding of their beam, they can also differentiate between different scenarios. So for example, on the right case, I'll show you the case with decay, on the left one without decay. So you could start disentangling these 2 cases. And I invite you to see Lloyd's Wade's talks on these experiments. Also, ice cube in Antarctica is not quite done. I invite you to see Kayla's Leonard de Holton's talk earlier this week for upcoming results from Ice Cube. The results I was talking to you earlier with these hints of mu neutrino disappearance are all related to the Ice Cube high energy events. And by high energy, we mean typically above 500 GeV. The Ice Cube low energy sample, that means below 100 GeV, is not being just studied and has a complementary reach to the high energy analysis. And so if they see something there, that'll be very interesting confirmation of something interesting going on. So you can see here the plot on the right, the sensitivity that the analysis will have. And in the right, and the plot on the right, it's expected range of analysis range. So just to summarize my take-home messages, 3+1 model is disfavored as a global solution. Maybe it's part of the solution. Alternative explanations of the short baseline anomalies have been proposed. I mentioned a bunch of them: 3+1 predicate, presupposition design, nominal net leptons, etc., etc. The low energy part of minimum hints to a non-oscillation explanation. There are lots of ideas out there, but we definitely need more data to solve the short baseline puzzle. And I'm excited to see what will happen in the near future. With that, thank you, and I look forward to your questions.
Thank you, Carlos. Questions? So I see a question by Emilio. Please go ahead.
Okay, sorry, this could very well be a very naive question, but if you have 3+1 plus decay, are you supposed to see like a decrease in the flux, for example, of solar neutrinos? Like if they propagate for a very long time, they should always oscillate and decay, no?
Yeah, that's a good question. So if the decay is visible, actually solar neutrinos are really a big trouble for visible decay, because in that decay process, you produce an antineutrino in the decay. And we have very strong constraints of antineutrinos from the sun. So that is what limits the strongest constraints on the visible decay. So for the invisible decay, I think your argument is correct, that there is a problem there could be a problem with the luminosity, right, of the sun. And I haven't checked those numbers, or at least don't know those numbers on top of my head. But yeah, that could be a probe. I do not know the answer to your question in that case.
Okay, thanks.
Okay, is there any question in the plenary room? Microphone seems off.
No, it doesn't seem so.
Oh, okay, yeah. Okay.
There is, you have
there is, yes.
a hand raised. Maybe it was a previous one.
Ryan, yeah.
Hey, Carlos. How you doing? I have a quick question, which maybe there's not a good answer to, but to what extent can this correlation in L and E, you know, these experiments going along a line, just be explained kind of by, it's not really anthropics, but we build experiments along this line. We happen to have built a lot of experiments along this line, and we continue to build experiments along this line, motivated by these excesses. So we're bound to see anomalies along this line in L over E because it's the region that we find interesting.
So I think that the LSND and minimum one, we definitely did it for anthropic reasons, right? These two are correlated 100%. And so the question is if the reactor anomaly was done on, I mean, the latest one for sure is done on purpose. If the original one, for example, the gallium anomaly was certainly not done on purpose for that, right? So I agree that LSND minimum for sure, that's anthropic. The new reactor ones, those probably also anthropic. The gallium anomaly is not anthropic, and the reactor antineutrino anomaly is also not anthropic.
And so how much weight do you put in these reactor anomalies? I'm a little ignorant, but my own bias is just that the uncertainties are so big, and this work from Patrick.
So the reactor anomaly, I think that people, at least I don't put much weight in the reactor antineutrino anomaly because of it's essentially a theoretically driven anomaly, right? Which for me is not necessarily always an anomaly. But the ratio measurements are the real, more robust measurements. And so I think that what I saw is that the prospect and other experiments are not quite at the reach to really rule out and confirm neutrino 4. And so I think that when they pass that point, if they see or not, we will see like, okay, if they don't see it, then essentially there's nothing. If they see it, then I think that will be a robust statement.
Okay, cool. Thanks.
We have a question here in the room by Andrea Longin.
In relation to the reactor neutrino anomaly, maybe something new that I saw at this conference is that maybe the deficit seems to be concentrated when the fuel is uranium rather than plutonium. What do you think?
Yes, I saw that. I mean, I don't have the plot I want to show for unfortunately, but yes, that will be an indication that will not work with a slight cell neutrino. In my memory, that's still not. Let me say like this: if you take the Huber-Mueller as the benchmark flux model, then yeah, there seems to be a discrepancy with respect to that baseline model. But I'm trying to, the problem is yeah, I know. I think that if that were to be confirmed, that all the reactor anomalies due to a single element at high confidence, then the answer will be that will definitely put a killer into that region. But again, for me, the reactor antineutrino anomaly is no longer the biggest reactor-based statement on light cell neutrinos. For me, the statement is the ratio measurements. So that could well be, and I wouldn't think, if the reactor antineutrino anomaly is gone, but the ratio measurement sees something where the things are still okay. Sorry, I'm going to give you a better answer. I will email you a plot later that I think will make more sense. I just don't have it right now to make my argument.
No, but I think I understand what you mean, and I agree.
Okay, I think here in the room we don't have any more questions.
We had online one more question by Emilio, or is that an old hand?
No. I already answered myself my question.
Okay, good.
Okay, thank you.
Then there are no more questions, and let's thank Carlos for his presentation. And yeah, bye. And so since we changed the order of the sessions a bit, since Carlos had to go teach, I would, and actually there's just, I received a few minutes ago also a cancellation actually from Goran Senjanovic, and so I received the slides from him, so I posted them, but I would propose, since people didn't get a coffee break, that we take a break now and then start with Chandip's talk at 5 p.m. Is that okay with everybody? Or when we start Sanjip's talk on time?
Okay, fine. So 5, then 5:30, and then we will have the committee meeting. Yes, that's okay.
Okay.
Sanjeev was there, keeping the engines, but he had to switch off again. Yes, and I left my phone.
So we'll restart the session in 1 minute.
Hi, Carsten.
Hi, Sanjeev. Are you ready?
So let me share my screen if you allow.
It should be allowed, actually.
Okay, let's try.
Yeah, but let's try it out. That it works.
Just a minute.
So I propose that we take a group picture now. If you don't mind, we go there, we take a picture, just 1 minute. Outside? Carsten,
Yeah.
just we take a group picture, one minute, and then we come back.
Yes.
Okay, yes.
Sorry, but it's a good moment for a group picture. So, let's go outside the cafeteria. Even better. With them on the here, with them on the there.
Yeah,
That
but,
is also a good idea.
but not with masks.
I will call you.
We all are breath. We don't breathe. So outside, you could switch on your cameras, and you will be also in the group picture. No, away. We need them back. We need that.
Can you see my slides, Carsten?
Yes, yeah, we can see your slides.
No, no slides.
Can you stop sharing for now?
Yeah, stop sharing. We need back the Zoom. All the people.
So if people can switch on the camera, we can take a.
Can we show the hearers? To the hearers?
Is it possible to? Yes, exactly.
No. Hi. If people can switch on their cameras, you will be part of the group picture. It's a hybrid picture. But to look like us, you should put on masks. Just kidding. So we have more cameras can be on. Let's see who's actually listening to the session.
Okay, maybe we come here. We really need to keep the mask. We come here and okay, we can keep the mask, no problem.
No, we can hold our breath for 1 minute.
If you want to go in the picture, you have to keep the mask on. I wouldn't take it off because we will get some nasty comments if you do.
Maybe they kill them.
No, non c'è francese. We're ready to start. Can I put up my mask?
Don't blue then.
Thank you.
Questo lo introduciamo con Photoshop.
So now we can go to talk.
Okay, good. Okay, so let's get started. With the
Carsten,
last
can you
part.
see my slides now?
Yes, yeah, we can see your slides.
And they are changing? They are changing?
Yes, they are changing.
Okay, great.
Okay, so we have the last speaker of the session now, Sanjeev Agarwala, and yeah, he will talk about exploring BSM physics with neutrino oscillation experiments. So.
Okay, should I start, Carsten?
Yes, please get started.
Okay, so before I start, I would like to thank the organizers, especially Walter and Francesco. They finally could manage this workshop in this year in spite of all these difficulties. And so a big thank to both of them and their team for organizing such a nice workshop. And I really enjoyed offline all the slides that they have put, they are discussed during this conference. And also I would like to thank them that they have invited me to talk on this topic, which is very close to my heart. So Walter told me that I should discuss, the prospects of BSM physics in neutrino oscillation experiments. So before I begin, I must admit that this topic has been discussed quite rigorously in this workshop. And I was looking at the slides and, most of the topics have been covered. So I was thinking that what else I can add. So let me try if I can, motivate you that why, should we care about BSM in neutrino oscillation experiments and what is lying ahead for us. Okay, so I'm going to my first slide. So when we think about neutrino oscillation experiments, immediately, we have three pictures. You need to produce neutrinos through some, interaction, charge current interaction. And then you need to allow those neutrinos to travel from source to the detector. And they travel in the mass basis, and you produce neutrinos in the flavor basis. And then you need a big detector to detect these neutrinos. So you have three stages in a neutrino oscillation experiment. One is production, then propagation, and then the detection of neutrinos. So when neutrinos are produced or detected, they are in the flavor basis, but when they propagate in the mass basis. And we don't know, and we really know, we know with the utmost confidence that these two bases does not coincide for neutrinos. And that's why, this whole phenomenon of neutrino oscillation came into the picture. So when we think about neutrino oscillation, we immediately need to worry about 6 fundamental neutrino oscillation parameters. There are 3 mixing angles, 2 independent mass square differences, and 1 CP violating phase delta CP. Here I am just talking about the basic 3-flavor oscillation picture. Now, what has happened in last 10 years or so, we have achieved remarkable precision on these parameters. And just to motivate you, I thought this kind of plot would be very nice. So what is there in this picture? I'm trying basically, I'm comparing the 3 global fit studies, on these neutrino oscillation parameters. We had a fantastic talk by Professor Thomas Suez. He also talked about this global fit work. But you can see on the top, we have these 3 mixing angles. And below we have the solar mass square difference, then we have atmospheric mass square difference, and the CP violating phase delta CP. Now you see that all these 3 global fit studies, they are agreeing well with each other. And this tells you that the data is so robust, and this phenomena is also very simple, but at the same time, it is very robust. And here, the red line, when you fit the data assuming normal mass ordering, and this blue line when you assume inverted mass ordering, because we just have a hint for this ordering issue at around 2 sigma confidence level. And this is the responsibility of currently running and future oscillation experiment to nail down this issue. So here you can see the most important thing that I would like to highlight, the delta CP. For last 20 years, basically, we have been discussing that the entire range of delta CP is allowed, and we had the landscape of from 0 to 360 degree all the way. But when I was preparing this plot, I didn't need to introduce the range between 0 to 90, because if we believe the data that we have now, the delta CP range between 0 to 90 degrees almost ruled out at more than 3 sigma confidence level. And thanks to the experiment like T2K, NOVA, they are doing a fantastic job. And also the data that we are having from Super Kamiokande atmospheric experiment, because recently they could manage to reduce their threshold, and also they could manage to distinguish, at least statistically, the neutrino and anti-neutrino event sample. They have better background rejection capabilities. So everything is positive as far as Super Kamiokande is concerned. And they are also contributing in this landscape of CP phase. So we have started probing CP violation. And you see that all the global fit studies are also matching quite well. But most remarkable is this precision that we have achieved. So if you see theta 1,3, we just started in 2012, and within 8 or 9 years, this is the most precisely measured angle now in three-flavor oscillation sector. We have 3% precision on theta 1,3, 6% on theta 2,3. By the way, these are all relative 1 sigma precision. On theta 1,2, we have around 4.5%. And for CP phase, for the first time, we are happy to quote a precision of 16%. So we are there on our target. And for frequencies, we have like 1.1% for atmospheric splitting and 2.3% for solar splitting. So this is the picture that we have. And I must say that because of this extraordinary precision that we have achieved, the whole discussion of BSM has started. Because when you know that your standard 6 oscillation parameters are under control, and you have a very good knowledge about those parameters, and the experiments are becoming bigger and bigger day by day, you have intense neutrino source, bigger detectors, you have better reconstruction of energy and the distance that neutrinos are traveling, and we have now better handle on systematic uncertainties. The systematic uncertainties that T2K could achieve in last 3-4 years, I must say it is extraordinary. And we hope that that legacy will continue further with hypercameo detector and also the liquid argon technology, the Dune experiment, and there are many other small scale liquid argon experiments are going to start. So that legacy will certainly continue, and we will have better handle on our systematic uncertainties. Another thing I would like to highlight, our cross-section uncertainties. We have now better theoretical understanding, and also the data from Minerva and the data that we are having from Argonute or Microboon, they are going to add to that information. So overall, we have better handle on systematics, we have better control on our cross-section uncertainties, we have intense source, better detector, and top of that, this high precise measurement of oscillation parameters. So I would like to motivate, before I flash some results from some experiments or future sensitivities, this is the biggest motivation for me, that we have started talking about that, okay, can these experiments reveal presence of some tiny amount of BSM? But keep in mind, neutrino oscillation is already a signature of BSM. So we are asking more from these experiments, that if there will be any subleading effect via any BSM mechanism, then this experiment should be able to reveal that. So this is I want to talk about the motivation, that we have really a big motivation. And just I want to add that when you think about neutrino oscillation experiments, you should appreciate that over the last 20 years, we have probed this phenomena over an energy scale which is around like 18 orders in magnitude. And if you think about the length scale, which is more than 23 orders of magnitude. So if you look for BSM in neutrino oscillation experiments, you can really test your BSM physics at different length scale and energy scale. As you see, if you probe BSM with ice cube, which is beyond the range of your traditional accelerators. So it is really amazing that, we have a landscape of these oscillation experiments, and they are telling us that work hard and look for this BSM. And what is lying in future when I talk about oscillation parameters, I must talk about this Juno experiment. So here you can see in coming years, Juno is going to further improve our knowledge about these oscillation parameters. You see for theta 1,2, our present knowledge of 3.9% uncertainty will go reduced to 0.7%. For solar frequency, from 2.8%, we hope to reach 0.6%. For atmospheric splitting, whether you are in normal ordering or inverted ordering, we expect an improvement of factor of 2. So I must admit that Juno will improve, this is our hope, significantly our knowledge on neutrino oscillation parameters. And these developments are really crucial when we will try to probe BSM in future long baseline or atmospheric experiments, or even if you think about IceCube upgrade or IceCube Gen 2. Okay, so I told you that non-zero neutrino mass, which is required by oscillation data, is the first experimental proof for BSM physics. And you can introduce several BSM possibilities in the effective field theory framework. So on the left, you see the effective Lagrangian, where you have the standard model part, but you also have this dimension 5 or dimension 6 operators, where this dimension 5 operator, which was proposed by Weinberg, in 1979, this is the LLHH operator, where lambda is the scale of your new physics. And this operator can give you neutrino mass. And if you think about this dimension 6 operator, they can also give you some new interactions in your mechanism. So these BSM scenarios, they are not ad hoc. I want to emphasize on this point that when we invoke different mechanisms to generate neutrino masses, these BSM physics, these BSM scenarios naturally occur in the scenario. And if you think about these BSM physics, these various models, what they suggest? They suggest the possibility that there can be new fundamental particles, or there can be new interactions. You may think of new sources of CP invariance violation, or there can be lepton number or lepton flavor violations, broadly speaking. So when I'm thinking or I'm talking about BSM in neutrino oscillation physics, what basically I am invoking in my picture some new fundamental particles or interactions, or some new source of CP violation, or lepton number or lepton flavor violation. Now, how we can probe them? So we have basically, if I categorize all the possibilities, I can see two different alternatives. One, if you think about very high energies. So at very high energies, I mean TeV, PeV energies, okay, we have these giant neutrino telescopes like IceCube at the South Pole, or KM3net in the Mediterranean Sea, or future IceCube generation 2, and they are all detecting these high energy astrophysical neutrinos. And they are coming through far distances. The distances are around gigaparsec to megaparsec to gigaparsec. So when you allow neutrinos to travel such a long distance, if there is any new physics, that can be accumulated on the way. And this approach will make us able to probe BSM at some energy scale which is beyond the reach of modern colliders. So this is fantastic, in my opinion. And if I go further, and if I look at lower energies like MEV or GV energies, we have these accelerator and atmospheric neutrinos. And they are traveling few hundred meters to few thousands of kilometers. And we have very good candidates in future, like DUNE in US and T2 Hyper K in Japan. And both the experiments have been discussed in detail in this workshop, and also some atmospheric experiment. Don't forget that this Hyper K or DUNE, they are all going to measure also atmospheric data. They are all going to collect atmospheric data. And there are also possibilities of the experiment like India-based neutrino observatory, where we have magnetic field. So you can distinguish between muon and anti-muon events in your detector. And these experiments, we believe that they will measure the oscillation parameters, or the issue of CP violation, mass addoring, or the octant of theta 2-3 very precisely. And therefore, I think it makes sense to ask whether these experiments can reveal the presence of any subleading new physics effect. And these searches at lower energies will certainly complement our BSM searches at high energy colliders like LHC. So let me proceed. So when we think about various BSM possibilities, a plethora of possibilities have been explored in the literature, starting from sterile neutrinos, non-standard interactions, long-range interactions, possibility of neutrino decay, or possibility of low-range invariance violation, decay of dark matter annihilation, extra dimension, a lot. So in this talk, in next 10-15 minutes, I'll be able to touch few of them, but not all of them. So when we think about neutrino experiment, I just explained in the beginning, you need to produce neutrinos. So here you can see that, these are not very rigid. This classification is not very rigid. This is just to give you an idea. So these are the various new physics possibilities which can affect the production of neutrinos. So the neutrino flux can be altered. Now let me proceed. If I think about neutrino propagation, so if new physics can occur during the propagation, they can alter the neutrino flux, or they can alter the oscillation or mixing mechanism. And most of these BSM physics, basically, they can affect your oscillation phenomena. You can see this ellipse. So most of the models comes into that category that they can affect your oscillation mechanism. And this has become a very hot topic, as day by day our measurement of oscillation parameters are becoming precise. Now, when you come to the detection, you can also have BSM physics at the detection. That means there can be some BSM physics which can alter your, detection cross-section of these neutrinos. For an instance, here I'm showing you the detection cross-section that we use in Borexino experiment. In Borexino experiment, we have the elastic electron-neutrino electron scattering cross-section. And you see, if you invoke some non-standard interactions which are purely leptonic, then these cross-sections can be altered. The magnitude as well as the shape of the cross-section can be changed. So this is just an example. Now, here I want to just show that how this entire gain can be accessed via experiments like IceCube, where you really probe very high energy neutrinos and a very long distance scales. So for an instance, in IceCube, we are going to exploit the information on energy spectra, or the information on arrival direction, or the information on arrival time of these neutrinos, or the flavor composition of these neutrinos. So we have this multidimensional approach when you think about these astrophysical neutrinos, and exploiting these variables, we can really probe various BSM models. And you can see with these threads, my friend Mauricio, he has tried to make a connection that which variable will be helpful to probe which BSM phenomena. So this is just an example, but you can also draw similar picture if you think about long baseline reactor or any such oscillation experiments. But there you will have different variables. Okay. So let me proceed. So in that direction, we did some work a couple of years back, and we showed that by measuring the flavor ratio at IceCube, we can probe a very, very small values of coupling and mass of new mediators, which are very light, and they can cause an interaction between these astrophysical neutrinos and the electrons that we have in big celestial bodies. This is what we call long-range interaction. And you can see, if we can measure this flavor ratio precisely in IceCube, we will be able to set tightest limits on the mediator mass and the coupling. And this coupling, you can see that we can probe is even smaller than the gravitational coupling. And you can see the landscape of the mass of the mediator. I can't think of any other experiment where you can probe such small values of coupling and the mass. But this is just an example. Let me talk very briefly about non-standard interactions. So these NSIs can affect the production, you can see here, or your detection or propagation. If you have NSIs in propagation, they are of neutral current type. But if you think of NSIs in production or detection, they will have charge current type. And I would recommend to go through these two review articles where they have reviewed this whole prospects of studying NSI in oscillation experiments in detail. And in this conference, I would recommend to go through these slides by various speakers, and they have covered this topic in detail. So just to give you an idea, the people from this publication, they have performed a global fit of all the available oscillation data in a framework where they consider that all the CP phases are 0. And they tried to put bounds on these NSI parameters. I will not read the numbers, but they gave us the bounds by analyzing the oscillation data in a two different framework, one with large mixing angle scenario, and then we have large mixing angle as well as the large mixing angle with LMAD solution. Okay, and they use the oscillation data along with the data from coherent experiment. So this is the bound that we obtain from this paper, and these epsilons are the phenomenologically relevant parameters that goes into your oscillation probability calculation. Okay, so and these are the bounds that we have from this very nice review by Mariam Tortola and Yasaman Farzan. What they have done, they have reviewed the literature very nicely, and they have collected these bounds for us on charge current NSIs, which affect the production and detection of these neutrinos when you plan a neutrino experiment. This is just a flavor I'm going to give, that the data that we have from solar experiment like Borexino and experiment in your lab with reactors like Texono, they can give you complementary information, because both these experiments are going to probe neutrino electron scattering cross section, and the role of this GL and GR, they switch their role, in when you think of neutrino and antineutrino, because in Borexino you deal with electron neutrino, but in Texono, which is a reactor experiment, you deal with electron antineutrino. And there is a nice piece of correlation or complementarity you have between Borexino and Texono data. You can see, so this is the combined constant from solar and Kamland, and this is the constant from Texono. And when you merge them together, your allowed parameter space become really small. So we need to keep an eye watch on all possible information, and we need to explore the complementarity among various data sets. I will not cover about sterile neutrinos. My previous speaker, my friend Carlos, has already talked about that, so I will just not cover this. So we have a bright future ahead to validate or reject this 3+1 hypothesis. But I will just straight away go to some discussion on CPT violations. So there are some unified theories such as string theory, which allow for violation of Lorentz symmetry. How? By introducing new space-time structure at the quantum gravity scale. And if you can really probe directly this Lorentz invariance violation signature at lower energies, you would be able to access some phenomena which is happening at the Planck scale. So in the standard model extension framework, you can introduce these LIV parameters. If you want to know details, I would recommend you go through these review papers by Costelletti and Muse, and they have nicely summarized the theoretical background and all possible constraints. And when you think about these LIV parameters, the strongest bound we are getting on dimension 6 LIV parameters from IceCube experiment. They had a fantastic publication in Nature in 2018, and you can see the strongest constraint that they can put by exploiting the IceCube atmospheric data. So we need to also keep an eye watch on this kind of BSM, where your new physics can come at different dimension level. Okay, now let me very quickly talk about neutrino decay. Yes, Carsten?
Yeah, just 5 minutes left.
Okay, so when we think about neutrino decay, just my previous speaker Carlos mentioned that you can elevate the tension between this appearance and disappearance if you are a little bit optimistic and you invoke 2 BSM. On top of oscillation, you have sterile as well as decay. So this is the decay that I'm talking about. So you can have 2 different types of decay. One is visible and another is invisible. So in an invisible decay, either the decay products are sterile neutrinos or they have sufficiently very low energy so that they have avoided the detection. And when you think about visible decay, it involves the regeneration of lower energy neutrinos, and it provides additional signature in your detector. So think like, an invisible decay of the heaviest mass eigenstate. Think like, that the M3 mass eigenstate is decaying to a sterile neutrino and a majoron. So if you work in that scenario, you can rewrite the oscillation probability expression of mu going to nu. And you can see that these decay possibilities are coming through this expression, where you have the lifetime of that decay process and the mass. So we have bounds on these decay parameters from super Kamiokande, K2K and Minos. This is the bound that we have from this paper. And from T2K and Minos, there is a study in 2015, and this is the bound that we have at 90% confidence level. Going further, there is a study based on T2K and NOVA. If they will collect the entire data, what bound they can put on this parameter. So this is the bound that we expect from T2K and NOVA. This is the bound that we can expect from the iron calorimeter detector at India-based Neutrino Observatory. This is the bound from Dune. This is the bound from Juno. So a lot of studies have been performed. There are limits from CMB, from solar neutrinos. So just take a look. So I just want to emphasize that this decay scenario has been explored in detail in the literature. And lastly, there was a recent paper by my friends Forero and Professor Junti, Tarnes and Totola. In this paper, what they did, they combined the information from short baseline experiments, especially NOMAD and NUTEF, and the data from long baseline experiment Minos, Minos Plus, T2K and NOVA. And they asked the question that if I combine these short baseline and long baseline data sets, can we put constraints on the possible violation of unitarity of neutrino mixing, which we call the non-unitary mixing of in the neutrino sector. And you invoke this non-unitarity in your picture with this triangular matrix with the help of these alpha parameters. And you can see they could manage to give a tightest bound on these parameters by exploiting this data. And you can see the bounds. And I hope that these bounds will be further constrained in the upcoming Dune and Hyper-Kamiokande experiments if they don't see any violation of this unitarity in their data set. So let me conclude. I must admit that I could not cover the huge amount of work that has been done even in last 5 to 10 years when you think about BSM in oscillation physics. It has become an industry. So what I tried here just to give you some flavor of some BSM scenarios, but I must admit, I would like to conclude with this fact that we have two different probes when you think about oscillation experiment. One is this high energy astrophysical neutrinos. I think we have high hopes from IceCube Gen 2 or the possible upgrade of this IceCube experiment in near future. And by exploiting several variables in this experiment, they are going to play an important role as far as these BSM scenarios are concerned. And remember, when you probe BSM with IceCube or Orca or Chem3Net kind of experiments, you are working at a totally different length scale and an energy scale. So you are just probing a different territory altogether. But at the same time, we have fantastic next generation high precision oscillation experiments involving atmospheric neutrinos, accelerator neutrinos, but there you work in MeV, GeV energies. And the length scale is smaller than the astrophysical neutrinos. So you have few meters to few thousand kilometers. So what I would like to emphasize that if I think about all these experiments, we will be able to probe BSM over a wide range of energies and baseline. I think that is the most important message I want to convey. That it is just not one data at one particular energy or length. You will have plethora of data at various energies and length scale to check that whether you are seeing some anomalies at some experiments, are we seeing the same anomaly at some different experiments? So I think neutrino oscillation experiments are going to play an important role to probe this BSM phenomena. And I think in next 5 or 6 years, when Dune or Hyper-K, these experiments will come online, this BSM physics will become the dominant physics topics in these experiments. So before I conclude, I apologize to my friends and colleagues. I didn't get time to talk about your excellent work. My apology for that. So stay tuned. We have a very bright future for BSM in neutron oscillation experiments. Thank you.
Thank you, Sanjeev, for this exciting talk. And we have time for questions.
Yes.
Yeah. Any questions in the plenary room? I don't see any
questions to Sanjeev.
I think we had so many talks in this workshop and people are already aware of everything. Credit goes to Walter and the working group.
No, congratulations for your talk. Also very entertaining. Very nice, very nice. Very nice, yes. Okay, thank you very much. I think, Karsten, you want to close the session?
Yes.
Thanks,
yeah.
Walter. Thanks, Karsten.
Yeah. So let's thank all the speakers in this session, and also remind you that Goran unfortunately had to cancel his talk last minute. So the slides are posted. If you have any questions for Goran, please also email him. And then let's close the session for today.
Thank you, Karsten. So now we go to the scientific program committee meeting. And so this is a restricted meeting. So I invite only the scientific program committee and the working group conveners to attend the meeting. Thank you. We start essentially now. Okay, so welcome to the scientific program committee meeting. So I don't know if Francesco wishes to say something, but there is no chairman at this meeting. So, I mean, it's self-organized. I can see 2 topics on discussion today. One is the selection of an next venue. And we have 2 proposals in our triannual rotation. The next year is for the Americas, and we got 2 proposals so far. I don't know if there is any other proposal over the last minute. And the second topic that we are going to discuss after, for which I also invited Matteo Cadeddu and Francesca